Welcome. Over the next 5 hours, we're going to cover microservices architecture patterns for software engineering interviews. We'll start from the fundamentals of what microservices actually are, and by the end, you'll understand how to decompose microservices, how they communicate, how to handle data ownership across service boundaries, and how to deal with distributed transactions and sagas. So let's get started. Now, here's exactly what we'll be covering in this course today. In the first section of this course, we'll spend 30 minutes on the microservices mental model. This is where we'll establish what microservices actually mean, the core promise they offer, the real costs they introduce, and how microservices relate to organization structure through Conway's law. This section sets up the vocabulary and the framing you will use in every microservices interview. Then in the second section of this course, we'll spend 45 minutes on monoliths to microservices decomposition transition. We'll cover the traditional monolith, the modular monolith, and the distributed monolith, which is one of the most common architectural mistakes teams make. We'll also cover when a monolith is actually the better choice over microservices. And then we'll walk through the Strangler fig migration pattern with a worked example, because interviewers frequently ask you, how would you migrate an existing system from monolith to microservices? In the third section of this course, we'll spend over an hour on service decomposition and boundaries. This is the single most important section in this course. We'll cover domain-driven design fundamentals, bounded context, aggregates, cohesion. We'll also walk through real-world service boundary examples for e-commerce, ride-sharing, streaming, and banking platforms, so you can see exactly how these patterns apply in real-world production scenarios. Then in the fourth section of this course, we'll spend over an hour on inter-service communication. In this section, we'll cover synchronous versus asynchronous communication, REST, gRPC, GraphQL, message queues, event streams, and the critical resilience patterns like circuit breakers, retry strategies, idempotency, and backpressure. We'll also cover contract versioning and distributed tracing with correlation IDs, which are essential for debugging in production microservices systems. Then in the fifth section of this course, we'll spend an hour on data ownership and read models. This is where we'll cover the database per service pattern, the shared database pattern, and why it causes problems. And we'll also cover cross-read, service reads and writes, CQRS with a worked example, eventual consistency, materialized views, and cache ownership. These are the data patterns that most candidates miss in the interviews, and understanding them is super important. And the sixth and the final section of this course will close with distributed transactions, covering the Saga pattern, orchestration versus choreography, the transactional outbox pattern, and idempotency in distributed systems. This section will tie together everything from the early sections into the hardest problem in microservices architectures. Before we get into patterns, protocols, or any specific design, we need to build a mental model. This section is the foundation that every other section in the course depends on. So most engineers, when asked about microservices, they will say something like, okay, there are small independent services, but that definition is incomplete. When your definition is incomplete, the design decisions you make on top of it will be incomplete too. You will make decomposition choices that look right on the whiteboard, but they will unfortunately fall apart under real production load. And in that case, folks try to, propose architectures in interviews that sound reasonable, but, they would have gap, that an experienced interviewer actually will be able to identify. Now, so in this section, we're going to reset. We'll cover what microservices actually mean, and I mean the precise testable definition. So we'll start with, we'll cover what microservices, also that do not mean, because the misconceptions are just as common as the correct understanding. Then we'll also walk through the three core premises of the architecture, which is independent deployment, independent scaling, and independent ownership. Then we'll cover the 5 core costs, because every one of those promises come with a price, and understanding what price is what separates strong interviewers from someone who might not do that well in the interviews. Also, we'll also look at why microservices are fundamentally an organizational decision through Conway's law, and finally we'll cover how to frame microservices correctly in a system design interview, because how you introduce your architecture choice in the first few minutes sets the tone for the entire interview conversation. Now, to ground all of this in reality, let's think of a platform like Amazon. So that would be, hundreds of engineering teams, each owning a microservice or multiple microservices, for example, catalog, cart, checkout, payments, shipping. Each of those microservices, would be built, deployed, and scaled independently. Now, Similarly, if you think about a streaming platform like Netflix, they will also have separate microservices for user profiles, recommendations, playback, billing, and content encoding. And then if you think of a messaging platform like WhatsApp, they will have independent microservices for message delivery, presence, media storage, and notifications. So now in every section that follows, that is upcoming in this 5-hour course, let's say, for example, a decomposition section to a communication pattern section or to data ownership and Saga sections, they all build in directly on the mental model that we'll be covering in this section 1. So let's get started. So now let's first cover, what actually makes something a microservices. A microservice essentially is a service that meets 4 criteria and has to meet all 4 simultaneously. The first is that it is independently deployable, so the service ships without coordinating with other services. The second is that it owns its own data. It has a private database and that no other service can access directly. The third is that it is aligned to a business capability. It represents a real business function, not a technical layer. And the fourth is that it is owned by a single team. So one team builds it, deploys it, monitors it, and is on call for it. Now, if a service meets only 2 or 3 of these, it's not a true microservice. It might be a well-structured component, it might even be a good piece of software, but it does not deliver the full benefits of the architecture because those benefits come from the combination of 4 properties working together. Now, let us test this with a real example. Consider an order service in a food delivery platform like DoorDash. First, is it independently deployable? Can the order service ship a new feature without requiring the restaurant service to deploy at the same time? Yes, as long as the APIs between them are version and backward compatible, that is possible. Second, does it own its own data? So for example, does the order service have its own orders database that no other service can query directly? Yes. So other services, they call the order API to get the order information. They do not connect to the orders table. Third, is it aligned to a business capability? So order management, which includes creating, tracking, and completing orders, is clearly a core business function. It is not a technical utility like a database access layer, so that is valid. And fourth, is it owned by a single team? More likely yes, or maybe multiple teams, but the orders team or the org, completely owns the code, the database, and the deployment pipeline and the on-call rotation. Now, the order service, it passes all the 4 criteria, so that is by definition it's a true microservice. But now here's a common pattern that breaks this. Many team builds microservices that share database. So for example, the payment service and the order service both read from the same orders table. So sometimes that happens in companies. They can be deployed separately technically, but they're not truly independent. If someone changes the schema of the orders table, say they rename a column or change a data type, both services break. So that fails its own, own its own data tests and the criteria. And once that property is gone, the dependence that microservices promise, they start to, go away. Now for interviews, this is what matters. When you say that, okay, I would use microservices as part of your architecture, an interviewer might follow with that, okay, what makes something a microservice? Being able to state these 4 properties clearly and test them against a concrete example will put you ahead of most candidates, who will just say something like, okay, it's a small independent service, which is not a complete answer to give in an interview. So now that we have the correct definition, let us clear out the misconceptions. These come up frequently in interviews, and they come up even more frequently in production systems where teams adopt microservices based on incomplete understanding. Now the first misconception is that, okay, microservices, they just mean small services. The micro in microservices does not refer to lines of code. A service with even 50,000 lines of code can be a well-designed microservice if it owns a single business capability end-to-end. A service with 200 lines of code can be poorly designed if it cannot handle a single request without calling 3 other services. Size is not the metric, independence and business alignment are the metrics. The second misconception is that microservices mean, they have to use modern tools like Docker and Kubernetes. So Docker and Kubernetes are deployment tools. They make microservices easier to operate, but they are not what makes something a microservice. You can run a monolith inside Kubernetes as well. You can run microservices on bare metal virtual machines with no containers at all. Containers are an operational choice. Microservices are an architectural choice. So these are 2 separate decisions. The third misconception is that microservices mean splitting code into separate repositories. Having 10 separate repos does not create service boundaries. You can have 10 repositories that are still all tightly coupled, and then they, for example, they might be sharing data models, and that must be deployed together in a specific order every time. That is distributed monolith, that is not microservices. So the boundary that matters is independent deployability and data ownership, not where the code lives in your version control system. The fourth misconception is that you should create one microservice per database table. This comes up in interviews, and it is a strong signal of a misunderstanding. If you split your user table into a user service and your address table into an address service, you have not decomposed by business capability. You have decomposed by database schema, so the result is a set of services that are extremely chatty. The user service needs to call the address service for almost every operation. Neither service can do anything useful on its own. The correct decomposition groups the user table and the address table together under a single user profile service, because managing a user's profile including the addresses is one business capability. Now, in interviews, mentioning Docker or Kubernetes as a defining trait of microservices signals that the understanding is not fully complete. Interviewers are testing whether you understand the architectural processes and properties, not just the tooling. So we know what microservices are and what they are not. Now let us look at what they actually give you. Microservices make three promises, and every architecture benefit from of the pattern flows from these three properties. The first promise is independent deployment. Each service can be built, tested, and deployed without coordinating with other teams. If the notification service needs a bug fix, only the notifications teams deploys. There is no release train. There is no waiting for the order service team to finish their sprint. That sounds simple, but in organizations with 50 or 100 engineers working on the same product, deployment coordination becomes one of the biggest bottlenecks. Independent deployment removes that bottleneck entirely. The second promise is independent scaling. Each service scales based on its own load profile, not a shared one. Think about an e-commerce platform like Amazon. The product catalog service handles reads at a rate that is roughly 50 times higher than the checkout service. With microservices, you scale catalog reads horizontally by adding more instances of that specific service without wasting resources on checkout infrastructure that is mostly idle. In a monolith, you would scale the entire application, even the parts that do not need it, because everything runs in the same process. And the third promise is independent ownership. One team owns one service end-to-end, so the code, the data, the deployment pipeline, the on-call rotation, everything is owned by one team. This matters because ownership boundaries reduces coordination overhead. A team of 4 to 8 engineers can move fast because they do not need approval from 6 other teams to ship a change. They make decisions with their service boundary, and those decisions do not ripple into other teams. Now, each of these promises comes with a trade-off. Independent deployments require backward compatible APIs between services. If the order service changes the API in a way that breaks the notification service, you have lost the independence. Independent scaling requires infrastructure complexity, so you need load balancers, service discovery, auto-scaling rules, and more moving parts than a single application. And independent ownership requires accepting data replication and cross-team communication overhead. When two services need the same piece of data, they each maintain their own copy, and keeping those copies consistent is a real engineering problem. And for interviews, this is what's pretty important. Let's say when an interviewer asks you that, okay, why microservices? Why you just do not say that, okay, because of scalability. You have to state all the three promises and then explain which specific promise justifies the choice for the system that you are specifically designing. A system with one small team and uniform load across all features does not benefit from all of these promises. The microservices overhead would cost more than the architecture delivers, so make sure you mention that in the interview. So we have talked about microservices promises. Now let us talk about what they cost. And these are not edge cases or rare failure modes. These are guaranteed consequences of distributing a system across a network. Now picture a request flow as shown here on the screen. A client sends a request to an API gateway. The gateway routes it to the order service. The order service calls the inventory service to check stock. It also calls the payment service to charge the customer. The payment service calls the fraud detection service to verify the transaction, and the order service calls the notification service to send a confirmation. Every one of those connections is a network call. Every network call can fail, so every network call can also time out, and it can also return stale data. In a monolith, all of those would be function calls within a single process, so that would take nanoseconds, and they would never fail because essentially of a network partition. Now, these are the 5 costs to understand here. The first is the network latency. Every service to service call adds 1 to 10 milliseconds of round trip time. A function call inside a monolith takes nanoseconds. When a single user request touches 4 or 5 microservices in a sequence, those milliseconds add up. A request that would take 5 milliseconds in a monolith now might take 30 to 50 milliseconds across microservices purely from network overhead. Now, the second is partial failure. This is one of the hardest problems in distributed systems. The payment service succeeds and let's say it charges the customer, but the inventory service fails and does not reserve the item. In a monolith, a single database transaction guarantees all or nothing. Either everything commits or everything rolls back. However, across microservices, there is no shared transaction. You need explicit strategies to handle, those partial failure scenarios, and we will cover those in detail in the Saga section later in the course. The third is data inconsistency. So the order service and the inventory service can temporarily disagree about stock levels. One service processed an update and the other has not received it yet. In a system backed by a single database, this cannot happen because both reads go to the same source. In a distributed system, temporary inconsistency is the default and you have to design around it. The fourth is debugging complexity. A user reports that the order confirmation never arrived. In a monolith, you open one log file, search for the request ID, and trace the entire flow in one place. In a microservices system, that same request might have touched 5 services across 5 separate log streams, possibly on 5 different machines. You need distributed tracing, correlation IDs, and centralized logging to even begin debugging. Without those tools, finding the root cause of a failure across services becomes extremely time consuming. Now the fifth is operational overhead. 20 services mean 20 deployment pipelines, 20 monitoring dashboards, 20 set of alerts, 20 potential points of failure. Each service needs its own CI/CD configuration, its own health checks, its own scaling rules. The operational burden grows linearly with the number of microservices. Now let us do the math because this makes the trade-off more concrete. A monolith making 4 internal functional calls to process a checkout has near zero failure probability from those calls. They are all in process, they do not cross a network. However, the same checkout flow across 4 microservices, each with let's say 99.9% availability, has a combined availability of 99.9% to the power of 4, which equals 99.6%. Now that difference of 0.4% sounds small, but the 99.9% availability means 8.7 hours of downtime per year, and 99.6% means 35 hours of downtime per year. That is an additional 26 hours of downtime purely from the architectural choice, not from bugs, not from bad code, just from the mathematical reality of distributed systems. Now in interviews, this is where strong candidates, they differentiate themselves. Proposing microservices without acknowledging these costs is a red flag at any level. The interviewer wants to hear that you understand, what you are signing up for and not just what you are getting into. And this is something you would want to write down for your interviews in this part of your notes. These 5 costs come up repeatedly in system design conversations, and being able to list them without hesitation signals practical experience with distributed systems. So yeah, these are the 5 costs of microservices. The first one is network latency. So every hop between services adds 1 to 10 milliseconds compared to nanoseconds for in-process calls within a monolith. The second is partial failure. One service can fail while others succeed. There is no shared transaction boundary to guarantee all or nothing behavior. The third is data inconsistency. Without a shared database, services can temporarily disagree about the state of the system. There is no single source of truth that all services read from. The fourth is debugging complexity. So one user request can touch many services, each with its own log stream. Tracing a failure across those services requires dedicated tooling. Fifth is operational overhead. So each service needs its own deployment pipeline, its own monitoring, and its own on-call setup. The operational cost scales with the number of services. And here's how to use these in an interview. You do not wait for the interviewer to challenge your microservices proposal. You actually state the cost proactively and then explain how you will handle each one. A strong patterns will sound something like this. Okay, I'm choosing microservices here in the interview because independent scaling matters for this system, and I will handle the distributed complexity by using distributed tracing for debugging, implementing the Saga pattern for cross-service transactions, and using eventual consistency with the idempotent consumers for data sync. When you give that kind of answer in the interview, it shows the interviewer that, okay, you're not just picking an architecture, you're reasoning about the consequences and planning for them. This is what separates a senior level answer from someone who might not have that much experience. So this is very important. You mentioned that in the interview. So far, we have looked at microservices through a technical lens, the promises, the costs, the properties that define them. But there's another dimension that is equally significant, and it is organizational. So Conway's law states that, okay, organizations design systems that mirror their own communication structure. This is not a suggestion or a best practice, it is just an observation that has held true across decades of software engineering. Let's say if you have three teams, you will end up with three major services or three major components. If two teams do not talk to each other, their services will not integrate well. The communication structure of the organization shapes the architecture whether you plan for it or not. So what this means for microservices is pretty important. Service boundaries should follow team boundaries. If the payment team and the inventory team are separate groups with separate managers and separate priorities, their code should live in separate services. Forcing them into a monolith creates a constant merge conflict, shared on-call rotations where neither teams feel full ownership, and deployment dependency that slow both teams down. Now, in production systems, we have seen in the past, it's one of the clearest patterns. When service boundaries match team boundaries, teams do move fast. They own the service fully, they deploy when they are ready, and when service boundaries cut across teams with two or three teams all contributing to the same service, everything kind of slows down. Deployments require coordination, on-call deployment responsibilities are unclear, and code reviews across team boundaries, they tend to take longer. Now, some organizations do this intentionally. It is called the reverse Conway maneuver. Instead of letting the org chart accidentally dictate the architecture, they design the ideal service boundaries first, then restructure teams to match those boundaries. The architecture drives the org chart, not the other way around. A good example of this will be Spotify. Spotify, the music company, music streaming service, they organize their company engineering teams into something called squads, where each squad owns a specific product area like search, playback, or recommendations. Each squad owns its own services, its own data, and its own deployment pipeline. The architecture mirrors the team structure by design, not by accident. When they need a new capability like podcast recommendations, they form a new squad. That squad builds and owns that service from day one. Now for interviews, mentioning Conway's law shows the interviewer that you understand microservices as an organizational decision, not just a technical one. When you explain that your service boundaries follow team boundaries and that those teams are structured around business capabilities, it demonstrates the kind of thinking that interviewers associate with senior and staff level engineers. So let us test what we have covered so far with an actual interview scenario. So the setup is this. Let's say you're in a system design interview. The interviewer asks you to design a food delivery platform and you say that, okay, I would use a microservices architecture. And then the interviewer will ask you, okay, please provide your reasoning behind it. Now let's take a moment to think about how you would answer that before we continue. Here's what, not a good answer would sound like. Okay, someone might say that, okay, microservices are the industry standard. Companies like Uber and Dash would use them. And they are more quote-unquote scalable, than monoliths. The problem with that answer is that it does not explain why this specific system needs microservices. Industry standard is not an architectural justification. Statements like modern is not an architectural justification as well. The interviewer actually wants to hear reasoning specific to the problem you're designing, not an appeal to what the other companies do. Now, here's what a strong answer would sound like. So, you can say something like, let's say a food delivery platform has at least, 4 distinct scaling profiles. Restaurant search is read heavy and spiky during meal times. Order processing is write heavy and needs strong consistency. Driver dispatch is real time and location intensive. And payment processing has low throughput but requires high reliability. These also map to different team specializations. So microservices let us to scale each of those independently, deploy the dispatch system without risking the payment flow, and let specialized teams own their domain. That said, if this is an early stage startup with one engineering team, I would start with the modular monolith and extract services as the team and the traffic load grows. So what makes that answer strong is being specific about it. The candidate identifies concrete scaling profiles. They map those profiles to promises of microservices. They acknowledge the team structure as a factor, and they show maturity by not defaulting to microservices unconditionally. That closing sentence about starting with the modular monolith is what tells the interviewer this person has real world judgment and not just, their textbook knowledge that they're kind of memorizing. So, yeah, please follow this strong, the second approach of the answer that we just shared. Now, this brings us how you should frame the architecture choice in an actual interview. And the framing matters because the first 2 to 3 minutes of a system design interview set the tone for everything that follows. Now, microservices should never be a default starting point. They should be a justified design choice that you arrived at through reasoning. Here's the decision flow. So, you start with the question that, okay, like how many teams will work on a system? If the answer is one small team, a monolith is the right choice. There is no need for independent deployment or independent scaling when a single team owns everything and the load is uniform. Now, if the answer is a growing team of 10 to 40 engineers, a modular monolith makes sense. You get clean module boundaries inside a single deployment unit, and you avoid the operational complexity of distributed services. If the answer is multiple teams, let's say with 30 or more engineers, then you should ask a follow-up question that, okay, are the domain boundaries well understood? If the boundaries are still being explored, if this team is still figuring out where one business capability ends and another begins, then you stay with the modular monolith. Premature decomposition into microservices creates boundaries that you will need to restructure later, and restructuring service boundaries is far more expensive than refactoring module boundaries inside a monolith. If the domain boundaries are stable and well proven, then you ask one more question that, okay, do parts of the system need independent scaling or independent deployment? If the answer is no, a modular monolith still serves you well. If the answer is yes, then microservices are the justified choice. So what interviewers look for here is the reasoning. They want to see that you do not jump to microservices just by default. They want to see that you ask about the team size, the product maturity, and the scaling requirements before choosing an architecture. The interviewers want to hear you articulate which specific promise of microservices justify the added complexity. They also want to hear you acknowledge the cost and explain how you will handle them. And they also want to see that modular monoliths is a valid and often better starting point. Now, the common mistake here is that every system design answer, is, let's say if you start with something like, okay, I would use microservices with an API gateway, a message queue, and a load balancer. That kind of sounds rehearsed. It shows no reasoning, so it tells the interviewer that you have memorized an architecture template rather than thinking through the trade-offs. And puts you on the defensive, for the rest of the interview because the interviewer spend remaining time probing whether you actually understand why you made the choice. Thoughtful framing, even if it takes an extra 60 seconds at the start, will build the credibility that carries throughout the entire interview. So you should please do that. Okay, let us bring together everything we have covered in this section. We start with the precise definition of a microservice, 4 properties, all required simultaneously. A microservice is independently deployable, it owns its own data, it is aligned to a business capability, and it's owned by a single team. If any of those properties is missing, you lose the benefit that the architecture is supposed to provide. Then we cleared out the misconceptions. So microservices are not about code size, they're not defined by Docker or Kubernetes, they're not created by splitting code into separate repos. They're not, one service per database table. These misconceptions lead to distributed monoliths, which carry all the costs of microservices with none of the benefits. So we also covered 3 core promises, so independent deployment, independent scaling, and independent ownership. Each promise removes a specific bottleneck, but each comes with a trade-off that you need to plan for. Then we covered the 5 core costs, which is network latency, partial failure, data inconsistency, data debugging complexity, and operational overhead. The availability math makes this concrete. So 4 services at 99.9% availability each, it gives you 99.6% combined. That gaps means roughly 26 additional hours of downtime per year. At 99.9% you have 8.7 hours of downtime per year, and at 99.6% you have about 35 hours per year. Now these numbers are worth keeping in your head for the interviews to show as an example. Then we also looked at Conway's law and why microservices are fundamentally an organizational pattern. Team structure dictates system architecture, so the stronger architectures are the ones where service boundaries and team boundaries are actually aligned. And then we also cover interview framing, so microservices are a design choice for trade-offs, not the default answer. The way to frame it in an interview is to reason through team size, domain maturity, and scaling needs, and then arrive at microservices as a justified conclusion, not as a starting assumption. And there are also, few common interview mistakes to avoid. Saying statements like, okay, I would, in the interview that, okay, if a candidate says like, I would use microservices because, they are quote unquote scalable, that statement does not explain what specifically needs independent scaling. A stronger version of that would be that, okay, the search service handles 10 times more traffic than checkout service, so independent scaling matters here. I mean, saying statement like microservices are the modern best practice, this also doesn't sound ideal because a strongest version of that statement would be that, okay, microservice makes sense here because we have 4 separate teams and 3 distinct scaling profiles. Now, jumping straight, to microservices without considering alternatives will show you that you only know one architecture. A stronger version for that would be that, okay, for an early stage product with one team, I would start with the modular monolith and extract services as the domain matures. And defining microservices, again, as small services is, it also misses the properties that actually matter. So the stronger version for that statement would be a microservice is independently deployable, it owns its data, and is aligned to a business capability. And these are the numbers you should keep in mind. Network call latency per hop is 1 to 10 milliseconds compared to 90 seconds for in-process calls. 4 services at 99.9% each gives you 99.6% combined availability. And where 99.9% means 8.6 hours of downtime per year and 99.6% means 35 hours. And a typical engineering team, size per service would be a 4 to 8 engineers. Now everything from here, builds on this foundation. So section 2 in this course, which is monolith to microservices, will show you how monoliths, modular monoliths, and distributed monoliths compare against the 4 properties we have defined on slide 2. Section 3, service decomposition, uses the aligned to the business capability property as a starting point for finding service boundaries. Section 5 in this course, which is data ownership, will expand on the principle, owns its own data property and explore what happens when services they need each other's data. And then in section 6 of this course, which is Saga's inconsistency, we'll address the partial failure cost we have covered on slide 5, and it will also teach you how to handle transactions that span multiple services. So let's move to the next section. In section 1, we covered the principles that define microservices. In this section, we are going to look at where microservices actually fit in the bigger picture, because microservices are not a starting point. They are one end of a spectrum. Understanding that full spectrum actually is what separates a thoughtful architecture decision from one that follows trends without reasoning. The spectrum has 4 points. So on one end, you have the traditional monolith, then the modular monolith, then the distributed monolith, which is an anti-pattern, and finally true microservices at the other end. Now we're going to walk through all 4 of these in depth. For each one, we'll cover what it looks like in practice, when is the right choice, and what happens when it applied in the wrong context. After that, we'll look at the comparison framework for choosing between these architectures. Then we'll walk through the actual migration path from monolith to microservices step by step, including the Strangler fig pattern, which is a standard technique for doing this incrementally in production. And then we'll close by covering the 5 most common anti-patterns that turn a well-intentioned migration into a distributed, not an ideal scenario. Now, here's something worth thinking about before we start. Every major platform used today started as a monolith. Shopify scaled to billions in gross merchandise value on a raised monolith. GitHub ran as a single raised application for years before selectively extracting services. So the question in this section is never that, okay, should we use microservices? The question is, when is the right time to move and how do we do it without breaking everything? Now let's start with the traditional monolith approach and then we move to different parts of the spectrum as we discussed. So what exactly is a monolith? A monolith is a single deployment unit. All features, all business logic, and all data access live in one code base and deploy as one artifact. Think of an e-commerce platform in its early days. You would have a user module, an order module, a payment module, and an inventory module. All 4 modules live in the same application. They all deploy together, they all scale together, and they all share one database. When the order module needs to check whether a product is in stock, it calls the inventory module directly. That call is an in-process function call. It happens in nanoseconds and never fails because of a network timeout. And it participates in a single database transaction that guarantees the consistency. Now, this limitation, this is an enormous advantage. The moment you distribute a system across a network, you give up all three of these properties. Function calls, they become network calls that take milliseconds instead of nanoseconds, and those network calls can fail, timeout, or return stale data. And single database transactions, they get replaced by distributed coordination mechanisms like Sagas and compensatory transactions, which are significantly more complex to build and to reason about. Now, what does the deployment looks like in a monolith? One team, run like git push. The CI pipeline builds one artifact, test run against one application, and one deployment goes to production. If something breaks, one rollback fixes everything. There's no question of okay which service caused the outage because there is only one service. That simplicity has real value and scales further than most engineers expect. And here's something for interviews. Interviewers expect, the candidates actually, is they actually really like the candidates who, articulate a monolith strengths with the same depth they can articulate microservices strengths. It signals that, the candidate chooses architectures based on reasoning, not based on, what is trending or might be, might be just like a really trending thing to say in interviews. Now that we understand the structure of a monolith, let us talk about why it works well and for how long. The first strength is simplicity of operations. One deployment pipeline, one monitoring dashboard, one on-call rotation, one long stream to search when something breaks. For a team of 5 to 15 engineers, this operation simplicity is not a minor convenience. It is a pretty significant productivity advantage. Every additional deployment pipeline, every additional monitoring setup, every additional service to debug during an incident adds overhead that a small team cannot afford. The second strength is full asset transactions. When a user places an order, you can debit inventory, create the order record, and charge the payment in a single database transaction. If any step fails, everything rolls back automatically. The database handles this for you. So in a microservices world, achieving the same guarantee requires sagas, compensating transactions, and idempotency keys. We'll cover those in more depth in section 6, but for now, just understand that what Monolith gives you for free becomes a significant engineering challenge in a distributed system. The third strength is fast iteration speed. You can change the order logic, the payment logic, and the notification logic in a single pull request. You can deploy it all at once and you see the results immediately. There is no need to coordinate deployments across teams. No backward compatibility concerns between different service versions, no integration testing across network boundaries. So when you're moving fast and the product is evolving quickly, this iteration speed matters more than anything else. And this is not just theory actually. Shopify processed over $200 billion in gross merchandise value in 2023, running primarily on a Rails monolith. They have extracted some services over time, but the core remained monolith. Similarly, Stack Overflow serves millions of developers from a monolith running on remarkably very few servers. They are not small companies making compromises. These are large-scale platforms where the engineering teams deliberately choose to keep the monolith because it was the right decision for their context. And here's something for interviews. If an interview asks you to design a system for a 5-person startup, proposing microservices is the wrong answer. The right answer is a well-structured monolith that can be modularized later. Saying this explicitly tells the interviewer that you have real-world judgment and that you reason about trade-offs, not defaults. Now, one of the most common interview questions in the area is that, okay, why would you not use microservices? Having concrete examples like Shopify and Stack Overflow makes your answer much more credible and memorable. Okay, now let us talk about the modular underused architecture in the industry, and it sits right in the middle of the spectrum between a traditional monolith and microservices. It deploys as a single unit, but internally it is organized into distinct modules that communicate through well-defined interfaces. Here's a key structural difference. In a traditional monolith, all 4 modules will share the same database. Any module can access any table. In modular monolith, each module still lives in the same database, but each module only accesses its own tables. The order module cannot directly query the user's tables. If it needs user's data, it must call the user module's public interface. So why does this matter? Because the modular monolith gives you the boundary discipline of microservices without the operational cost of distribution. You practice data ownership, you define clean interfaces between modules, and you discover where the real domain boundaries are. All of this happens while you keep a simplicity of a single deployment, a single database, and a single operational footprint. And here's the part that makes this architecture so powerful as a stepping stone. So when you eventually decide to extract a module into a microservice, the interface already exists. The order module is already calling the user module through a public interface, so you replace that in-process function call with a network call to the new user service. The contract remains the same. The migration becomes a targeted infrastructure change, not a redesign of how modules interact. For interviews, mentioning the modular monolith is a deliberate architecture choice that shows the interviewer that you understand the full spectrum of options. You are not thinking in terms of monolith versus microservices. So you also show them that there is a middle ground, and you know that when is the right choice and in what situations. The difference between a modular monolith and a messy monolith is one word: enforcement. Without enforcement, module boundaries erode within months. Engineers under time pressure start reaching into other modules. One shortcut becomes 2, then 10, and soon the boundaries exist only in the documentation that nobody actually follows through. So now, how do you enforce boundaries in practice? Let us walk through a code example. The order module here class, that takes the user module and inventory module as dependencies through its constructor. When the place order method is called, it calls the user module.getUser to retrieve the user data. It calls the inventory model.check availability, to check stock. It never imports the user model directly. It never writes SQL queries against the inventory tables. It goes through the public interface of each module. This is the discipline that makes the modular monolith work. The order module treats the user module and inventory module as if they were external services. The only difference is that call happens in process instead of over the network. Now there are 3 practical mechanisms for enforcing this discipline. The first is package level access control. So the package level access control, in Java, so you use separate packages with package private classes so that internal implementations are not accessible from outside the package. In Python, you use explicit exports in your int.py files to control what is visible. The second mechanism is architecture tests. Tools like ArcUnit for Java or custom linting rules in your CI pipeline can automatically fail if the build is, if any of the module imports from another module's internals. This catches boundary violations before they reach the main branch. The third mechanism is code review discipline. Reviews reject any pull request that crosses module boundaries without going through the public interface. This is a human layer of enforcement, and it is just as important as the automated layer. Now here's the critical test to keep in mind. If the order module can reach into the inventory database and run a direct SQL query like select all from inventory where product ID equals some value, you do not have a modular monolith. You have a monolith with folders. The folders look like boundaries, but they provide actually no actual isolation. Now in interviews, when you're asked about, how would you prepare a monolith for future microservice extraction, this is the answer. A modular monolith with enforced boundaries is a textbook approach, and being able to explain the enforcement mechanism shows depth beyond the surface level understanding. So please do that in the interviews. So this leads us directly to the architecture that sits on the opposite end of the quality spectrum from the modular monolith, the distributed monolith. A distributed monolith gives you the full cost of a distributed system with none of the benefits. You pay for the network latency, partial failure scenarios, distributed debugging, and operational complexity. But you get none of the independent deployment, independent scaling, or independent ownership that microservices are supposed to provide. Now here's how it typically begins. A team, let's say, splits the monolith into 5 services, but all 5 services still share the same database. Deploying service A requires deploying service B at the same time because they depend on each other's internal data formats. Every feature requires changes across 3 or 4 services simultaneously. There is a release train, as they say, where all services must be deployed together on Thursday, let's say at 2 p.m. So you now have all the complexity of distributed systems, but you have none of the independence that justifies the complexity. Now there are 6 key signals that indicate that you're looking at a distributed monolith. The first is a shared database, where multiple services read from and write to the same tables. The second is coordinated deployments, so where someone says, we need to deploy services A, B, and C together. The third is circular dependencies, so where service A calls B, B calls C, and C calls back A. The fourth is chatty communication, so where a single user request triggers 10 or more network calls between services. The fifth is cross-service ownership, where one team owns multiple services or one feature required changes across 4 services. And the sixth is shared data models, where services import the same ORM models or share protocol buffer definitions with business logic embedded in them. Now, the key test to apply is pretty straightforward. You should ask this question about each service. Can the service be deployed independently right now without any other service also deploying? If the answer is no for most of your services, then you have a distributed monolith. In interviews, if your design has a shared database, coordinated deploys, or circular dependencies, the interview will push back hard. Being able to identify and name this anti-pattern before the interviewer points it out is a very strong signal which you should mention in the interviews. So let us test what we have covered so far with the scenario that commonly comes up in interviews. An interviewer shows you an architecture with 4 services, let's say a user service, an order service, a payment service, and a notification service. All 4 services connect to a single shared PostgreSQL database. The order service calls the payment service synchronously for every order. The payment service calls back to the order service to update order status, and the notification service queries the order table directly to find the orders that need notifications. Now the interviewer asks you, okay, what is wrong with this design? Let's take a moment to think about what problems you can identify here. Now, a weak answer, not a strong answer to this question would be something like, okay, it needs more services. I would also add an inventory service and a shipping service. If you say that answer, as a statement in the interview, that's not ideal because adding more services to a design that already has structural problems will make things worse, not better. The candidate would miss the fundamental issues and jump into just adding more complexity. Now, a strong answer would actually identify this as a distributed monolith and calls out 3 specific problems. The first problem is the shared database. All 4 services share a single database, so the schema migration to the orders table could break the order service, the payment service, and the notification service simultaneously. There is no true data ownership here. The second problem would be the circular dependency between the order service and the payment service. The order service calls the payment service, and the payment service calls back the order service. This creates tight coupling that prevents either service from being deployed independently. Now, the third problem would be that the notification service directly queries the order table instead of consuming events or calling an API. This means the notification service is coupled to the order service internal database schema. Now, the fix addresses all 3 issues. Each service needs its own database. The circular dependency should be broken with asynchronous events, and the notification service should consume order events from a message queue instead of querying the orders table directly. So what makes this answer strong is the structure. The candidate names the anti-pattern. They identify 3 specific structural problems. They explain why each problem is harmful, and they propose concrete fixes. That combination of diagnosis and solution is exactly what the interviewers are looking for. Now that we understand what a distributed monolith looks like, let us look at what true microservices look like and what makes them fundamentally different. Now the key difference is not the number of services, it's the independence between them. In a true microservices architecture, each service has its own database. The order service cannot query the user database directly. If it needs user data, it calls a user service API or holds a cache copy of the specific user data it needs. Now, communication between services is primarily asynchronous, so when a user places an order, the order service publishes an order created event. The payment service and the notification service each consume that event independently on their own schedule. The order service, it does not wait for either of them to finish, it just publishes the event and then just moves on. And as you can see, there are no circular dependencies. Data flows in one direction for any given workflow, and each service can be deployed independently. A new version of the payment service does not require the order service to deploy at the same time. The team that owns the payment service can ship changes on their own schedule, run their own test, and roll back independently if something goes wrong. To verify that your architecture truly qualifies as microservices, apply the 4 properties from section 1 to each service. Is each service independently deployable? Does each service own its own data? Is each service aligned to a business capability? Is each service owned by one team? If every service passes all 4 tests, you have the true microservices. And here's something for interviews. When you draw a microservices diagram on a whiteboard, always show separate databases for each service. This immediately signals to the interviewer that you understand data ownership. So drawing multiple services pointing to one database is one of the fastest signals of a distributed monolith, and interviewers notice it within the first minute of whiteboard drawing. So we have now covered the three valid architectural choice, which is the traditional monolith, the modular monolith, and true microservices. Let us put them side by side and compare them across the dimensions that matter. For deployment, monolith and the modular monolith deploy as a single artifact. Microservices deploy independently per service. For internal boundaries, the traditional monolith has weak or no boundaries between modules. The modular monolith has strong boundaries enforced in code through interfaces, package access control, and architectural tests. Microservices have the strongest boundaries of all because the modules are separated by the network itself. For the database, the traditional monolith uses a single shared database with no access restrictions. The modular monolith also uses a single database, but each module only accesses its own set of tables. Microservices give each service its own separate database entirely. For inter-module communication, the monolith and the modular monolith, both use function calls. The difference is that the modular monolith forces those calls to go through defined interfaces. Microservices that replace the function calls with network calls, whether that is a REST, gRPC, or asynchronous events. For team scaling, a traditional monolith works well for 1 to 15 engineers. A modular monolith can scale to about 40 engineers if module discipline is strong, and microservices are typically justified for 30 or more engineers spread across multiple teams with independent roadmaps. For failure isolation, both the monolith and the modular monolith have the same weakness. One bug can crash the entire application. Microservices provide natural fault isolation, whereas failure in one service stay contained to that service only. For data consistency, the monolith and modular monolith gives you full asset transactions for free. Microservices require eventual consistency and patterns like Sagas. For operational complexity, the monolith and modular monolith are both low. Microservices are high. Multiple deployment pipelines, distributed tracing, independent monitoring, service discovery. All of that is operational overhead that your team needs the capacity to handle. And for where to start, a monolith is the right choice for early stage products and small teams. A modular monolith fits a growing team with maturing domain. Microservices fit a large organization with proven stable boundaries. Now notice that the distributed monolith is not in this comparison. That is deliberate because it is not a valid architectural choice. It is an anti-pattern that happens when microservices are adopted without the discipline of data ownership and independent deployment. So this comparison framework is one of the highest value tools in this section. Interviewers expect you to reason about when each architecture is appropriate, and this table gives you the structured way to do that. So when is monolith the right choice? Not as a compromise, not as a fallback, but as a correct engineering decision. The first situation is a small team working on an early product. You have 3 to 10 engineers. The product is pre-product market fit. I know the requirements are changing weekly. So in this environment, the ability to change anything and deploy everything in minutes is worth more than the independent scaling. The coordination overhead of microservices would slow this team down and not speed it up. The second situation is unclear domain boundaries. Let's say you're building a new product and you do not yet know where the real boundaries are. Is pricing part of the catalog domain or the checkout domain? Should user preferences live with the user profiles or with the recommendations? Getting these boundaries wrong in microservices architecture is expensive to fix because you have to redraw the service boundaries, then migrate data between databases, and update all the inter-service communication. Getting them wrong in Monolith is not that hard because it's just a refactor. You just move some classes around, update some imports, and you're done. The third situation is strong consistency requirements everywhere. If nearly every operation in your system requires ACID transactions across multiple data entities, microservices make this dramatically harder. Consider a banking ledger system where every transaction must be immediately consistent across accounts, balances, and audit logs. That system may be simpler and safer as a monolith with a single relation database than as a set of distributed services trying to coordinate consistency through sagas. The fourth situation is a uniform scaling profile. If every part of your system has the same load pattern and scales the same way, independent scaling per service adds infrastructure complexity without providing any benefit. You can scale a monolith horizontally by running multiple instances behind a load balancer. Not every system needs fine-grained per component scaling. For interviews, answering, let's say, when would you like questions? If you get questions like, okay, why would you not use microservices? If you provide these specific scenarios and concrete reasoning, it's one of the strongest signal of architecture maturity you can display in interviews. It will show that you think about trade-offs, not just about what is popular or trendy in the industry. So please do that in the interview. And this is exactly where microservices they earn their complexity, not as a default, but when specific organizational and technical conditions are met. Let us walk through each condition. The first condition is that multiple teams need to ship independently. You have 30 or more engineers across 4 to 8 teams. Each team has its own roadmap and release cadence. Waiting for a shared release train slows everyone's down. In this context, independent deployment becomes a genuinely productivity multiplier. Each team can build, test, and deploy on their own schedule without waiting for or coordinating with anyone else. The second condition is that different parts of the system have different scaling needs. Think about a platform like YouTube. The video upload pipeline handles, maybe 500 hours of video uploaded every minute, but it can tolerate some latency. The video playback service handles millions of concrete streams and needs sub 100 milliseconds, whereas the recommendation engine is compute intensive and has bursty traffic patterns. Scaling all of these behind one monolith wastes resources because you would have to provision for the most demanding component even when the others are idle. Separate services lets you allocate infrastructure precisely to match each component's needs. The third condition is that domain boundaries are well understood and stable. The team has been working on the product for 1 to 2 years. The domain model is mature. The boundaries between orders, payments, inventories, and shipping are clear and rarely change. Extracting these into services carry low risk of getting the boundaries wrong because the team has already discovered where the natural boundaries are. The fourth condition is that fault isolation is critical. A bug in the recommendation engine should not take down the checkout flow. A surge in the notification sending should not slow down the processing. And when failures in one domain must not cascade into unrelated domains, service boundaries provide natural fault isolation. Each service fails independently and the rest of the systems keeps running. And in production systems, the decision to move to microservices generally is driven by a combination of these conditions, never just one. And this is exactly how you should present this in interviews. State the conditions explicitly before proposing microservices. You can say statements like that, I'm choosing microservices for this design because we have multiple teams, different scaling profiles for search versus checkout, and well understood domain boundaries. That sentence tells the interviewer that you're reasoning from the first principles, not from the defaults. Now, the gap between a junior level answer and I would say a senior level answer is a justification. A younger candidate, who's probably very early in their career, says, okay, microservices. A senior candidate would say something like microservices because these specific conditions are met. Now here's a scenario you might face in an actual interview. You're designing a system for a startup that just raised a Series A. They have 8 engineers, 1 product, and about 10,000 daily active users. The CEO asks you to design the backend architecture. The CTO, let's say, mentions that they want to start with microservices so we do not have to rewrite later. Now let's take a moment to form your answer. A weak answer agrees with the CTO without examining the premise. The CTO is right. Okay, starting with the microservices avoid technical debt and prevents painful rewrite later. I would create separate services for users, orders, payments, and notifications. That actually answer is not ideal because it does not question the assumptions. With 8 engineers and 10,000 daily active users, microservices add operational overhead that the team is not staffed to handle. You now need 4 or more deployment pipelines, distributed debugging tools, eventual consistency handling, and inter-service communication management. An 8-person team will spend more time operating the infrastructure than actually building the product. And the avoid the rewrite argument ignores that wrong service boundaries chosen now will require a more painful rewrite than refactoring a monolith would. A strong answer will actually respectively disagree with the CTO, not in public but in private, but with a concrete reasoning. It could, strong answer would sound like, okay, I would recommend starting with a modular monolith. With 8 engineers, the team does not have the capacity to operate multiple independent services, maintain separate deployment pipelines, and handle distributed debugging. More importantly, at 10,000 daily active users, with the product still finding its market, the domain boundaries are not yet stable. If we split into microservices now, we are likely to draw the boundaries in the wrong places. And redrawing the service boundaries is far more expensive than refactoring modules within a monolith. The answer then explains a concrete plan. Okay, You can say something like, okay, I would structure the monolith with clear internal modules for users, orders, payments, and notifications. Each module would have enforced interfaces and module scope database access. When the team would grow to 20 to 30 engineers and the domain will eventually stabilize, we can extract the modules that need independent scaling or deployment into services. The modular monolith makes that future extraction straightforward because the interfaces already exist. So now what makes it strong is that the candidate respectfully disagrees using concrete reasoning, team size, operational complexity, and domain maturity. They propose a specific alternative and explain how it sets up the future migration path. They demonstrate that avoiding a rewrite is actually, better achieved by modular design now than actually by premature distribution. So we have covered when to stay with monolith and when microservices are justified. The natural next question is, okay, how do you actually get from one to the other? Moving from monolith to microservices is not a binary switch. It is a staged migration that should happen incrementally over months or years. There are typically three stages. So stage 1 is going from a monolith to a modular monolith. You identify major business domains in your code base, you draw boundaries around them, you enforce those boundaries with package structure, interface definitions, and architectural tests. Each module gets its own set of database tables, and no module directly accesses another module's tables. This stage involves zero infrastructure changes, so it is purely a code organizational exercise. But it is the most important stage because it is where you discover where the real boundaries are. Now, stage 2 is, where it's the first extraction. You pick the module with the strongest case for extraction. This is usually the module with the most distinct scaling profile, or the one owned by a team that is most bottlenecked by shared deployments. You extract it into a separate service with its own database. You replace the in-process function calls with API calls or event consumption. And you keep everything else in the monolith. This stage is where you learn the operational mechanics of running a distributed service alongside a monolith. Now, stage 3 is incremental extraction. You extract additional modules one at a time, each time following the same pattern. Separate database, separate deployment, to replace in-process calls with network calls. And this is where the discipline matters. You stop extracting when the remaining modules do not have a strong case for independence. Not everything needs to be a microservice. Some modules are perfectly fine staying in the monolith. Now, this is a critical principle here. Extract the module with the highest pain, not the easiest one. The easiest module to extract teaches you the least. The one that is causing deployment bottlenecks or scaling problems teaches you the most and delivers the most value to the organization. For interviews, describing a stage migration path shows the interviewer that you have practical experience with system evolution. Most candidates only talk about the greenfield designs. Being able to articulate how you evolve an existing system over time is a strong differentiator. And this is exactly where the Strangler fig pattern comes in. It is a standard technique for incrementally migrating a monolith to microservices without a big bang rewrite. It is named after the Strangler fig tree, which grows around an existing tree and gradually replaces it. And here's how it works mechanically. You place a routing proxy in front of the monolith. Initially, all traffic goes through the proxy to the monolith. Nothing changes. Then, when you extract a service, say the payment service, you update the proxy to route all payment-related requests to the new payment service instead of the monolith. The monolith still handles users, orders, and inventory. Over time, more routers shift to new services until the monolith handles nothing and can be retired. Now, this approach works because of 4 properties. So first is there is zero downtime during the migration. Traffic is routed, it's not switched. Second, each extraction is independently testable and reversible. If the new payment service has problems, you route traffic back to the monolith. Third, the monolith continues, working for everything that has not been extracted yet. There is no moment that, where you are halfway between two systems with neither one complete. Fourth, risk is contained to one service at a time. A problem with the payment service extraction does not affect order processing or user management. For interviews where an interviewer asks you, okay, let's say, they ask you that, okay, how would you migrate from monolith to microservices? The Strangler fig pattern is the expected answer. Proposing a big bang rewrite where you rebuild the entire system from scratch and switch over all at once is a very big red flag. It signals that you have not done this in practice because teams that have done it, they know that big bang rewrites almost always fail. They take longer than estimated, the business stops getting features during the rewrite, and the new system has its own bugs that the old system had already resolved. Now let us walk through the Strangler pattern with a concrete example to see how it works in practice. The scenario is an e-commerce platform running a Rails monolith that handles, let's say, 50,000 requests per second. The payment modules process $500 million in monthly transactions. The team wants to extract payments into a separate service. Now, step 1 is adding the routing proxy. You place an API gateway or a reversed proxy like Nginx in front of the monolith. You configure it to forward all the traffic to monolith unchanged. Then you verify that adding the proxy does not affect latency or reliability. This step changes zero behavior. Its only purpose is to establish the routing layer that you will use in the later steps. Now, step 2 is building the new payment service. You build the payment service as a standalone application with its own database. You implement the same payment API that the monolith currently exposes. You deploy it alongside the monolith, but you do not route any traffic to it yet. At this point, the new service exists in production, but is receiving actually no real traffic. Step 3 is shadow traffic. You route a copy of payment request to both the monolith and the new service simultaneously. The monolith response goes to the client. The new response, service's response is actually logged and then compared. Now you're looking for, if any discrepancies between the two. For example, does the new service return the same results? Does it handle edge cases the same way? This phase actually catches problem before any real traffic moves over. Typically, it's ideal to run this for 1 to 2 weeks. Now, step 4 is the canary rollout. So you route 1% of your actual payment traffic to the new service. You monitor error rates, latency, and transaction success rates. If the metrics are healthy, you increase it to 5%, then 25%, then 50%, then 100%. At each stage, you watch the metrics closely. If anything degrades, you roll back to the previous percentage. Now, step 5 is decommissioning the old payment code. Once 100% of the payment traffic runs through the new service, you remove the payment module from the monolith. You remove the payment tables from the monolith database. The monolith is now smaller and the payment service is fully independent. For critical service like payments, processing $500 million monthly, this entire process will roughly take around 2 to 4 months. Rushing it is actually not worth the risk when real money is flowing through the system. Now, walking through these specific steps in an interview will demonstrate that practical understanding. So most candidates they generally stop at we'll use Strangler pattern, but they do not explain the actual mechanics. Being able to describe the routing proxy, shadow traffic, canary rollout, and decommissioning steps, where it separates the candidates who have actually done this in production versus candidates who have just actually have a high level understanding. So I would suggest you cover this in the interviews as well. Now that we understand how to migrate correctly, let us talk about the mistakes that turn a well-intentioned migration into a distributed monolith. Each of these anti-patterns violates the principles we have covered in section 1. The first anti-pattern is splitting by technical layer. This is when teams create a front-end service, a back-end business logic service, and a database service. The problem is that where every single feature requires changes across all three services. Adding a new field to the order form means changing the front-end service, the business logic service, and the database service, and deploying all of them three together. These are three tightly coupled services that must always now change together. Services boundaries, they should follow business capabilities like orders, payments, and inventory, not the technical layers. The second anti-pattern is one service per database table. A team creates a user service, an address service, a phone number service, and let's say an email service because, each has its own table. But these are not independent business capabilities. These are fragments of a single user profile capability. An address never changes independently of a user. A phone number is always associated with a user. So these should be one service, not four. A database table is not the right unit for drawing service boundaries. The third anti-pattern is premature extraction. This happens when services are extracted before the domain is well understood. The team splits catalog and pricing into separate services, then discovers that every pricing change actually requires a catalog change. They now have two services that must always deploy together. That is a distributed monolith, so the domain needed more time to stabilize before the boundary between the catalog and pricing was clear enough to separate. Now the fourth anti-pattern is a GOT service, one service that gradually accumulates business logic that should belong elsewhere. The order service starts handling payments validation, then inventory checks, then shipping calculations, then notification formatting. Over time, it becomes a monolith with a microservice label. It has the operational complexity of a distributed system, but it has the coupling characteristics of a monolith because everything important runs through this one service. Now the fifth anti-pattern is the shared database backdoor. Services officially communicate through APIs, but three of them still read from a shared reference database table. Any schema change to that table breaks all three services, and this hidden coupling that defeats the purpose of having separate services. The APIs create the illusion of independence, but the shared table means these services are just as coupled as if they were in the same codebase. Now, being able to name these anti-patterns and explain why they are harmful shows the interviewer that you understand the principles behind microservices, not just the surface level structure. Now, this is something you should keep in your notes for the interviews. These 5 decomposition anti-patterns come up pretty frequently, and being able to name them by name and explain the fix is a strong signal of experience. So the first is splitting by technical layer. Services should follow business capabilities, not front-end, back-end, and database layers. The second is one service per table. A database table is not a business capability. Group related data under one service. The third is premature extraction. Extract services only when domain boundaries are stable and the pain of coupling is real. Do not extract early just to avoid a future migration. The fourth is a God service. So if one service does everything, you have a monolith with extra network calls. The overhead of distribution without the benefit of independence. The fifth is the shared database backdoor. So if services share a database table, they are not truly independent, regardless of what the API layer looks like. And here's a test to apply to any microservices design, whether it is yours or one an interview shows you. For each service, you should ask, okay, can this service be developed, deployed, and operated by one team without coordinating with other teams? If the answer is no, you have one of these anti-patterns. Now, interviewers may describe a flawed architecture and then ask you to identify the problems. Being able to name these anti-patterns by name, explain why each one is harmful, and describe the fix is exactly what separates, a strong candidate from someone who might not have deep experience in distributed systems covered in this section. We start with a traditional monolith, a single deployment unit, a shared database, simple operations. It works well for small teams and scales further than most engineers expect. Then we covered the modular monolith, still a single deployment but with enforced internal boundaries. Each module has its own database tables and communicate through defined interfaces. This is the best stepping stone toward microservices because the interfaces you build now become the service contracts later. We cover the distributed monolith, which is the anti-pattern. You get all the costs of a distributed system with none of the benefits of the independence. Shared databases, coordinated deployments, and circular dependencies are the telltale signs. Then we looked at the true microservices, so independent deployment, private databases, business-aligned services, each owned by one team. The independence between services is what defines this architecture, not the number of services. We walked through when to stay with the monolith, so small teams, unclear domains, uniform scaling, and strong consistency requirements. And when microservices are justified, so for example, multiple teams, different scaling profiles, stable domain boundaries, and fault isolation needs. For migration, the path goes from monolith to modular monolith to incremental extraction using the Strangler fig pattern. Route traffic through a proxy, build the new service alongside the old one, run shadow traffic to catch discrepancies, do a canary rollout from 1 to 100%, and then decommission the old code. And then we closed with 5 decomposition anti-patterns, which is splitting by technical layer, one service per table, premature extraction, God services, and shared database backdoors. Now there are some common interview mistakes that you should be aware of. The first is saying that someone says that always start with microservices to avoid rewriting later. This shows that you do not understand that wrong service boundaries are harder to fix than refactoring a monolith. The stronger approach would be saying something like start with a modular monolith, extract services when domain boundaries stabilize, and team size justifies the overhead. The second common mistake is saying our monolith cannot scale. So a monolith scale horizontally just fine. The bottleneck is usually team coordination, not performance. The stronger framing is the monolith scales fine technically, the problem is 6 teams blocking each other on deployments. The third mistake is proposing a big bang rewrite. This almost always fails because of high risk, long timelines, and the business stops getting features. The strong approach for that would be, I would use the Strangler fig pattern to extract one service at a time over 6 to 12 months. The fourth mistake is drawing multiple services pointing to one database. This immediately signals a distributed monolith, and the fix for that would be that okay, each service has its own database, and you can say in the interview that okay, cross-service data access goes to APIs or events. And these are the key numbers worth remembering. A monolith works well up to about 50 engineers before coordination becomes painful. A modular monolith can scale to about 40 engineers with strong module discipline. Microservices are typically the right choice at 30 or more engineers across multiple teams with independent roadmaps. A Strangler fig migration takes roughly 2 to 4 months per critical service extraction, with the shadow traffic comparison phase typically running 1 to 2 weeks before canary rollout begins. Now looking ahead, section 3 takes the business capability alignment principle from this section and turns it into practical methodology using bounded context, aggregates, and domain-driven design. Section 4 addresses how services communicate once they are extracted, building directly on the replace in-process calls with network call step from the migration path. And then section 5 expands on the each service owns its own database principle and tackles a hard question, like what happens when service A needs data that service B owns. If there's one skill from this entire course that will change how you approach system design, it is service decomposition. Getting the boundaries right means services that are independent, focused, and easy to evolve over time. Getting the boundaries wrong means you end up with a distributed monolith, a system that has all the complexity of microservices but none of the benefits. And in many cases, a distributed monolith is harder to work with than the original monolith ever was. Now in section 2, we covered when to use microservices and when not to. This section answers the next question. When do you choose microservices and how do you find the right boundaries? Now we are going to cover a lot of ground here, so we'll start with the business capability decomposition, which is the foundation of good service boundaries. Then we'll go into domain-driven design, specifically bounded context and aggregates. This will give you a precise vocabulary for the thinking about whether where one service ends and another one begins. After that, we'll cover cohesion and coupling, the two principles that guide every boundary decision. We look at the team ownership and service granularity because boundaries that do not match your organization will not survive in production. Then we'll walk through 3 concrete decomposition approaches by business capability, by workflow, and by read-write pattern. We'll cover the anti-patterns, the mistake teams make when drawing boundaries. And we'll finish with real-world decomposition examples across 4 domains: e-commerce, ride-sharing, streaming, and banking. Now here's the core idea that ties this entire section together. Every microservices architecture that works well has boundaries drawn around business capabilities. Everyone that struggles has boundaries drawn around database tables, technical layers, or arbitrary code splits. The skill taught in this section is what makes the difference between these two outcomes. So, where do you start when you need to break a system into services? The most reliable starting point is to decompose by business capability. A business capability is something the organization does to generate value and is defined independently of how the code is structured. Now let us make this concrete with an e-commerce platform like Amazon. Think about what the business actually does. It manages a product catalog, maintaining listings, descriptions, images, and categories. It manages inventory, tracking stock levels, reserving items, triggering the restocks. It manages the order, so creating them, tracking them, and completing them. It processes the payments, so authorizing charges, handling refunds, and storing the payment methods. It also handles shipping and fulfillment, so calculating shipping options, generating labels, tracking deliveries. And also handles customer support, managing returns, resolving dispute, tracking tickets. Now each of these capabilities actually can be owned by a separate team. Each has its own data and each changes for its own business decision. When the marketing team wants to add video to product listings, only the catalog service changes. When the finance team wants to support a new payment provider, only the payment service changes. No other service needs to be touched or redeployed. And this gives you a very practical test for whether the boundaries are right. If changing one capability forces a change in another capability, those two might belong together. If they can change independently, they are strong candidates for separate services. Now, why does this work better than decomposing by technical layer? Think about what happens if you create a database service or a validation service. Every feature in the system touches the database. Every feature needs validation. A service built around a technical concern becomes a bottleneck that every team depends on. This is opposite of independence. So business capability decomposition avoids this because each capability is self-contained. It has its own logic, its own data, its own reason to exist. And here's something important for interviews. When an interviewer asks you, okay, so how would you split the system into services? Starting with business capabilities is the expected approach. Starting with technical layers explains the misunderstanding of what microservices are trying to achieve. Now that we understand business capability decomposition as a starting point, let us talk about the methodology that gives us precise tools for finding and defining those boundaries. That methodology is domain-driven design or DDD. So you do not need to adopt all of the DDD to benefit from it. There are three concepts from the domain-driven design that are directly relevant to microservices decomposition, and understanding these three will give you a significant advantage both in production and as well as in interviews. The first concept is ambiguous language. So every domain has its own vocabulary, and the words used by the business should be in the same words used in the code. If the business calls something an order, the code should also have an order class, not a transaction request class. If the business distinguishes between a shipment and a delivery, the code should maintain that distinction too. So why does this matter for microservices? When two teams use different words for the same concept or the same word for different concepts, that is a signal. It tells you that they operate in different domains and they may need different services. Language boundaries often reveal service boundaries. The second concept is bounded context. A bounded context is a boundary within which a particular domain model is defined and consistent. The same word can mean completely different things in different bounded contexts, and that is perfectly fine. Each context has its own model, so we'll explore this in depth on the next slide because it is the single most useful domain-driven design concept for microservices. The third is aggregates. An aggregate is a cluster of related entities that are treated as a single unit for data changes. The aggregate defines your consistency boundary, the line between what is guaranteed to be consistent and what is eventually consistent. We'll cover this in more detail on slide 27. And here's how these three concepts connect to microservices. A bounded context often maps directly to a microservice. An aggregate, often maps, to the primary entity that a microservice manages. These are not rigid rules, but they are strong starting points that work well in practice. Now, for interviews, mentioning bounded context and aggregate signals that you approach decomposition with the methodology, not just intuition. So, of the three domain-driven design concepts we just covered, bounded context is the one that matters most for microservices. It defines a boundary within which a term has, one specific ambiguous meaning. Now, here's the core insight, and once you understand this, bounded context will feel intuitive. The same word means different things in different parts of the business. Take the word product. In catalog domain, a product is a listing with a title, description, images, and categories. In the inventory domain, a product is a SKU with a stock count, a warehouse location, and a reorder threshold. In the shipping domain, a product is a physical item with weight, dimensions, and a fragility classification. Now, these are three very different definitions of the same word, and this is where the team runs into trouble. If you try to build one product model that satisfies all three domains, you end up actually with a bloated entity that has dozens of fields and most of which are irrelevant to any given team. Now, every change to that shared model requires coordination across all three teams. The catalog team adds a field for, let's say, video thumbnails, and now the shipping team has to redeploy because the shared product class changed. Now, the alternative is to let each domain define product in its own way. The catalog context has its own product model with the fields it cares about. The inventory context has its own product model with the fields it cares about. And these are separate models in separate databases owned by separate teams. So when data needs to cross the boundary between contexts, it is translated at the boundary through APIs or events, not shared through a common database. Now, this is exactly why bounded context maps so naturally to microservices. Each bounded context represents a self-contained domain model with clear boundaries, and that is exactly what a microservice should be, a self-contained service with clear boundaries and its own data. Now, in an interview, if you can explain bounded context with a concrete example of the same word meaning different things in different services, you demonstrate a level of design thinking that sets you apart. So let us walk through a concrete example to see bounded context in action. Imagine an e-commerce platform like Amazon with four teams: catalog, orders, shipping, and payments. All four teams work with the concept of a customer, but customer means something completely different to each team. To the catalog team, a customer is a browser who views and searches products. The attributes they care about are browsing history, wishlist, preferences, and recommended categories. To the orders team, the customer is a buyer who places and tracks orders. They care about shipping address, order history, and saved payment methods. To the shipping team, a customer is a recipient who receives packages. They care about delivery address, delivery instructions, and signature requirements. And to the payment team, a customer is a financial entity who pays for goods. They care about the billing address, credit card tokens, and fraud risk score and payment history. Now imagine you build one customer service that holds all of these attributes in a single model. Every team depends on that service. A change to add, let's say delivery instructions for the shipping team risk breaking the payments team fraud scoring logic. Deployments require coordination across all four teams, and you have created a central dependency that slows everyone down. The better design, is to actually let each bounded context own its own representation of the customer. The catalog context stores browsing preferences, the order context stores order history, the shipping context stores delivery details, the payment context stores financial information. Each team moves independently, so when the order context needs the customer's delivery address, it calls the shipping context APIs or receives it through an event. Now there's a trade-off here, and it is worth being upfront about it. And this means some customer data is being duplicated across services. The customer's name might exist in all four databases, but this duplication is the price of independence and is almost always worth paying. We'll explore this trade-off in depth in section 5 when we cover data ownership. Now walking through a specific example and interview showing how the same entity means different things in different contexts is one of the strongest ways to demonstrate microservices in design thinking. Now let's talk about aggregates. An aggregate is a cluster of related domain objects that must be changed together to maintain consistency. And the reason aggregates matter so much for microservices is that they define where consistency boundary lives. Now here's what it means in practice. Everything inside an aggregate is guaranteed to be consistent. It is changed in a single ACID transaction within one database. Everything outside the aggregate is eventually consistent, handled across services through events or sagas. The aggregate is the line between this is one transaction and this requires distributed coordination. Now let us make this concrete with an order aggregate. An order is not just a single row in a database, it is a cluster of related objects. There is the orders itself, there is order ID, status, and creation timestamp. There are also the order line items, each with product preference, a quantity, and the price at the time of purchase. And there are the order totals, so subtotal, tax, shipping costs, and the final total. Now these objects must be consistent with each other at all times. You cannot have an order total that does not match the sum of the line items. You cannot have a line item that references an order that does not exist. They form a unit, so they change together in a single transaction. And this leads to a very clear rule. Changes to objects inside an aggregate happens in a single transaction within one service. Changes that span multiple aggregates or multiple services happen through events, sagas, or eventual consistency. This rule is what prevents you from needing distributed transactions which are complex, slow, and fragile. In an interview, understanding aggregate helps you answer a question that comes up pretty frequently. Where do you draw the transaction boundary? The answer is at the aggregate boundary. Everything inside is one transaction. Everything that crosses the boundary is eventual consistency. Let us see how aggregates work in code. Imagine a customer adds 3 items to their cart and places an order on a platform like Amazon. The order class is the aggregate root. It controls all access to the objects inside the aggregate. The order has an order ID, a customer ID, a list of line items, and a status. When you add a line item, you call the add line item method on the order object. That method creates a new line item with the product ID, product name, quantity, and unit price, and appends it to that list. When you calculate the total, the order iterates through all of its line items and sums up the quantity times unit price for each one. When you confirm the order first checks whether it has any line items. If it does not, it raises an error. If it does, it says the status to confirmed. Now, the key thing to notice here is that no external service actually, reaches into the order and modifies the line item directly. All changes go through the order's methods, so the order enforces the business rules like the rule that you cannot confirm an empty order. This is what it means for the order to be the aggregate root. It's a gatekeeper. Now, what falls inside versus outside the aggregate? Inside the aggregate, meaning it happens in a single database transaction within the order service, creating the order, adding line items, calculating the total, and confirming the order. All of that is one transaction. Outside the aggregate, meaning it involves other services and happens through eventual consistency, reserving inventory, authorizing payment, and scheduling shipment. These are separate operations in separate services, so if payment authorization fails after the order is confirmed, a compensating action cancels the order. That pattern is called a Saga, which we will cover in detail in section 6. And here's something important for interviews. When you're designing a service in an interview, explicitly state what falls inside your aggregate and what falls outside. Say something like, okay, order creation and line management are inside the aggregate, so they are single transaction. Inventory reservation and payment authorization are outside the aggregate, so they are eventually consistent. This shows the interviewer that you understand exactly where local transaction end and distributed coordination begins. So let us test what we have covered so far with a realistic interview question. Let's say an interviewer asks you, okay, you have to design a microservices architecture for an online food ordering platform like DoorDash. Now, how would you determine the service boundaries? Now, let's take a moment to think about how would you approach this before we walk through the answers. Now, a weak answer would something sound like, for example, let's say the candidate says, I will create a restaurant service, a menu service, a food item service, an order service, a delivery service, a driver service, a payment service, a rating service, and notification service. Basically, they just list out all the possible services they could think of. Now, why is that not a good answer? Because the thing is, the candidate has just listed nice services without explaining the reasoning behind any of them. Like menu service and the food item service are almost certainly too granular, since menus and food items change for the same business reason and are owned by the same team. There is no mention of the business capabilities, bounded context, team ownership, or any methodology. To an interviewer, this will sound like guessing than actually designing the system. Now, a strong answer would look like something like this. Okay, if the candidate says that, okay, I will start by identifying the core business capabilities. So food ordering has at least 5 distinct capabilities. First, restaurant management, which covers onboarding restaurants, managing menus, and managing operating hours. Second would be order management, which covers placing orders, tracking status, and handling cancellations. Third will be dispatch, which would cover, matching orders to available drivers and optimizing delivery routes. Fourth would be payment processing, which would cover, charging customers, paying restaurants, and paying drivers. And fifth will be customer experience, which would cover ratings, reviews, and support tickets. Now, each of these capabilities has different data, changes for different business reasons, and maps to a different team. The restaurant team manages menus and hours. The order team manages the order lifecycle. The dispatch team handles real-time matching, which has very different scaling and latency requirements than the order team. I would then validate these boundaries by checking 3 things. Does each service own its own data? Can each service deploy independently? Does a change in one service really force a change in another? If the answer is yes to all 3, these are good boundaries. If 2 capabilities frequently change together, I would merge them into one service. So what makes this strong is that the candidate explains a clear methodology, identifies specific capabilities with reasoning behind each one, and considers team ownership and applies a validation test. As you can see, this is much more design thinking, so that will be ideal for an interview. So far, we have talked about business capabilities, bounded context, and aggregates as tools for finding service boundaries. Now let us talk about the 2 fundamental principles that guide every boundary decision, which is cohesion and coupling. We'll start with cohesion. Now, cohesion measures how strongly related the responsibilities within the service are. High cohesion means everything inside the service serves a single focused purpose. Low cohesion means the service is a collection of unrelated functionality that happens to live in the same code base. Now let's look at the high cohesion example. Let's say a payment service that handles payment authorization, refund processing, payment method management, and payment history. All of these responsibilities relate to a single business capability, which is processing payments. When the business adds a new payment provider, all the changes happen within this one service. Nothing else needs to change. That is the benefit of high cohesion. Now let's look at low cohesion example. Let's say a utility service that handles email sending, PDF generation, currency conversion, and address validation. These responsibilities have nothing to do with each other. Email sending changes when notification requirements change, PDF generation changes when report formats change, currency conversion changes when new markets are added, and there's no business capability that unifies all of them. They're grouped together only because someone thought, okay, these are small utilities and let us put them all in one microservice. To be very fair, that is not a good principal boundary. Now, here's the practical test for cohesion. You should list every responsibility of a service, then try to describe what the service does in one sentence without using the word and. If you can do it, cohesion is high. For example, the payment service processes payments. That is clean. If you cannot do it without and, the cohesion is low. For example, the utility service sends emails and generates PDFs and converts currencies and validates addresses. As you can see, there's so many mentions of the keyword and, so that it clearly says, suggests that this microservice should be split into multiple parts. Now, why does this matter? A highly cohesive service changes for one reason, is owned by one team, and deploys independently. A low cohesion service changes for many different reasons, pulls in multiple teams, and becomes a deployment bottleneck. This is exactly the problem microservices are supposed to solve. Now, in an interview, when you're justifying your service boundaries, saying a statement like, okay, I group these together because they have high cohesion and they all relate to the payment domain and changes for the same business reason. So when you say a statement like that in an interview, that's a very good, example to demonstrate your system design, and microservices thinking to the interviewer. Now, cohesion tells us what belongs together inside a service. Coupling tells us the opposite. It tells us how dependent one service is on another, and the goal of good boundaries is to keep coupling as low as possible. So when coupling is low, teams work independently. They deploy on their own schedule. They change the internal implementation without breaking other services. When coupling is high, every change becomes a coordination problem. You cannot deploy service A until service B is ready, and that defeats the purpose of having separate services. Now, there are 4 levels of coupling, ranging from the most damaging to the most acceptable. Let us walk through each one. The first and most harmful is database coupling. This is when two services read from and write to the same database table. If the order service and the shipping service both query the same orders table, any schema change to that table can break both services. Adding a column, renaming a field, changing a data type, every modification becomes a cross-team coordination exercise. This is the shared database anti-pattern from section 2, and between true microservices, it should never exist. The second level is implementation coupling. This happens when service A depends on the internal implementation of details of service B. For example, service A knows that service B stores user preferences as a JSON blob in a specific format, and it reads and parses through that JSON directly. The moment service B switches from JSON to protocol buffers, service A will break. Service A was never supposed to know how service B stores the data internally. It should only interact with service B's public API. Now the third level is temporal coupling. This happens when service A can only function when service B is available at the exact same moment. Synchronous HTTP calls between services creates temporal coupling. If the order service makes a synchronous call to the inventory service every time an order is placed and the inventory service goes down, orders fail too, even though order creation and inventory availability are separate concerns. Now, asynchronous managing reduces temporal coupling because service A can publish a message to a queue and continue processing without waiting for an immediate response. The fourth level is contract coupling, and this is what to aim for. Service A depends only on the public API contract of service B. It knows the endpoint, the request format, and the response format. As long as the service B maintains backward compatibility in its API, service A keeps working. Service B can change its database, its programming language, its entire architecture. None of that affects service A because the contract has not changed. Now, an important point, the goal is not zero coupling. Services need to communicate. The system does not work if services are completely isolated. The goal is to move coupling away from the hidden fragile end of spectrum, database, and implementation coupling, toward the explicit manageable end, which is the contract coupling. Contract coupling is visible, versioned, and testable. In an interview, being able to name these four levels and explain which are acceptable versus harmful demonstrated this depth that goes beyond the surface level statement. Something like, okay, services should be loosely coupled, because that is not specific enough for the interviews. So, you should cover these 4 points in front of the interviewer when you do that. Now that we understand cohesion and coupling individually, let us combine them into a practical decision tool. Every service boundary decision comes down to one question. Does this split increase cohesion and reduce coupling, or does it do the opposite? Now, when the answer tells you to keep things together, meaning you should merge rather than split, it looks like this. Two components always change at the same time for the same business reason. Splitting them would require constant synchronous communication between the two new services. They share the same data, and splitting would create complex data synchronization problems. And they are owned by the same team with no organizational reason to separate them. Now, when the answer tells you to split, it looks like this. Two components change for completely different business reasons at different frequencies. They have different scaling requirements. Let's say one is read heavy and the other is write heavy. They are owned by different teams with different release cadences. A failure in one should not affect the other. Or they need different data storage technologies. One needs a relation database and the other needs a document store. Now, here's a common mistake. Teams sometimes split two components because they feel like separate things, even though those components always change together. If the pricing module and the catalog module are always modified in the same sprint by the same team, they have high cohesion with each other. They should probably be one service, even if pricing and catalog sound like different domains. And here's something specifically for interviews. When an interview challenges your boundary choice and asks you to say, why did you put pricing inside the catalog service? You can explain it in terms of cohesion and coupling. For example, you can say that pricing and catalog always change together when you update product listings, and splitting them would create synchronized coupling for every product read. Keeping them together gives us the higher cohesion with no added coupling. If you say that statement in an interview, it's a principled answer that shows you have evaluated the trade-off and not just followed a naming convention. Now, this cohesion and coupling reasoning framework is the most versatile tool for defending service boundary decisions in interviews. Now, let us talk about a dimension of service boundaries that is not purely technical, which is team ownership. In microservices, every service must have one owning team. One team, one service, and this is not just an organizational preference, it is an architectural requirement. Here's why. If two teams co-own a service, every change requires cross-team coordination. Deployment schedules conflict, on-call responsibilities become unclear, code review standards diverge. Over time, the service becomes inconsistent because neither team feels fully responsible for it. Shared ownership creates the same coordination overhead that microservices are designed to eliminate. Now, there are 4 ownership rules to follow. First, one team owns one service. That team controls the code, the database, the deployment pipeline, the monitoring, and the on-call rotation. Second, one team can own multiple services. A team of 6 engineers might own 2 or 3 closely related services. Third, no service has 0 owners. Every service must have a team registered in the service catalog. Orphan services with no owner become unmaintainable liabilities that accumulate technical debt. Fourth, the owning team owns the API contract. They decide what the public interface looks like, how it is versioned, and when breaking changes happen. Let us make this real with an example. In a platform like Uber, the dispatch team will own this dispatch service, and they'll decide how the driver-rider matching works, how the API is structured, and when to deploy changes. The rider team and the driver team consume the dispatch API, but they do not modify the dispatch services code. If the rider team needs a new dispatch feature, they file a request with the dispatch team. And this connects directly to Conway's law from section 1. The team structure mirrors the service structure. When you draw service boundaries, you're also drawing team boundaries. If a boundary does not make sense organizationally, if it would assign a service to a team that has no expertise in that domain, then the boundary is probably wrong. Now, in an interview, mentioning team ownership when explaining your service boundaries shows that the interviewer, that you think about a microservices as an organization's architecture, not just a technical one. That is perspective many candidates actually miss in their interviews, so please don't do that. Now, one of the hardest decisions in microservices is how big or small each service should be, and both extremes can cause problems. When services are too large, you end up with what is sometimes called a mini monolith. Imagine a single order service that handles order creation, payment processing, inventory reservation, shipping calculation, and email notifications. It has 15 database tables and requires, let's say, 8 engineers to maintain. Let's say it deploys, twice a week because changes are risky and require extensive testing. This is a monolith wearing a microservices label. It has all the problems of a monolith, deployment coupling, and team bottlenecks, plus the added cost of being a distributed service and network, also the network overhead and the operational complexity is there. Now, when services are too small, you end up with what is called a nano service. Imagine separate services for order creation, order status, order history, and order cancellation. Each one has a single database table and maybe 200 lines of code. A single view order details request now requires calling all 4 services, adding network latency, and introducing 4 potential failure points. Each service is too simple to justify its own deployment pipeline, monitoring setup, and on-call rotation. The team ends up spending more time managing infrastructure than building features. Now, the right granularity actually sits between these two extremes. A service should be large enough to represent complete business capability and small enough to be owned by a single team of 4 to 8 engineers. It should have enough internal complexity to justify the operational overhead of being an independent service. And here's a useful heuristic. If a service manages fewer than 3 database tables, it is probably too small. If it manages more than 15, it is probably too large. These are not hard rules, but they give you a reasonable range to work with. Now, in an interview, if the interviewer pushes back with, let's say, okay, that service seems too big, or that seems like too many services, now being able to articulate this granularity trade-off shows that you have thought about sizing beyond the textbook guidance of, services should be small. Now, here's another interview scenario to work through. Let's say you're designing a social media platform like Instagram. A candidate in a mock interview proposes these services: user profile service, user settings service, user avatar service, user follow service, user block service, like user notification preferences service. Now the interviewer will ask you to evaluate the design. Now, what would you say? Now let's take a moment to think about this before we walk through the answers. Now, a weak answer to that question would be, let's say a candidate says a statement like, okay, this looks like pretty good. Each service is small and focused, which is what microservices should be. But let's say if the candidate said that statement, that is pretty weak because the candidate accepted the design without actually analyzing cohesion, coupling, or granularity. They just equated small with good, which misses the point entirely. 6 services for user-related functionality is almost certainly too granular. Now, a strong answer would sound something like this statement. Let's say candidate says that, okay, this design is too granular. All 6 of these services relate to a single business capability, which is user profile management. They are all owned by the same team. They change for similar business reasons, and a single user action like update my profile would need to call multiple services to complete. Honestly, I would consolidate them into 2 services. First, a user service that owns profiles, settings, avatars, and notification preferences. These all change when the user updates their account and they share the same consistency requirements. Second, a social graph service that owns follows and blocks. That is generally different domain with different data structures. Relationship between users form a graph, not a row. It has different scaling characteristics because of fan-out queries for feeds. And it may need a different database technology, for example, a graph database or a wide column store rather than a relational database. The user service has high cohesion because everything inside it relates to a single user's account. The social graph service has high cohesion because everything inside it relates to relationships between users. Coupling between them is minimal, limited to the user service providing basic profile data when the social graph service needs to display follower names. Now, what makes this strong is that the candidate identifies the granularity problem, consolidates with clear reasoning based on cohesion and shared ownership, and draws a principal boundary exactly where a genuine domain difference exists. two fundamentally different approaches to splitting a system into services, and the one you choose determines whether your architecture succeeds or fails. Now, the first approach is technical layer decomposition, as shown in the screen here. In this approach, you split the system into an API service, a business logic service, and a data access service. The client talks to the API service forward requests to the business logic service, the business logic service calls the data access service, and the data access service queries the database. The problem with this becomes clear the moment you try to add a feature. Say you would want to add a discount code feature. Now you would need to update the API service with a new endpoint, and after that you would need to update the business logic service with a discount calculation, and then you would need to update the data access service with a new query for discount rules. Now 3 services change for one feature. These services cannot be deployed or scaled independently. You have to rebuild the monolith layers as separate services with network calls in between. Actually, that's kind of worse than monolith. Now let's talk about the second approach, which is the business capability decomposition. Here, each service contains its own API layer, its own business logic, and its own data access for one business capability. A catalog service handles everything related to product listings. An order service handles everything related to orders. A payment service handles everything related to payments. Each one has its own database. Now, when you add the discount code to a feature, only the order service changes. The catalog service and the payment service do not need to change. They do not need to redeploy. The feature is now contained within one service developed by one team. Now, here's a definitive test. When a product manager requests a new feature, how many services need to change? If the answer is consistently only one, you have decomposed by business capability. If the answer is consistently 3 or more, you have decomposed by technical layer. Now in an interview, if an interview sees you drawing, let's say, a front-end service, back-end service, and a database service architecture, they will immediately recognize it as a technical layer split, and then they will challenge it. So you should ideally start with business capability decomposition. Service boundaries become clear only when you trace the workflow that a user action triggers from start to finish. Let us walk through how that works. Now, let us take the e-commerce checkout workflow as an example. Let's say when a customer clicks place order button, a sequence of steps execute. First, the system creates the order, then it reserves the inventory for the items in the order. Then it authorizes the payment, and then it creates a shipment, and finally sends a confirmation notification. Now each step, for example, in this workflow is a distinct responsibility with different data, different failure modes, and different teams. Order creation is write heavy with transactional step. Inventory reservation needs real-time stock data from warehouses. Payment authorization involves external payment providers, with their own latency and failure characteristics. Shipment creation integrates with logistic partners who have their own APIs, and notification sending is fire and forget. It should never block the order from completing. So, how do you use workflows to find the boundaries? There are 4 major steps. First, map out the major user workflows in your system: checkout, sign up, content upload, search, and so on. Second, for each workflow, identify the distinct steps. Third, group the steps that share data and change for the same business reason. Fourth, steps that have different scaling needs, different failure tolerance, or different team ownership become separate services. Now, there is one important consideration when doing this. If 2 steps in a workflow always happen in the same transaction, and a failure in either means that both should roll back together or even separately, those steps probably belong in the same service. Splitting them would require distributed transaction, and that adds complexity without providing any benefit. Now, for interviews, tracing a workflow on the whiteboard and then deriving the service boundaries from that workflow is one of the strongest techniques for demonstrating decomposition skill. It shows the interviewer that you can reason from concrete user actions to architectural decisions. Now, there is a third way to discover service boundaries, and it comes from observing the reads and writes often have fundamentally different characteristics. In many systems, the write path and the read path differ in volume, latency requirements, and data shape, and also scaling needs. When this difference is large enough, separating them into different services or at least different models become a justified architectural decision. Now let us use the product catalog in an e-commerce platform as an example. On the right side, volume is low. Product managers, they update the listings a few hundred times per day. Each update involves complex validation, image processing, and category assignment. The ideal data model for writes is normalized and relational because normalization prevents data inconsistency when updating. Now on the read side, as you can see on the screen, volume is extremely high. Millions of customers browse the catalog every hour. They need fast, denormalized responses with the product name, price, main image, and average rating all in a single query. The ideal data model for reads is denormalized and optimized for fast retrieval because denormalization eliminates the need for joins. Now, if you try to serve both patterns from the same service and the same database, you have to compromise on both. You make the write model denormalized to speed up reads, which makes writes more complex and error prone. Or you keep the read model normalized to simplify writes, which makes reads slower because of the joins. Now the alternative is actually, command query responsibility segregation pattern, which is more commonly known as CQRS. So the idea for that is actually, you separate the write model from the read model. The write service processes, updates, and publishes events. The read service consumes those events and maintains an optimized read model. Section 5 on data ownership will cover CQRS, in more details. Now, when does this decomposition apply? When read volume is listed 10x to 1000x higher than the write volume. When read and write latency requirements differ significantly. When the ideal data shape for reading is different from ideal shape for writing. Now, mentioning read and write separation as a decomposition strategy in an interview shows that the interviewer, that you think about data access patterns, not just the business domains. Now, this slide covers a mistake that comes up frequently in both production systems and interviews, and the reasoning behind why it fails actually illustrates the core principles of good decomposition. Now, the mistake looks like this. Let's say a team looks at their database schema, sees 12 tables, and create 12 microservices. The user service owns the users table, the address service owns the addresses table, the phone service owns the phone numbers table, basically like one table and one microservice for it. Now this fails for three reasons. The first problem is the lack of cohesion. An address service with one table has no meaningful business logic. It is a CRUD wrapper around a database table. It adds network overhead, a deployment pipeline, a monitoring setup for something that could be function call inside the user service. The operational cost far outweighs any benefit. And the second problem is static communication. Displaying a user profile now requires calling the user service, then the address service, then the phone number service, and then the email service. That is 4 network calls for what used to be a single database join. Now latency adds up, failure probability increases with each call, and debugging becomes significantly harder because a single user-facing operation is spread across 4 services. Now the third problem is wrong consistency boundary. When a user updates their profile with a new name and a new address that used to be one transaction, with separate services, you now need to coordinate a distributed update across the user service and the address service. If one succeeds and the other fails, the user has an inconsistent profile, part of their data updated and part of it is not. Now the fix is to group the related tables into services based on business capability. Users, addresses, phone numbers, and emails, they all belong to the user profile capability. They form one aggregate owned by one service chained in one transaction. Now in an interview, if you respond to, let's say, the question by interviewer is like, how many services would this system need? And if you answer that by counting database tables, the interviewer will immediately recognize that the decomposition instinct is not right. So you should please not do that. Now, beyond the decomposition mistakes we have covered, there are 3 specific boundary level anti-patterns that show up pretty regularly during the design phase. And let us go through 4 of them. Now, the first one is circular dependencies. The order service, let's say, calls the payment service to process the payment. The payment service then calls back to the order service to update the order status. Now, this will create a cycle where neither service can function without the other. Neither service can be deployed, tested, or scaled independently because now they form a loop. The fix for this is pretty straightforward. The payment service publishes a payment completed event and the order service subscribes to that event. Data flows in one direction instead of going back and forth. Now the second is just one more call chain. So for example, service A calls service B, which calls service C, and which calls service D, which calls service E. Now, a single user trigger request, actually triggers a chain of 5 synchronous calls, and the total latency is now the sum of all 5 calls. If any one of the service in the chain is slow or unavailable, the entire request fails. The fix for that is to evaluate whether service A truly needs all that data in real time, or whether some of those calls can be replaced with cached data or asynchronous events. The third anti-pattern is what we call anemic services. So these are services that have no business logic and only forward requests to another service. For example, an API routing service that receives requests and passes them to the real services is not a useful boundary. It has an unnecessary network hop with no value. The API gateway already handles this responsibility. Now, the fourth anti-pattern is kernel coupling. This happens when two services import the same shared library that contains business logic. When that shared library is updated, both services must redeploy, even if only one of them needs a change. Now, shared libraries for infrastructure concerns like logging, metrics, or HTTP client configuration are fine. Those change infrequently and have no business logic. But shared libraries for business rules defeat the purpose of the independent deployment. Now, being able to spot these anti-patterns in a whiteboard design, whether it is your own design or the one interviewer presents you for you to evaluate, is a key skill for senior level interviews. So this is something you should write down in your notes. These are the 6 service boundary anti-patterns to have memorized. First is circular dependencies. If service A calls service B and service B calls service A, you break the cycle with events so the data flows in one direction. Second, call chains. If a single request triggers 5 or more synchronous hops through different services, some of those calls should be replaced with caching or asynchronous events. Third is anemic services. So if a service has no business logic and only proxies requests to another service, it is not a useful boundary. You should remove it. Fourth is shared business logic libraries. If two services share a library that contain business rules, those services are coupled at deployment time. A change to the library forces both to redeploy. Fifth is database table equals service. So if each table in the schema has its own service, the decomposition is done by schema structure, not by business capability. And the sixth is the God service. So if one service handles multiple unrelated business capabilities, it needs to be split. And here's a universal test that applies to every boundary you draw. So can this service be developed, deployed, and operated by one team without coordinating with other teams for most changes? If the answer is yes, the boundary is sound. If the answer is no, the boundary needs to move. Now, keeping these anti-patterns, in mind prepares you for the interview questions that come up in almost every senior engineer, interview loop, which would be that, okay, what would go wrong with the microservices design? And then, you keep the 6 anti-patterns and you mention them in the interviews. So that is super important. So we have covered the principles of good boundaries. Now let us talk about the practical techniques that engineering teams use to actually find those boundaries in real systems. So the first technique is event storming. The idea is to get domain experts, engineers, and product managers in a room together. Everyone writes down the events that happen in the system on sticky notes. For example, order placed, payment authorized, inventory reserved, shipment created. You place all these on a wall and start grouping related events together. The groups that form naturally often correspond to the service boundaries. Now, events that cross between groups become the inter-service communication points. In production systems, event storming has been a very common, effective, one of the most effective ways I would say to get alignment between engineering and product teams on where the boundaries should be. Now, the second technique is to start with the transaction boundaries. Identify every operation in the system that must be atomic, meaning it must succeed or fail as a whole. Everything that must succeed or fail together belongs in one service. If created order, and add line items must happen in one transaction, they belong in the same service. If create order and reserve inventory can be eventually consistent, they can be separate services. Now the third technique is to ask, okay, what changes together? Now look at your version control history. Which files always change the same commit? Which modules always appear in the same pull request? Code that changes together has high cohesion and should stay together in the same service. Now the fourth technique is to actually follow the team structure. If your organization already has a payments team and an orders team, those are your starting boundaries. Conway's law tells us that the architecture will drift towards the team structure over time regardless, so aligning proactively avoids fighting that natural force. For interviews, if an interviewer asks you, okay, so for example, if they say, how would you discover service boundaries for a system you are not familiar with? Mentioning event storming and transaction boundary analysis shows a practical methodology. That is much stronger than saying a statement like, okay, I would think about it and, like go from step by step. But you need to define, have more structure and mention these techniques like event storming and, starting with transaction boundaries. So let us put everything together with a concrete decomposition of an e-commerce platform like, let's say, Amazon. The architecture for that would be, most likely an API gateway, which will be routing requests to 6 services, each with its own database. Let us walk through, each one of them one by one and why these boundaries work. So the catalog service manages product listings, descriptions, images, categories, and service search indexing. It changes when the merchandising team updates product content. It is read heavy and needs caching and search optimization. The cart service manages shopping carts, saved items, and cart's persistence across sessions. It changes when the conversion team experiments with the cart features. It needs session level storage with fast reads and writes. The order service manages the order lifecycle from creation through to completion. It changes when order workflows rules change. The core aggregate is the order with its line items as we have covered earlier. Then the payment service handles authorization, capture, refunds, and payment method management. So it changes when new payment providers are added. It integrates with external payment gateways, that have their own APIs and latency characteristics. And then we have the inventory service, which tracks stock levels, warehouse locations, reservations, and restocking triggers. It changes when warehousing logistics change. It needs real-time accuracy for stock counts because overselling has direct financial consequences. The shipping services manages, shipment creation, carrier integration, package tracking, and delivery estimates. It changes when logistics partnerships change. So each of these services map to a distinct business capability and is owned by a separate team and manages its own database. A change in how payment providers are integrated does not affect how the catalog is searched. A change in shipping carrier APIs does not affect how orders are tracked. Now, having a well-reasoned e-commerce decomposition like this ready to present in an interview will save you time and demonstrate experience with what is one of the very most common system design problem domain. Let's look at a completely different domain. So that would be, let's say, a ride-sharing platform, something like Uber or Lyft. Now, the ride-sharing service handles rider accounts, ride requests, and ride history. It stores ride profiles, save locations, and ride preferences. It exists as a separate service because rider-facing features change independently from driver-facing features. Now, the driver service handles the driver onboarding, availability tracking, and earnings management. It stores driver profiles, documents, vehicle information, and earning records. The driver lifecycle is a separate domain with different regulations like background checks and vehicle inspections that do not apply to the riders. The trip service manages active trips and the trip lifecycle. It tracks the trip state from requested to matched to in progress to completed, along with the route and timestamps. That is the core domain object in ride-sharing platform. The trip lifecycle is the most complex workflow in the system. Now, the pricing service handles surge pricing, fare estimation, and fare calculation. It works with pricing models, real-time demand data, and fare rules. Pricing algorithms change frequently as the economics team adjusts surge models, and these changes should not require deploying the trip service. Now, the dispatch service actually, it handles the driver-rider matching and route optimization. It works with real-time driver locations, matching algorithms, and ETA calculations. This is latency critical, requiring sub-second matching decisions. It needs specialized infrastructure, in-memory data stores, and geospatial indexing. The payment service handles rider changes, driver payouts, and promotional codes. Financial data has strict compliance requirements and separate audit needs that justify keeping them in its own service. Now, there is a key insight here worth calling out. The dispatch service and the pricing service both need real-time location data. You might think they should be one service, but they change for completely different reasons. Pricing changes when the economics team adjusts search algorithms. Dispatch changes when the engineering team optimizes matching algorithms. They have different teams, different release cadences, and different scaling characteristics. Same data dependency and different business capabilities. Now, ride sharing is one of the most frequently asked system design problems. Having a clear system service decomposition with reasoning prepares you in advance to give a significant head start in the interviews. Now, let's look at two or more domains to round out more examples. First, a streaming platform, let's say like Netflix or Disney Plus. Here, the user profile handles profiles, preferences, parental controls, and account settings. The catalog service manages movie and show metadata, genres, cast information, and region availability. The recommendation service, it actually generates personalized suggestions based on the viewing history and similar user patterns. It is compute intensive, relies on ML models, and changes independently from catalog content. Then there is the playback service, which handles stream initiation, quality adaptation, digital rights management, and it is latency critical and closely tied to the CD infrastructure. And then there's the billing service, which manages subscriptions, payment processing, plan management, and invoicing. It changes when the pricing tiers change and has strict financial compliance restrictions. Now, the key insight here is that, like in this architecture, is about the recommendation and playback. Both are part of the, watching a movie experience, so you might be tempted to combine them. But they have completely different pair of profiles. Recommendations, they are batch computed, ML heavy, and can tolerate latency. However, playback is real time, infrastructure heavy, and must respond in milliseconds. They both have different scaling needs and different technology stacks, which that makes them drive into be part of the different services. Now let's talk about a banking platform. For this, the account service will handle account creation, balance inquiries, and account status. It is a core entity that every other services references. The ledger service handles transaction recording, double entry bookkeeping, and balance updates. Every financial movement is a ledger entry. This service must be append only and fully auditable. The transfer service initiates and executes transfers between accounts. It orchestrates the Saga, so debit the source account, credit the destination account, record the entity in the ledger. The risk service handles fraud detection, transaction limits, and suspicious activity monitoring. It evaluates every transfer in real time and changes when compliance regulations change. And the notification service handles alerts for transactions, low balances, and suspicious activity. It is fire and forget and should never block a financial transaction from completing. Now, the key insight here is that the banking, the ledger service is the most critical service because it's a system of record. Every other service eventually writes to or read from the ledger. This difference from the e-commerce, there's a difference from the e-commerce platform, because where the order service is the central, or the ride sharing where the trip service is the central part. Each domain, essentially has its own center of gravity. Now, having the decomposition examples across multiple domains like e-commerce, ride sharing, streaming, and banking shows the interview that you can apply decomposition principles to any system, not just the one you actually prepared for. Let's work through one more interview scenario. An interview, let's say, asks you to decompose a messaging platform like WhatsApp into microservices. And now let's think about it before jumping to the answer. Now, for a question like that, not a good answer would be something like, let's say candidate says that, okay, I would have a message service, a user service, a group service, a media service, a notification service, and a presence service. That answer is not good because the candidate lists services without explaining why those boundaries exist. More importantly, they did not discuss the unique characteristics of a messaging platform that should drive the decomposition, which is, real-time delivery requirements, massive fan out for group messages, presence tracking at enormous scale, and the very different storage needs for media versus text. Now, for the same question, a strong answer would look something like this. Let's say the candidate says that, okay, I would decompose based on the distinct business capabilities and the very different scaling and technical requirements. First, a user service for account management, contacts, and profile information. This is a standard CRUD with relatively low write volume. Second, a messaging service for the core message delivery pipeline. This is the heart of the service, handling one-to-one and group messaging routing, and delivery receipts and end-to-end encryption. This service has extreme throughput requirements. The platform at WhatsApp scale handles over 100 billion messages per day. It needs a specialized storage engine optimized for write-heavy and sequential message storage. Third, a group service for group creation, membership management, and group metadata. I'm separating this from messaging because group management, adding members, changing group names, setting permissions is a different business capability from message delivery. And group fan out, sending one message to 256 members, has different scaling characteristics than one-to-one delivery. Fourth, a media service for image, video, and document storage and delivery. Media has completely different storage requirements, blob storage with serial delivery rather than a message database, and it has a different latency tolerance. Uploading a video can take seconds, but that upload should not block text message delivery. Fifth is a presence service for online offline status and last seen timestamps. This is extremely high frequency data, so every app open and close triggers a presence update across 2 billion users. It needs a specialized in-memory data store rather than a relational database. So if you say that in the interview as answer, so what makes this answer a strong answer is that the candidate explains the reasoning behind each boundary, different scaling profiles, different storage needs, and different business capabilities. They include real-world scale numbers to justify the separations, not just the abstract principles. So we have covered principles, techniques, examples, and anti-patterns. Now let us put it all together into a single decision framework you can use whenever you are unsure whether to split or merge two components. You split into separate services when the following conditions hold. Different teams own them and have different release cadences. They have significantly different scaling requirements, at least a 10x difference in load between the two. They change for different business reasons at different frequencies. Failure in one should not affect the other. They need different data storage technologies, or they have different compliance or security requirements. Now you should keep together in one service when the following conditions hold. They always change together for the same business reason. Splitting would require synchronous calls between them for the most operations. They share the same data and need transactional consistency. They are owned by the same team with no foreseeable organizational split, or one cannot do anything useful without the other. After you draw your service boundaries, validate each boundary against 3 questions. The first is the independence test. Can each service deploy without coordinating with other services? The second is the cohesion test. Can you describe each service's purpose in one sentence without the word and? And the third is the coupling test. Does a change in one service really require a change in another? If all 3 answers are yes for every service, your boundaries are sound. If any answer is no, that boundary needs to be considered. And here's something important for interviews. Running through this checklist out loud during an interview shows the interviewer that you have a repeatable process for validating service boundaries, not just intuition. That distinction matters at a senior level where interviewers are evaluating whether you can make consistent, principled discussions, not just one-off good guesses. This framework is the most practical tool in this entire section. The split criteria, the merge criteria, and the 3 validation questions. These are definitely worth keeping in your mind for preparing for interviews. Let's bring everything in this section together. We started with the business capability decomposition. Services should map to business functions, not technical layers or database tables. This is a starting point for every decomposition. We covered bounded context from domain-driven design. The same word means different things in different parts of the business. Each context gets its own model, its own database representation, and its own definition of shared terms. After that, we covered aggregates. So the aggregate is the consistency boundary within a service. Everything inside is one transaction, everything outside is eventually consistent. Then we covered cohesion, so we group things that change together for the same reason. And coupling, so we minimize dependencies between services, aim for contract coupling, and avoid database coupling. Then we covered ownership, so one team, one service. Team boundaries should match service boundaries following Conway's law. Then we covered granularity, so 4 to 8 engineers per service, 3 to 15 database tables, large enough to be useful, small enough to be independently owned. After that, we covered workflow decomposition, so we trace user workflows to discover where service boundaries naturally fall, and read-write decomposition where dramatically different read and write patterns can justify separate services. Now the common interview mistakes to avoid are here. First, listing services without explaining the reasoning. That shows memorization, not design skill. Instead, explain why you choose each boundary. So for example, you can say a statement like, I chose these boundaries because each maps to a distinct business capability with different scaling needs and team ownership. Second, creating one service per database table. That produces chatty anemic services with no cohesion. Instead, group related tables under one business capability. Third, splitting by technical layer. When every feature touches every service, independence is lost. Split by business capability so each feature changes one service. Fourth, ignoring team structure. Architecture that does not match the organization will drift. Align service boundaries with team boundaries per Conway's law. Fifth, not validating boundaries. Boundaries chosen by gut feel without a principal check are unreliable. Apply the independence, cohesion, and coupling test to each boundary. Now, a few numbers worth remembering. The ideal team size per service is 4 to 8 engineers. A reasonable range for database tables per service is 3 to 15. A new feature should typically change one service, not 3 or more. A platform like WhatsApp handles roughly 100 billion messages per day. A typical e-commerce platform has 5 to 8 bounded contexts: catalog, cart, order, payment, inventory, shipping, customer, analytics. And now here's how this section connects to what comes next. Section 4 on communication patterns answers the natural follow-up question. Okay, now that we have drawn boundaries, how do these services talk to each other? The choice between asynchronous and synchronous communication depends directly on the coupling level you're willing to accept. Section 5 on data ownership tackles the hardest consequence of good boundaries. When each service owns its own data, how do you handle cross-service queries and data duplication? And Section 6 on sagas and consistently builds directly on aggregates. Everything inside an aggregate is a local transaction. Everything across aggregates requires a saga pattern. So in Section 3, we drew boundaries between microservices. We decided what each service owns and where the lines sit. The immediate next question is this: how do these different microservices they communicate to each other, how they talk to each other? So now this is not necessarily a technology choice. Picking REST or gRPC or message queue is secondary. The real decision is about communication patterns, and those patterns determine how tightly your services are coupled, how much latencies your users will experience, how your system behaves when something fails, and whether your data stays consistent across different microservices. So most real systems, they use multiple communication patterns at the same time. Like, think about what happens when someone requests a ride on a platform like Uber. The ride mobile app send a REST request to through the API gateway. Internally, the dispatch services, it uses gRPC to match drivers with low latency. When the trip finishes, the trip service publishes an event to a stream like Kafka. The payment service picks up that event to charge the rider. The analytics service picks it up to update the dashboards. The notification service picks it up to send the receipt. A single ride request touches at least 3 different communication patterns. In this section, we'll cover each of these patterns and when to use them. We'll start with the fundamental choice between synchronous and asynchronous communication. Then we'll go through REST, gRPC, and GraphQL for synchronous calls. We'll cover message queues and event streams for asynchronous communication, and the difference between commands and events. We'll spend also significant time on resilience patterns like timeouts, retries, circuit breakers, bulkheads, and backpressure, and we'll close with contact versioning, correlation IDs for debugging, and a decision framework that ties everything together. By the end of this section, when an interviewer asks you, how your services communicate, you'll be able to choose the right pattern for each interaction and explain exactly why. The first communication decision for any interaction between two microservices is this: does the caller need to wait for a response, or can it move on immediately? There is a choice between synchronous and asynchronous communication, and it is the foundation for every other communication decision in this section. In synchronous communication, service A sends a request to service B and waits. It is blocked. It cannot do anything until service B responds or a timeout occurs. Think of the order service, let's say calling the payment service to authorize a payment. Now the order service cannot confirm the order until it knows whether the payment has went through. So it sends a request and waits for the answer. However, in asynchronous communication, service A sends a message and continues immediately. It does not wait. Service B processes the message whenever it is ready. Think of the order service sending an order confirmation event. The notification service will eventually pick up that event and send a confirmation email, but the order service does not wait for the email to be sent. It moves on to the next request. Now, the trade-offs between these two patterns is pretty fundamental. Synchronous communication gives you immediate feedback. You know right away whether your call has succeeded or failed, but it does create a temporal conflict. If service B is down, service A is stuck. It cannot proceed, and the failure in one service will propagate directly to the other. So this coupling here in that case is not ideal. Now asynchronous communication removes this coupling. Service A does not depend on service B being available right now. The message sits in the queue or stream until service B is ready to process it. But you do lose immediate feedback. You do not know if service B processed the message successfully until some later point of time. So the practical rule here is pretty straightforward. If the caller needs a response to continue its work, you use synchronous communication. For example, the order service needs to know if the payment was authorized before it can confirm the order. So that is synchronous. If the caller does not need to wait for the result, you should use asynchronous communication. For example, in that case would be the order service does not need to wait for the confirmation email to be sent. So that operation can be asynchronous. When discussing communication in an interview, start with this choice for each interaction. Deciding synchronous versus asynchronous first before picking any specific technology shows that you are thinking about coupling and failure modes rather than jumping straight to implementation details, which is super important to do in the interviews. Now REST, which stands for Representational State Transfer, is the most widely used communication protocol for microservices. It uses HTTP, it works with JSON, and is a default choice when you need broad compatibility across different types of clients. REST fits well in a very few specific situations. First, public-facing APIs where browsers, mobile apps, and third-party integrations all need to call your service. REST works everywhere, so every language, every platform, every tool understands HTTP and JSON. Second is CRUD-style operations on resources. Creating an order, reading a product, updating a shipping address, deleting a saved item. REST maps naturally to these CRUD operations. The third is interactions where simplicity and tooling support matters much more than raw performance. Now here's what a typical REST interaction looks like. The client sends an HTTP post to the order's endpoint, let's say with a JSON body containing a customer ID and a list of items. The server responds with HTTP 201 created and a JSON body containing the new order ID, the status, and the total. As you can see, this is simple to understand for the users, for the developers. It's readable, it's easy to test, and it's easy to debug. But REST has some several limitations as well in a microservices environment, and understanding these limitations is what helps you know when to choose something else. The first limitation is overfetching. When the client calls the order's endpoint, it gets back the entire order object with all 30 fields, even if it only needs the order ID and the status. A mobile app on a slow network is downloading data essentially it will never display. The second limitation is chattiness. Displaying a single product page might require separate calls to the catalog service for product details, the pricing service for current price, the inventory service for stock availability, and the review service for ratings. So that is 4 separate HTTP round trips to render one page. The third limitation is the lack of native streaming. REST is strictly request response, so it does not support server pushing updates to the client or bidirectional communication without workarounds. The fourth limitation is payload overhead. JSON is human readable, which makes debugging easy, but JSON payloads are text-based and significantly larger than binary formats. For internal service-to-service calls happening thousands of times per second, that extra size adds up in terms of network bandwidth and serialization cost. Now, REST is safe default for any external facing API. For internal service-to-service calls, these limitations become more relevant, and this is where gRPC enters the picture. Now that we understand where REST has limitations, let's talk about what many large-scale systems use for internal service-to-service communication. gRPC is a high-performance RPC framework originally developed by Google. It uses protocol buffers, commonly called Protobuf, for serialization and HTTP2 for transport. It is designed for specific situations where both the caller and the receiver are services under your own control, and performance and type safety matters quite a bit. gRPC fits well for internal service-to-service calls. When the dispatch service needs to query the driver location service thousands of times per second with, let's say, a sub 10 millisecond latency budget, the overhead of JSON serialization and HTTP 1.1 in REST states, it starts to matter. So now that becomes an issue, so that gRPC is what addresses that issue directly. Now, the way gRPC works is through contract definitions. You write a proto file that defines the service, its methods, and the structure for requests and responses. From the proto file, the code generators they produce typed clients and server stubs in whatever language you need. There is no handwritten HTTP parsing, no guessing about what fields exist and what types there are. If a field is an integer in the proto definition, it is an integer in every language that generates codes for that definition. All the differences are meaningful. Protobuf messages are binary, roughly 5 to 10 times smaller than the equivalent JSON payload. HTTP2 supports multiplexing, which means multiple requests can share a single connection. It compresses headers automatically. And because gRPC generates type stubs, you get compile time guarantees that the request and response structures are correct. However, the trade-off is real. Binary payloads are not human readable. You cannot just look at a gRPC request the way you can look at a JSON body in a REST call. Debugging requires specialized tools. Browsers cannot call gRPC endpoints directly without a proxy layer like gRPC web. And both sides must share the proto definition file, which means coordinating contract changes across teams. A strong pattern that works well in interviews is to say that, okay, REST is for external APIs, gRPC is for internal service-to-service calls. When you say that in the interviews, this shows that you pick the protocol based on what the consumer needs and what the requirements are, rather than picking one technology or for pretty much every use case, which is not ideal to say in interviews. Now, GraphQL is a query language for APIs that solves a specific problem, letting the client decide exactly what fields it needs. It is not a replacement for REST. It is not a replacement for gRPC. It serves a different purpose entirely, and understanding where it fits is what matters quite a bit. GraphQL fits well when different clients need different subsets of the same data. A web dashboard might need 15 fields from an order. A mobile app showing an order summary might need only 3 fields: the order ID, the status, and the total. With REST, both clients receive the full 30-field order object. With GraphQL, each client specifies exactly what it needs, and the response contains only those fields. So no wasted bandwidth, no unnecessary data processing on the client side. GraphQL also works well as an aggregation layer. If rendering one screen requires data from the catalog service, the pricing service, and the inventory service, a GraphQL gateway can combine those into a single client request. The client sends one query, the gateway translates into calls to the appropriate backend services and assembles a response. The client does not need to know which backend services exist or how to call each one. So now, where does the GraphQL fits in microservices architecture is specifically at the edge between the clients and your backend. It should not be used as a service-to-service protocol. The backend services communicate with each other using REST or gRPC. The GraphQL gateway sits in front of them and translates client queries into those internal calls. Now, GraphQL does come with some real risks. A single complex query can trigger expensive operations across multiple backend services. Without query complexity limits, a client can accidentally or even maliciously send a query that fans out to dozens of backend calls and overloads the system. The GraphQL gateway can also accumulate business logic over time, becoming what is sometimes called a God gateway. The gateway should only translate queries and aggregate results. It should never contain business rules. And caching is also harder with GraphQL because every query can be unique, unlike REST where we cache based on the URL. Now, in the interviews mentioning GraphQL as an edge aggregation layer rather than a service-to-service protocol will show you that you understand where it adds value and where it creates risk. So that is super important to mention in the interviews. I've covered 3 synchronous communication protocols. Let us put them side by side and understand where each one of them is the right choice. Now, REST is best for public APIs, CRUD operations, and situations where broad client compatibility matters. It uses JSON, which is text-based and human-readable. Performance is moderate. Type safety is weak because there is no compile time contract between the client and the server. REST does not support streaming natively, but it works in every browser, has straightforward HTTP caching, and is the easiest to debug because you can read the payloads directly. Now, gRPC is the best for internal service-to-service communication where performance matters. It uses Protobuf, which is binary and 5 to 10 times smaller than the JSON. HTTP2 gives you multiplexing and header compression. Type safety is strong because both sides generate code from the same proto definition. Streaming is built in, service streaming, client streaming, and bidirectional streaming all work natively with it. The trade-offs are that it requires a proxy for browser access, binary payloads are harder to debug, and caching requires custom implementation here. Now, GraphQL is best as a client-facing aggregation layer, particularly for mobile apps that need flexible queries. It uses JSON for responses, and it lets the client specify exactly what fields it needs. Type safety is moderate through the schema. It supports subscriptions for real-time updates through a separate protocol. Caching is harder because every query is potentially unique. Now, the typical pattern in production microservices is to use REST for public-facing APIs and third-party integrations, gRPC for internal service-to-service calls where latency budgets are tight, and optionally a GraphQL layer at the edge for mobile and web clients that need flexible queries. Many systems use REST and gRPC together without any GraphQL layer at all. Now, in the interviews, the key is not to say that, okay, I would use REST or I would use gRPC. The key is to say that which protocol for which interaction and why. You should say something like, okay, REST for public API because it has broad client compatibility, gRPC for internal service calls, between the, let's say, the order service and the payment service because the latency budget is tight and we need type contracts. So when you provide answers like that with that level of specificity in interviews, that is very ideal and the interviewers like to see that. Let us test with what we have covered so far with some practice problems that you might actually see during, as part of interview questions. So let's say the scenario is this. You're designing the communication between services in a food delivery platform. Let's say the interviewer asks you, okay, how would the rider app communicate with your backend and how would your backend services communicate with each other? Now let's take a moment to think about the answer. Now a weak answer to this question would be something like, okay, everything will use REST. It is simple and well understood and easy to implement. The problem with that answer is that it ignores the different requirements of external versus internal communication. Internal calls between the dispatch service and the driver location service happen thousands of times per second with a sub 10 millisecond latency budget. REST with JSON serialization adds unnecessary overhead for those calls. Using one protocol for everything, it also tells the interviewer that you have not considered the different performance and compatibility requirements for each interaction. A strong answer would address each interaction separately based on its own requirements. So for example, for communication between the rider app and the backend, REST through an API gateway is the right choice. REST gives you broad compatibility across iOS, Android, and web clients. The API gateway will handle the authentication, rate limiting, and request routing. And this is exactly the type of interaction REST is designed for. For internal service-to-service calls, gRPC is a better fit. The dispatch service needs some 10-second millisecond responses from the driver location service when matching a rider with the nearby drivers. gRPC's binary serialization and HTTP2 transport deliver the performance needed, and the proto definitions provide compile time safety between teams. For communications that does not require an immediate response, asynchronous events are the right pattern. When a trip completes, the trip service publishes a trip completed event, and the payment service, it consumes that to charge the rider. The analytics service will consume it to update the dashboards. The notification service will consume it to send the receipt, and none of these need to block the trip completion flow. Now, what makes this a strong answer is that the candidate matches each communication pattern to a specific requirement: client compatibility, low latency, or decoupling. Each choice has a clear reason behind it. So we have covered synchronous communication patterns. Now let us move to asynchronous side. The first asynchronous pattern is the message queue. A message queue is a buffer that sits between a producer, the service sending a message, and a consumer, the service processing it. The producer puts a message on the queue and moves on to his next task. The consumer picks up the message whenever it is ready. Now, the defining characteristic of a message queue is that each message is delivered to exactly one consumer. If you have 3 work instances consuming from the same queue, each message goes only to one of them. The queue distributes work across consumers. This makes queues ideal for task distribution. Now, message queues are the right choice in three common situations. The first is background processing. A user uploads a video, the API responds immediately with upload received. A worker picks up the video encoding task from the queue and processes it asynchronously. The user does not have to wait for the encoding to finish. Now, the second is load leveling. During a flash sale, let's say the order service might receive 10,000 orders per minute. The payment service can only handle 2,000 per minute. Without a queue, the payment service will be overwhelmed. With a queue, the burst is absorbed. The payment service processes messages at its own sustainable pace. Orders still get processed, just with a small delay during the peak load. The third is decoupling. The order service does not need to know which service, specific service processes the payments. It puts a message on the queue, then the payment service or any other future replacement service will pick it up. If the payment service, processing service changes, the order service does not need to know at all. Now, here's how it works in a real system. Let's say on a platform like Amazon, when you click, let's say, place order button, the API returns immediately with the order confirmation. The actual payment processing, inventory reservation, and shipping creation happens asynchronously through messages. This is why your order status shows processing for a few seconds before updating. The queue is absorbing and distributing the work behind the scenes. Now, the interview takeaway here is simple. Whenever the caller does not need an immediate response and the work can happen in the background, a message queue is usually the right pattern. Now let us look at the second asynchronous pattern, and this one is different from a message queue in a fundamental way. An event stream is durable, ordered log of events that multiple consumers can read independently. The critical difference from a message queue is this. In a queue, each message goes to one consumer. In an event stream, every consumer can read every event. Now, think about what happens when an order is placed on a large e-commerce platform like Amazon, for example. That single event is relevant to the payment service, the inventory service, the shipping service, the analytics service, and the notification service. If you put that event on a message queue, only one of those services will receive it. With an event stream, all 5 services read the same event independently. Each consumer in an event stream maintains its own read position called an offset. One consumer might be processing events in real time, another might be running a few seconds behind, a third might be a brand new service that just deployed and is reading events from the beginning of the log to build up its initial state, so they do not interfere with each other. Adding a new consumer has no effects on the existing ones. Now, this replay capability is one of the most powerful aspects of event streams. Imagine your team deploys a new analytics service and it needs all historical order events to build its initial dashboards. With a message queue, those messages are gone after the consumption. With an event stream like Kafka, the new service reads the stream from the beginning, processes every historical event, and catches up to the present. Here's a real-world example. On a platform like LinkedIn, when you update a job title, that event is published to an event stream. The search index service consumes it to update search results so people can find you by your new title. The feed service consumes it to notify connections. The recommendation engine consumes it to update job suggestions based on a new role. The analytics service consumes it to track engagement patterns. Each consumer processes the same event independently at its own pace. Now, event service streams are the right pattern whenever multiple services need to react to the same event independently. When event history matters, or when you want services to react to what happened rather than being told what to do. So the distinction between commands versus events seems subtle when you first encounter it, but has a direct impact on how tightly coupled your microservices are. Getting this wrong creates a tight coupling even when you're using asynchronous messaging, which defeats the purpose. A command essentially says, okay, do this. It is an instruction directed at a specific service. The sender knows exactly who will process it and expects a specific outcome. For example, a command could be like, okay, process payment with order ID 123 and amount $59.98. This is a command sent to the payment service. The sender knows the payment service exists, knows its API, and expects the payment to be processed. An event would say something like, okay, this happened. It is a notification that something has happened or occurred. The publisher, does not know and does not care actually who and which service consumes it. It does not expect any specific outcome. For example, of an event could be, okay, order placed with order ID 123 and customer ID 456. That is an event published to a stream. The order service has no idea which microservices will react to it. Now, why does this matter for coupling? Commands create coupling because the sender must know about the receiver. The order service must know that the payment service exists. It must know the payment service API. If the payment service is renamed, moved, or replaced, the order service needs to be updated. The two services are tied together through that command. Now, events reduce coupling because the publisher does not know about the consumers. The order service publishes, like order placed event, without the knowing the payment service, the notification service, and the analytics service, which all consume that same event. A new loyalty service can start consuming the same event tomorrow without changing a single line of code in the order service. Now, the guideline for choosing between them is based on what you need. Use commands, when you need a guaranteed outcome from a specific service. Authorizing a payment before confirming an order is a command because you need to know if it succeeded. Use events when you want to notify the system that something has happened and let interested services react on their own. Publishing order placed and letting various services decide what to do with that information is an event. Now, when describing communication patterns in an interview, you should use the correct terminology. The order service, you can say in the interview that, the order service publishes an order placed event, which sounds fundamentally different from the order service sends a process payment command to the payment service. The first is loosely coupled, second is tightly coupled. Interviewers, they do notice this distinction, and at using the terms correctly signals that you understand coupling at the message level, which is super important in the interviews. Now that we understand both message queues and event streams, let us put them side by side so the differences are clear. The delivery model is the most fundamental difference. In a message queue like RabbitMQ or SQS, each message goes to exactly one consumer. In an event stream like Kafka or Kinesis, each event goes to all consumers. Now, message persistence work differently too. In a queue, the message deleted after it has been consumed. Once the worker processes the message, it is gone. In a stream, events are retained for a configurable duration that could be days, weeks, or even indefinitely. Now, consumer tracking is also different. In a queue, the queue itself tracks what has been delivered. In a stream, each consumer tracks his own position using an offset. This means each consumer reads at his own pace without affecting others. Now, replay capability follows directly from persistence. In a queue, there is no replay. Once a message is consumed, it is gone forever. In a stream, consumers can reread from any point in the log. This is what makes it possible for a new service to catch up on the historical events. For ordering, queues, they provide best effort in ordering. For example, per queue FIFO, which is first in, first out. Streams, they guarantee ordering within a partition, which is stronger guarantee for use cases where, event sequence matters. For throughput, message queues typically handle thousands of messages per second. Event streams like Kafka can handle millions of events per second with partitioning. Now, the choice between them comes down to the use cases. If only one consumer should process each message, use a queue. Background jobs, work distribution, and load leveling are queue problems. If multiple consumers need the same event, you use a stream. Broadcasting an order event to payment, analytics, and notification is a stream problem. If you need replay capability for rebuilding state or onboarding new services, that requires a stream. Now, many production systems, they use both. Message queues handle specific task routing where one worker should process each message. Event streams handle system-wide event broadcasting where many services need to react to the same event. When a single user action triggers calls to multiple downstream services, you face what is called the fan-out problem. How you handle it determines both the latency and the resilience of your system. Now, consider what happens when a user clicks on place order button on an e-commerce website like, let's say, Amazon. The order service needs to check inventory, calculate the final price, authorize the payment, and the payment call itself triggers a fraud check. And that is 5 downstream calls from a single user action. If each call takes 50 milliseconds and they happen one after the other, the total latency is 250 milliseconds. If the fraud check is slow at 200 milliseconds, the entire order now takes 400 milliseconds. And if any single service in that chain is down, the entire order fails. Now there are 4 strategies to manage this. The first strategy is to parallelize the independent calls. Inventory check, pricing calculation, and fraud check do not depend on each other. They can run at the same time. Only payment authorization needs to wait for the fraud check result. Running independent calls in parallel reduces the total latency from the sum of all calls to the duration of the longest parallel branch. The second strategy is to make non-critical calls asynchronous. The notification that confirms the order does not need to complete before the order is confirmed. Publish an event and let the notification service process it later. This removes it from the critical path entirely. The order succeeds whether or not the email sends in time. The third strategy is to cache frequently needed data. If the order service calls the pricing service for every order and pricing data changes only a few times per day, caching pricing data locally eliminates the network call for most requests. The fourth strategy is to set up per hop timeout budgets. So for example, if the total request budgets from client to response is 500 milliseconds, divide that budget across each downstream call. Allocate 100 milliseconds to inventory, 100 milliseconds to pricing, 200 milliseconds to payment including the fraud check, and 100 milliseconds for overhead. If any hop exceeds the budget, you fail fast rather than consuming the remaining budget, waiting for a response that may actually never come. When an interviewer sees a fan-out approach in your design during the interview, they will ask you how you handle it. Having a clear strategy ready, parallelizing the independent calls, pushing non-critical work to async, caching the stable data, and setting timeout budgets are exactly what they are looking for. Let's work through a more detailed fan-out scenario. So let's say the practice problem is, you're designing the checkout flow for an e-commerce platform. When a user clicks on the place order button, your order service needs to verify inventory, calculate the final price with discounts and tax, authorize payment, create a shipment record, and send a confirmation email. The interviewer, let's say that they ask you to walk you through the communication pattern for this workflow. Now let's take a moment to think through which calls are critical, which are independent, and which do not belong on the critical path at all. So not a good answer would be like, the order service calls each downstream service one at a time. First inventory, then pricing, then payment, then shipping, then notification, and each call will be rest. So if someone gives that answer in the interview, the problem with the answer is that sequential synchronous calls produce the maximum possible latency. The sum of every single call and the maximum fragility, and any one failure will block everything. Notification has no business being on the critical path because it does not affect whether the order succeeds or fails. Now a strong answer will separate these calls into 2 categories: critical path synchronous calls and non-critical asynchronous events. On the critical path, inventory check and pricing calculation are independent of each other. They can run in parallel. Both must succeed before proceeding. Then payment authorization happens synchronously because the order cannot be confirmed without knowing that the payment has succeeded. Shipment creation does not need to block the order confirmation. The order service publishes an order confirmed event and the shipping service consumes it to create the shipment asynchronously. If the shipment creation fails, it retries from the event. The order is already confirmed by then. Now, the notification itself is fully asynchronous, so the order service publishes the same order confirm event and the notification service consumes it to send the confirmation email. If the email fails, the order is still valid. With this design, the critical path is the longer of inventory check and pricing calculation plus payment authorization. If the inventory and pricing each take 50 milliseconds and they run in parallel, that step takes 50 milliseconds. Payment takes 100 milliseconds, and total checkout latency is about 150 milliseconds instead of 300 milliseconds for sequential calls. So what makes this answer strong is that the separation of critical from non-critical, the parallelization of independent calls, and the use of asynchronous events for fire and forget steps, and also the specific latency math that quantifies the improvement. Every network call in a microservices system must have a timeout, every single one, and this is not optional. A call without a timeout can hang indefinitely, holding threads, connections, and memory that other requests will need. Now let us walk through what happens without timeouts. For example, the payment service, will become slow. Instead of responding in 100 milliseconds, it will take 30 seconds, for example. And in that case, let's say the order service, it sends a request and then it has to wait. And then it has to wait for more than 30 seconds. Meanwhile, the thread handling that request is blocked. It cannot serve anyone else. And now you have to multiply that. Every order request that hits the payment service also waits 30 seconds. In this situation, the threads pile up, and within a short time, every available thread in the order service is stuck waiting on the payment service. Now, new orders cannot even begin processing because there are no free threads to handle them. The order service has effectively gone down, and not because something is wrong with its own code, but because the payment service is slow. And now this is the cascading failure, and timeouts are the first line of defense against it. Now the way to set timeouts in a microservices system is through per hop timeout budgets. If the total request budget from the client to the final response is, let's say, 2 seconds, each downstream call gets a fraction of that budget. Inventory check gets 200 milliseconds, pricing calculation gets 200 milliseconds, payment authorization gets 500 milliseconds because it calls an external payment provider that is inherently slower. Serialization, network transit, and processing overhead account for about 300 milliseconds, so that leaves 800 milliseconds to buffer. Now, if the inventory service does not respond within 200 milliseconds, the calls will fail immediately. The order service returns an error rather than consuming 1.8 seconds of the remaining budget waiting for a response that is unlikely to arrive. For setting the right timeout value, the P99 latency of the downstream service is a good starting point. P99 means 99% of requests complete within this time. Setting the timeout at P99 means you tolerate the normal range of response time but cut off the extreme outliers that indicate something is wrong. Timeout should be on every outgoing call. That includes calls to downstream services, database queries, and cache lookups. You should log every timeout hit so your monitoring can detect when a downstream service is degrading. And never use no timeout or infinite timeout as a default in any configuration. Mentioning timeouts proactively when describing service communication in an interview shows that you understand how distributed systems they behave in production, not just a happy bar design where everything works perfectly. So we have established that every call needs a timeout. When a call fails or times out, then the natural response is to try again. But retrying incorrectly can take a bad situation and make it significantly worse. Understanding when and how to retry safely is what separates a well-designed system from one that actually amplifies its own failures. So the core rule is this: a retry is safe only when the operation is idempotent. An operation is idempotent when executing it twice produces the same result as executing it once. Now, for example, reading data is always idempotent. If you read an order record twice, you get the same order. No harm done in that. Creating a resource with a client-generated ID is also idempotent. If the client sends a create order with ID order 123 and that request is processed twice, the result is still one order with ID order 123. But incrementing the counter is not idempotent. If you increment a counter twice instead of once, the counter is wrong. Charging a credit card is also not naturally idempotent. If a payment request is processed twice, the customer will be charged twice. For operations that are not naturally idempotent, the solution is idempotency keys. The client generates a unique key for each request and includes it within the call. The server stores the key along with the result. If a request with the same key arrives again, the server returns the stored result without re-executing the operation. Now, here's how this works mechanically. The authorized payment function receives an idempotency key, an order ID, and an amount. It first checks the database for a result associated with that key. If one exists, it returns the stored result immediately. No second charge happens. So if no result exists, it processes the payment, stores the result with the idempotency key, and returns the result. If the client retries with the same key, the second execution hits the stored result and the payment is not processed again. Now, how you retry matters as much as whether you retry. If a service goes down and all of its callers retry exactly at the same moment, the service will get hit with a synchronized wave of retry traffic the instant it starts recovering. This can push it back right down. So the solution for that is exponential backoff with jitter. So for example, the first retry waits 1 second, the second will wait 2 seconds, the third retry will wait 4 seconds, and so on. So in that case, for to each wait, you add a random delay between 0 and 500 milliseconds. This spreads the retries out over time so that the recovering service is not overwhelmed. You should also set a maximum number of retries, typically 2 to 3. After that, stop retrying and return the error to the caller. Unlimited retries can overload a service that is trying to recover and prevent it from ever getting healthy again. So we have talked about timeouts and retries. Timeouts prevent a call from waiting forever. Retries give a failed call in the chance. But what happens when a downstream service is not just slow or temporarily glitchy, but consistently failing? If the payment service is failing on every request, retrying just sends more traffic to a service that cannot handle it. Each retry, consumes threads, connections, and time on the calling side and adds load to a service that is already struggling. This is the problem circuit breakers, solve. The concept comes from electrical engineering. In a building, a circuit breaker detects excess current and cuts the circuit to prevent damage. In a distributed system, a circuit breaker detects that a downstream service is consistently failing and stops sending requests to it, giving the failing service time to recover while protecting the caller from wasting resources. A circuit breaker has 3 states. The first state is closed, and this is normal operation. Requests pass through to the downstream service normally. The circuit breaker tracks failures in a rolling window. As long as failures stay below a threshold, everything continues as usual. Now, once failures exceed the threshold, let's say 5 failures within a 10-second window, the circuit breaker transitions to the second state, which is open. In the open state, no requests are sent to the downstream service at all. Every call fails immediately with a predefined error response. There is no waiting, no timeout delay, no resource consumption. The caller gets an instant failure and can return a graceful message to the user, something like, let's say, payment services, temporary, unavailable, please try again shortly. Meanwhile, the downstream service receives zero traffic from this caller, giving it breathing room to recover. Now, the circuit breaker stays in the open state for a configured timeout period, typically between 15 and 60 seconds. After that, timeout expires, it moves to a third state, which is called half open. In half open state, the circuit breaker allows exactly one test request through the downstream service. If that test request succeeds, the breaker transitions back to close and normal traffic resumes. If that the test request fails, the breaker goes back to the open for another timeout period. Now let us walk through why this matters with a concrete scenario. Let's say we have, there is an order service that calls the payment service for every order. Without a circuit breaker, if the payment service goes down, every order request waits for the full timeout duration before failing. If the timeout is 500 milliseconds and the order service handles 1000 orders per second, that is 1000 threads blocked for 500 milliseconds each. Now within seconds, the order service runs out of available threads. It effectively goes down as well, and this is a cascading failure. With the circuit breaker, after 5 failed requests in 10 seconds, the breaker trips to open. From that point, every payment call fails in under a millisecond. Threads are freed almost instantly. The order service stays responsive for everything that does not require the payment service. Only the payment path is affected, and users get a clear, immediate message instead of a long wait followed by a confusing error. So here are the key numbers. A failure threshold of 5 to 10 failures within a 10-second window is a common starting point. And the recovery timeout is typically 15 to 60 seconds, and only one test request is sent in the half-open state before deciding whether the service has recovered. The core idea is that circuit breakers turn slow failures into fast failures. In distributed systems, a fast failure is almost always better than a slow one because it frees resources, gives users a clear signal, and prevents one struggling service from pulling down the rest of the system. Circuit breakers protect a service from a failing downstream dependency. But what about the scenario where a dependency is not failing, but it is just slow, and that slowness drains the resources away from everything else? This is where bulkheads and backpressure come in. These two patterns prevent failures and slowdowns from spreading across the system. Bulkheads take their name from the water weight compartments in a ship's hull. If a compartment floods the float because the damage is contained. Similarly, in microservices, bulkheads work the same way. They isolate the resources so that a problem with one dependency does not exhaust resources needed for other operations. Now here's a concrete example. The order service calls both the payment service and the recommendation service. Without bulkheads, both calls share the same thread pool of 100 threads. If the recommendation service becomes slow and 90 threads are stuck waiting on it, only 10 threads remain for payment processing. Payments slow down because of recommendations, and a non-critical essentially feature is now degrading a critical one. With bulkheads, you assign separate thread pools. Let's say 70 threads go to the payment pool because payments are critical, 30 threads go to the recommendation pool because recommendations are a non-critical business function. If the recommendation service becomes slow and all 30 recommendation threads are stuck, payments still continue unaffected on the dedicated 70 threads. The damage is contained to the compartment where the problem exists. Now, backpressure solves a different problem. When a service receives more requests than it can handle, it needs to signal the callers to slow down rather than accepting everything and degrading for everyone. Without backpressure, a service might accept, let's say, 50,000 requests per second when it can only process 10,000. Response times, they go from 50 milliseconds to 5 seconds, and all 50,000 callers now they get a degraded experience. With backpressure, the service accepts 10,000 requests per second and rejects the remaining 40,000 with a clear signal, which is HTTP 429, too many requests, and tells the caller to retry later. The 10,000 accepted requests get normal performance. The rejected callers know immediately to back off rather than waiting for a slow response. Now, backpressure mechanisms include returning HTTP 429 when at capacity, using bounded queues that reject the messages when full, instead of growing until memory runs out, and implementing the rate limiting per caller so one noisy client cannot starve other callers' resources. In production systems, bulkheads and backpressure together are what prevent a minor issue in one part of the system from becoming a system-wide outage. Circuit breakers get the most attention, but bulkheads and backpressures are equally valuable for failure isolation at a granular level. Let us bring all of the resilience patterns together and see how they compose into a complete defense strategy. We have covered 5 patterns. Each one prevents a specific type of failure. Timeouts prevents indefinite waiting and thread exhaustion. Every outgoing network calls gets a maximum wait time. If the downstream service does not respond within that time, the call fails immediately and the thread is freed. Retries with exponential backoff prevent transient failures from becoming permanent errors. When a call fails, you retry with increasing delay and random jitter, but only for idempotent operations and with a maximum of 2 to 3 attempts. Circuit breakers, they prevent repeated calls to a failing service. After the failure threshold is exceeded, the breaker trips and all subsequent calls fail instantly without contacting the downstream service. This protects the caller and gives the failing service time to recover. Bulkheads prevent one slow dependency from exhausting resources needed by other operations. Separate thread pools or connection pools for each dependency mean that a problem in one compartment stays contained. Backpressure prevents an overloaded service from degrading for everyone. When a service reaches capacity, it rejects excess requests with a clear signal like HTTP 429, and the accepted requests continue to get normal performance. And tying into retries, idempotency keys, they prevent duplicate processing when retries happen. A unique key per request lets the server detect and deduplicate repeated submissions. Now, these patterns are not alternatives. A well-designed service uses all of them simultaneously. A request goes out with a timeout. If it fails, a retry is attempted with a backoff, but only if the operation is idempotent. If the multiple retries fail, the circuit breaker trips. The dependency is isolated behind a bulkhead so other operations continue normally, and the service applies backpressure if its own capacity is certain. Now, being able to explain how these patterns compose together, not just define each one of them in isolation, is what will really help you in the interviews in front of the interviewer. Now, this is something you should write it down for your interview preparation. These 6 resilience patterns come up pretty frequently, and being able to state them clearly and explain any one of them in depth is a strong signal to interviewers. Pattern 1. Timeouts. Every call gets a timeout, no exceptions. Use the P99 latency of the downstream service as a starting point for the timeout value. Pattern 2, retries. Only retry idempotent operations. Use exponential backoff plus random jitter to spread retries out. Set a maximum of 2 to 3 retry items. Pattern 3, circuit breakers. That will be 3 states: close for normal operation, open when a failure threshold is exceeded and requests fail immediately, and half open when one test request is sent to check recovery. Pattern 4, bulkheads. Separate the resource pools per dependency. Assign more resources to critical paths and fewer to non-critical paths so that a problem in one compartment does not affect the other compartments. Pattern 5 is backpressure. Reject excess load with HTTP 429. Use bounded queries that reject messages when full. Implement rate limiting per caller. Pattern 6, idempotency keys. The client generates a unique key for each request. The server stores the key and deduplicates. This is required for safe retries for or any write operation. And here's a sentence that ties them all together, and this is something you should note down as well. Every outgoing call has a timeout. Retries only if idempotent with backoff and jitter, is protected by a circuit breaker, isolated by a bulkhead, and the service applies backpressure when overloaded. If you can state this sentence naturally during an interview and then explain any pattern the interviewer asks you about in depth, you have essentially demonstrated production-grade distributed systems knowledge in that interview. So far in this section, we have talked about how services communicate and how they handle failures. Now let us talk about something that determines whether your services can truly deploy independently, which is contract versioning. In microservices architecture, services deploy on their own schedules. The payment service might deploy 3 times this week. The order service might deploy only once. That means the version 2 of payment service must work with version 1 of order service, and version 1 of payment service must work with version 2 of the order service. If a new deployment breaks existing consumers, you do not have independent deployment. You have a release train where everything has to deploy together, which removes one of the primary benefits of microservices. The rule that makes independent deployment possible is backward compatibility. You can add new fields, you can add new endpoints, but you cannot remove fields that consumers depend on. You cannot change the type of existing fields, you cannot rename existing endpoints. Additions are safe, removals and changes are not. Now there are different strategies for versioning REST APIs. URL versioning puts the version in the path, for example API/v1 orders and API/v2 orders. It is simple and explicit, but it requires routing logic and you end up maintaining multiple versions simultaneously. Header versioning uses a custom except header to specify the version. It keeps URLs clean, but the version is less visible. The preferred approach in most production systems is backward compatible evolution. You can add new fields without removing old ones. Consumers that do not know about the new fields simply ignore them, and no version number is needed. Now here's a concrete example. The original order response returns 3 fields: order ID, status, and total. In an update, you can add 2 new fields: currency and estimated delivery date. The updated response now has 5 fields. Old consumers that only know about the original 3 fields continue working perfectly. They parse the order ID, status, and total, and they ignore currency and estimated delivery because they were not expecting those values. New consumers can read all 5 fields. No version bump is required. No coordination between teams is needed. Now, when you say services deploy independently in an interview, a natural follow-up question by the interviewer would be, okay, how do you ensure that one service's deployment does not break another one? For that, backward compatibility API evolution is the answer. For services communicating through gRPC with Protobuf or through event streams with Avro or JSON schema, the schema defines a contract between producer and consumer. Schema evolution rules determine which changes are safe to make without breaking the consumers. Now let us start with Protobuf, which is what gRPC uses. In Protobuf, each field has a number, a name, and a type. The field number is what matters for binary encoding, not the name. Adding a new optional field with a new field number is safe. Existing consumers ignore the new field because they do not know about it. The new field simply gets skipped during deserialization. Deprecating a field is safe as long as you do not reuse this field number. You stop populating the field, but old consumers that still read it get the default value for that type, like 0 for integers or an empty string for strings. Removing a field and using its numbers is not safe, so a consumer compiled against the old schema would interpret the new field's data as the old field's type. The binary encoding breaks in unpredictable ways here. Changing a field's type is also not safe. If you change a field from, let's say, int32 to string, binary encoding fails because the bytes are interpreted with the wrong type. For event streams, Avro is commonly used with Kafka and it handles schema evolution differently. Avro uses a schema registry where producers register their schema. Consumers fetch the schema and can handle both old and new formats. Avro supports 3 compatibility modes. Backward compatible means the new schema can read data written with the old schema. You achieve this by adding fields with the default values. Forward compatible means the old schema can read data written with the new schema. You achieve this by removing fields that have defaults. Full compatible means both backward and forward. It is the safest but the most restrictive. The practical rule across all schema formats is the same. Always add fields with default values. Never remove fields in the same release that consumers depend on. Deprecate first, confirm all consumers have migrated, and then remove in a later release. If you propose a gRPC or a Kafka in an interview, the interviewer may ask, how you handle schema changes. Knowing the evolution rules for Protobuf or Avro shows that you have thought about the long-term maintainability of the system and not just the initial design. We have talked about versioning rules in schema evolution, but rules can be broken by accident. A developer renames a field and all unit tests pass because they test the service in isolation. The break only shows up in staging after deployment when the consumers start failing. Contract testing catches these breaks before deployment, not after. Here's the problem it solves. The payment service team adds a new field and accidentally renames transaction ID, let's say, to TXN ID. The unit test will pass because they test the payment service on its own. The order service, which depends on the field being called transaction ID, is now broken. But now nobody discovers this until the payment service deploys to staging and the order service starts throwing errors. Consumer-driven contract testing flips the approach here. Instead of the payment service defining what it provides and hoping consumers can handle it, each consumer writes a contract describing what it expects. The order service writes, I send a post to the payments endpoints with these fields and I expect a response containing transaction ID and status. The refund service writes its own contract with its own expectations. Now these contracts are shared with the payment service team. The payment service runs all consumer contracts as part of its continuous integration pipeline. Every time a developer pushes a change, the build runs every consumer contract. If any contract fails, the build fails, and the team knows exactly which consumers would break before the code ever reaches staging or production. The key insight is that the consumers define the contract, not the provider. This ensures the provider never accidentally breaks a field or endpoint that a consumer actually depends on. Changes that no consumer cares about, like adding a new field or a new endpoint, passes all contracts automatically because no consumers have expectation about them. The most widely tool for this is Pact, which supports REST, gRPC, and messaging contracts. Mentioning contract testing in an interview shows that you have thought about the full lifecycle of service communication, and not just how services talk to each other when they're first built, but also how they continue to work correctly as they evolve independently over months and years. In a monolith, debugging is pretty straightforward. One request, one process, one log file, one stack trace. You search the log, you find the error, and then you fix it. In microservices, a single user request can touch 5 to 10 microservices. The request enters through the API gateway, hits the order service, which calls the payment service, which calls the fraud service. An event is published and then it's consumed by the notification service, and each service has its own logs, its own format, its own storage. Without a way to connect the log entries from all these different microservices for one specific request, debugging is pretty hard and pretty much nearly impossible. You have thousands of log entries across multiple microservices and no way to tell which entries belong to the same user request. Correlation IDs solve this. The mechanism is simple, but is super important. When a request arrives at the API gateway, the gateway generates a unique correlation ID, typically a UID. That correlation ID, then is passed in the request headers to every downstream service. The order service receives it, includes it in its call to the payment service, which includes it in the call to the fraud service. When the order service publishes an event, the correlation ID is included in the event payload. The notification service that consumes the event also has a correlation ID. Each service includes a correlation ID in every log entry for that request. This means every log entry across every microservice that was involved in that processing a single user request will share the same correlation ID. Now, when a user reports, okay, my order failed, you go to your log aggregation system, whether that is a ELK stack, Datadog, or any other tool, and you search for that correlation ID. You instantly see every log entry from every microservice that touched that user's request in chronological order. You can trace exactly where the failure occurred. For example, was it in the order service, the payment service, the fraud service, or the notification service? The correlation ID will help you figure that out and will actually show you that easily. The implementation requirements are pretty straightforward as well. The API gateway generates a correlation ID or optionally accepts one from the client for mobile debugging scenarios. Every service reads the correlation ID from incoming headers and includes it in all outgoing calls. Every log entry includes the correlation ID as a structural field, and the log aggregation system lets you search and filter by correlation ID. So when an interviewer asks you, okay, how would you debug a problem in this microservice system? Correlation IDs and distributed tracing are the expected answer. Now let us work through a debugging scenario that tests everything we have just covered about correlation IDs. Let's say the scenario is you have 8 microservices. A user reports that their order was placed, but they never received a confirmation email. The order exists in the database. Now, how would you debug this? Let's take a moment to think about your approach. Which services might be involved? What could be the chain that, point in the chain that would have been broken? So a weak answer in the interview would be that, okay, I would check the logs of the notification service to see if it tried and sent the email. But the problem with that answer is that it jumps straight to one service without understanding the full request path. Maybe the order service never published the order confirmation event. Maybe the event was published, but the message queue or event stream lost it. Maybe the notification service consumed the event, but the email provider was down. Checking one service in isolation does not tell you where in the chain the failure actually occurred. In this case, you are essentially guessing instead of actually doing the tracing. Now, a strong answer would be that, okay, which walks through the system systematically. First, get the order ID from the user's report and look up the correlation ID for that request in the logs. Using the correlation ID, trace the request through every service it touched. Start the beginning, did the order service successfully create the order? The user says yes and the order exists in the database, so this step succeeded. Next, did the order service publish an order confirmed event? Check the order service logs for the correlation ID and look for an event publication log entry. If the event was published, check the event stream or message queue to verify it was persisted. Then check the notification service consumer logs. Did it receive the event? If it did it attempt to call the email provider? What response did the email provider return? This systematic trace tells you exactly where the chain broke. The event might not have been published. The event might not have been delivered. The notification service might have failed to process it, or the email provider might have rejected the send. Each of these scenarios has a different root cause and a different fix. So what makes this answer strong is that the candidate uses correlation IDs, traces the full request path from start to finish, and checks each link in the chain rather than guessing which service would have failed. So we have covered a lot of ground in this section: synchronous and asynchronous patterns, 3 protocols, message queues, and event streams. We also covered commands and events, 5 resilience patterns, contract versioning, and correlation IDs. Now let us bring it all together into a decision framework you can use whenever you're designing communication between microservices. The first question to ask is, for any interaction is that, okay, does the caller need the response to continue? If the answer is yes, the response is required before the next step can happen, like needing to know if the payment was authorized before confirming the order, then the communication should be synchronous. If the answer is no, the work can happen independently, like sending a confirmation email, then the communication should be asynchronous. Now, if the answer was synchronous, the next question is which protocol? For external clients like browsers, mobile apps, and third party integrations, REST is the right choice because of its broad compatibility. For internal service to service calls with a tight latency budget, gRPC gives you the performance and type safety you would need. If clients need flexible field selection across multiple backend services, a GraphQL layer at the edge can aggregate and translate those queries. If the answer was asynchronous, the question becomes queue or stream. If only one consumer should process each message, like task distribution or background jobs, you use a message queue. If multiple consumers need the same event, like broadcasting to payment, analytics, and notifications, you use an event stream. If you need an event replay capability for rebuilding state or onboarding new consumers, that also requires an event stream. And regardless of which pattern you choose, every interaction needs resilience. Every synchronous call should have a timeout, a circuit breaker, and a bulkhead. Every retriable operation should use exponential backoff with jitter and an idempotency key. And every service should apply backpressure when it is overloaded. Now, walking through the decision framework in an interview, choosing different patterns for different interactions, and explaining the reasoning behind each choice is one of the most effective ways to demonstrate communication design skill. The framework itself matters less than the reasoning, so interviewers would want to see that you evaluate coupling, latency, failure modes, and consistency for each interaction rather than applying one pattern everywhere. Now here's a reference card for everything we have covered in this section. Synchronous versus asynchronous. So you use synchronous when the caller needs a response to continue. You use asynchronous when it does not. This single decision determines the coupling, latency, and failure behavior for each interaction. For synchronous protocols, REST is a default for public APIs because of its simplicity and broad compatibility. gRPC is for internal service-to-service calls with tight latency budgets, offering binary serialization, typed contracts, and HTTP2. GraphQL is an edge aggregation layer for clients enabling flexible queries, not a service-to-service protocol. For asynchronous patterns, message queues that deliver each message to one consumer and are best for task distribution and load leveling. Event streams that deliver each event to all consumers retain the event history and support replay, making them the foundation for event-driven architectures. Now, commands decouple the sender to the receiver, events decouple them. Using the correct terminology in the interview signals the understanding of coupling at the message level. For resilience, every call gets a timeout, no exceptions. Retries are only for idempotent operations with backoff and jitter and a maximum of 2 to 3 attempts. Circuit breakers have 3 states and prevent cascading failure. Bulkheads isolate resource pools per dependency, and backpressure rejects excess load to protect accepted requests. For contracts, you add fields, never remove them. Backward compatibility enables independent deployment. Consumer-driven contract testing catches, the regressions and breaks in production before the deployment. For debugging, correlation IDs trace a single request across all services using one unique identifier. And now, these are the 5 essentially common interview mistakes that you should be avoiding. First, saying, something like everything should use REST ignores, different requirements of external and internal communication. Second, not mentioning timeouts implies no production experience with distributed systems, so please don't do that. Third, retrying non-idempotent operation causes duplicate payments and data corruption. Fourth, using synchronous calls for non-critical work like notification adds unnecessary coupling and latency to the critical path. And fifth, having no debugging strategy means you cannot explain how to troubleshoot failures across services. Some key numbers to keep in mind. Protobuf payloads are 5 to 10 times smaller than equivalent JSON. The P99 latency of a downstream service is the starting point for timeout values. Maximum retry attempts should be 2 to 3, with exponential backoff. A circuit breaker typically trips after 5 to 10 failures in a 10-second window. The recovery timeout in the open state is typically 15 to 60 seconds. And Kafka can handle millions of events per second with partitioning. So far we have covered how to define service boundaries, how services communicate, and how APIs are designed and evolved. All of that is pretty important, but none of that actually addresses the problem that makes microservices generally difficult in production. The problem is data. In a monolith, when you need data from two different parts of the system, you write a SQL join. The data lives in one database and joins are pretty cheap. In microservices, those tables they live in different databases owned by different services, potentially running different database technologies. There is no join that works across service boundaries. Every pattern we'll cover in this section now exists to solve that fundamental problem. How do you handle data that multiple services need when each service owns its own database? So we'll start with the core rule here, which is that every microservice must own its own database. Then we'll look at what happens when the teams break that rule, which is the shared database anti-pattern. From there, we'll work through practical solutions. For reading data across services, we have API composition and materialized views. For writing data across services, we have Sagas and event-driven workflows, which we'll cover in depth in section 6. We'll also cover, data duplication as a deliberate strategy, eventual consistency, and its practical implications, CQRS for separating read and write models, and several specialized topics like reference data ownership, search indexing, cache ownership, and reporting. To make all of these topics actually more concrete, let's think about a platform like Amazon. For example, when a customer opens a product page, the data on that page comes from at least 5 different microservices. The product name and description, more likely comes from a catalog service. The stock availability, likely comes from an inventory service. The current price comes from a pricing service. The ratings come from a review service. And the customers also bought section, which is on the page as well. It likely comes from a recommendation service. None of those services, they actually share a database. The product page is assembled from data that 5 independent microservices own separately. Now, how that assembly works, how those services make the data available to each other, and what trade-offs are involved at that scale is exactly what this section is about. The single most important data rule in microservices is this: every service must own its own database, no exceptions. So what does owning its own database actually mean? It means that the order service is the only service that can read from or write to the order database. No other microservice has the credentials to connect to that database. No other service knows the order database schema, the table names, the column types, the indexes. If the payment service needs order data, it calls the order service API. It does not run SQL against the order database directly. The reason this rule exists comes down to one word, which is independence. Without database per service, you cannot deploy services independently. Here is why. If the order service and the payment service both query the orders table directly, then any schema change to that table, like renaming a column, changing a data type, adding a constraint, requires coordinating both services. You cannot deploy the order service migration without first making sure that the payment service can handle the new schema. That coordination is the deployment dependency. And deployment dependencies are exactly what microservices exist to eliminate. Now, there's a second benefit that is equally valuable, which is, when each service actually owns its own database, each service can choose the database technology that fits best its workload. The order service might use PostgreSQL because it needs relational data with ACID transactions. The catalog service might use Elasticsearch because it needs full text search. The recommendation service might use a graph database because it models relationship between products and users. And similarly, the session service might use Redis because it needs sub-millisecond key value lookups. The technology independence is a direct benefit of the database per service principle. In a shared database world, every service is logged into whatever the technology the shared database happens to use. Now, in an interview, when you draw your system architecture on the whiteboard, drawing separate databases for each microservice is the first signal to the interviewer that you understand microservices data ownership. Drawing multiple services, let's say, pointing to a single database, immediately raises concerns about, whether you, the candidate, understand the boundaries that make microservices work. Now that we understand why each service needs its own database, let us talk about what happens when teams do not follow that rule. The shared database anti-pattern is the most common architectural mistake in microservices systems. It happens when multiple services read from or write to the same database, even if they access different tables within that database. Teams fall into that pattern for understandable reasons. Someone says, let's say, it is easier to just query the data directly than to build an API. Or some folks might say, we'll separate the databases later when we have time and bandwidth. Or some folks might say, okay, we'll only read from their tables, we do not write it, so it is fine. Or sometimes people also say that, okay, it is the same PostgreSQL instance, but we use different schemas, so it is logically separated. Now, every one of these justifications sound reasonable in the moment, and every one of them leads to the same outcome, which is coupled services that cannot deploy independently. Now, there are the three levels of shared database coupling, and each one creates its own problems. The first level is the most severe. Multiple services read from and write to the same tables in the same schema. Any schema change across becomes a cross-team coordination effort. So if you need to rename a column, every service that touches that column must be updated and deployed together. The second level is the same database in different tables. Each service uses its own set of tables, but they all live in the same database instance. This is better than sharing tables, but the services still share compute resources, connection pools, and availability. A database outage takes down all services simultaneously, so a long-running migration locks the database for every service. Now the third level is the same instance, different schemas. This offers better logical isolation, but the services still share the underlying compute. A runaway query from one service can exhaust the connection pool, starving other services of connections. A disk I/O spike from one service's bulk operation slows down reads for every other service on that instance. If an interviewer describes a system where services share database and asks you that, okay, what should change first? This should be the answer. Separating databases is the foundation that every other microservices benefit depends on. Now let us walk through a specific scenario that shows exactly how a shared database prevents independent deployment. An e-commerce platform has an order service and a reporting service. Both services query the orders table in the same PostgreSQL database. The order service team needs to improve their address handling. Right now, the shipping address is stored as a single text field. They want to split it into separate columns, which is street, city, state, zip code, and country. This is a straightforward improvement that enables better address validation and more accurate shipping cost calculations. Now here's what happens when they share a database. The order service team writes a migration to add the new columns and populate them from the existing shipping address field. But they cannot drop the old shipping address column because the reporting service reads it. So they go to the reporting service team and ask them to update their queries to use the new columns instead. The reporting service team, says that, okay, they're in the middle of a different project and cannot prioritize the change for, let's say, 3 weeks. Now the order service, team has two choices: wait 3 weeks to ship their feature or maintain both the old and the new columns indefinitely. Neither option is acceptable. Now, here's what happens with database per service. The order service team changes the internal schema however they want. They split the column, migrate the data, and then they deploy. The order service API still includes the shipping address field in its response for backward compatibility, just as we discussed in section 4 on contract versioning. The reporting service continues calling the order service API. It has now no idea that the internal schema has changed. It is not affected at all. The lesson here goes beyond technical coupling. Database per service prevents organizational coupling. Teams can move at their own pace. They do not need to wait for other teams to adapt internal changes. The API is the boundary. As long as the API contract is maintained, each team is free to evolve their internal implementation independently. Now, this exact scenario, an internal schema change blocked by another service direct database access, is a concrete example worth keeping in your back pocket for interviews. It makes the principle, tangible instead of abstract, so that you can share that with the interviewer in the system design interviews. Once each service has its own database, now the next question is which data belongs in which database and how do you decide what a service owns? Now the rule is straightforward. A service owns the data that is the system of record for. So for example, the data that it is fully responsible for. So for example, the service that creates and modifies a piece of data is the owner of that data. Other services can hold copies, but only one service is the authoritative source of truth. Now let's look at some practical examples. The user service owns user profiles. It is where user profiles are created, where email addresses are updated, where account statuses are changed. Other services might cache the user's display name for convenience, but the user service is the authority. If there is ever a question about what a user's current email address is, the user service is the answer. Now, the second example is, let's say, the order service, which owns the orders data. It is where orders are created, updated, and cancelled. The reporting service might have a copy of order data in a warehouse for analytics, but the order service is a source of truth. The inventory service owns stock levels. So, for example, it is where inventory is reserved when an order is placed and where inventory is replenished when stock arrives. The catalog service might display in stock on the product page, but that information originates from the inventory service. Now, the owning service has responsibilities. It must provide an API so the other services can query the data they need synchronously. It must publish events when data changes so other services can maintain their own copies asynchronously. And it must version its contracts and maintain backward compatibility so consumers are not broken by internal changes. The owning service also has protections it must enforce, so no direct database access from other services. The database credentials should be known only to the owning service, no exposing internal schema details in the API. So the API response structure can and often should differ from the database schema. So when you define service boundaries in an interview, explicitly stating which service is a system or record for each entity shows that you have thought about data ownership at a deeper level than just naming services. The order service is a system record for orders is a much stronger statement than just saying, okay, this is the order service. So please make sure you phrase that way in the interviews. So if every service owns its own database and no service can query another service's database directly, how does a feature that needs data from multiple services actually work? The most straightforward answer is the API composition. API composition means calling each service's API and combining the results. Now let's consider a product page in an e-commerce platform like Amazon. The page needs to display the product name and description from the catalog service, the current price from the pricing service, the stock availability from the inventory service, and the average rating from the review service. An API gateway or a backend front-end layer calls all four services in parallel and assembles the product page response from the individual responses. Now, this approach works well under specific conditions. First, the data needs to be fresh. If the product page must show the current price and the real-time stock level, calling the source of truth service at request time guarantees freshness. Second, the number of services is small, typically 2 to 4 calls. So that's the ideal case as well. Third, the downstream services are fast and reliable. And fourth, the call pattern is simple. Parallel fan-out where you fire all requests at once and then wait for all responses is manageable. Sequential chains where one call depends on the result of another one are much more fragile. Now, API composition breaks down in 3 situations. The first is too many calls. If you need data from 10 services to assemble a dashboard, the combined latency and failure probability make the approach not ideal. One slow service delays the entire response. The second is when the data actually needs joining. So if you want to display the top 10 products by revenue, that requires combining order data from the order service with the product data from the catalog service. Now neither service has both data sets and you cannot do a SQL join across the APIs. The third is high volume. If the product page receives 100k requests per second and each request triggers 4 downstream calls, the downstream services now receive 400k requests per second from the single consumer. The fan-out effect multiplies the load. Now, when any of these limitations appear, the alternative is a materialized view, which we will cover next. Also, in an interview, API composition should be a starting point for cross-service reads. It is the simplest pattern. So you propose it first and then you move to materialized views only when you can clearly articulate why composition is not sufficient for the specific requirements. So when API composition is too slow, too fragile, or requires joining data across services, the alternative is materialized view. Instead of calling multiple services at read time, the consuming service builds and maintains its own pre-computed copy of the data that it needs. Now here's how it works. The catalog service, the pricing service, the inventory service, they each publish events when their data changes. A product-based service consumes all the 3 event streams. It builds a denormalized read model in its own database that contains the product name, the current price, and the stock status together in a single row. When a client requests a product page, the product-based service queries its own local database. That is one query, so there's 0 cross-service calls at the read time. Now the trade-offs are pretty clear and they're worth understanding as well. So reads, they become fast. One local database query instead of 4 network round trips. Reads are also, they become resilient. So if the catalog service goes down, the product page service continues serving data from its local copy. So the catalog service outage means, new product updates stop flowing, but the existing product data will remain available. Now the cost of that is actually eventual consistency. When the pricing service updates the price, there is a slight delay before the product page service read model reflects that change. That delay is typically measured in milliseconds to a few seconds under normal load, and storage is duplicated. So for example, the product data exists in the catalog service database and it also exists in the product page service read model. Now materialized views are the right choice when read volume is much higher than the write volume. Product pages are viewed millions of times per day, but prices change thousands of times. They are the right choice when you need data from 3 or more services combined into a single query result. They are the right choice when latency requirements are strict and fan out adds too much delay. And they work when slight staleness measured in seconds is acceptable for the use case. Now proposing a materialized view in an interview is a senior level signal. It shows that you understand the core trade-off for microservices data access. You trade data freshness for read performance and resilience. Now let us test what we have covered so far with a question that could come up in an actual interview. Now the scenario is this. Let's say you are building a search page for an e-commerce platform like Amazon. Now the search results need to show product name from the catalog service, current price from the pricing service, average rating from the review service, and stock status from the inventory service. The search page receives, let's say, 500k requests per second. Now, how would you design the data access for this page? Now, let's take a moment to think about your approach here. Now, a weak answer for that would be, okay, the search page calls all 4 services for each request, then you can parallelize the calls so it is fast. Now, the problem with that answer is that at 500k requests per second, each downstream service receives, 500k additional calls just from the search page. These services also handle their own direct traffic, so the combined load becomes unsustainable. And if any one of those 4 services slow down or fails, the entire search experience degrades. Now, a strong answer starts by recognizing the stick scale. At 50,000 requests per second, API composition would overwhelm the downstream services and add latency that users will feel. Instead, the candidate should propose that, okay, building a search service with its own denormalized data store, like let's say like Elasticsearch, because the search use case requires full text search capability. The search service consumes events from all the 4 upstream services, which is product updated from catalog, price changed from pricing, rating updated from reviews, and stock updated from inventory. It maintains a search index where each document contains the product name, price, rating, and stock status together. Now, when a user searches, the search service queries its own local Elasticsearch index. Zero cross service, calls at query time. So, for example, the search index updates within seconds of any upstream change, which is acceptable for a search results page where slight staleness does not affect the user experience. Now, the candidate should also acknowledge that the trade-off, pretty clearly. Now, the data is now duplicated across 5 locations, which is catalog DB, pricing DB, reviews DB, inventory DB, and the search index. But at 50,000 QPS, this is the only pattern that delivers the performance and resilience that the system needs. So now what makes this answer strong is the reasoning. The candidate does not just name a pattern, they explain why the simpler pattern fails at this scale, propose a concrete architecture with the right technology, explain the event-driven update mechanism, and acknowledge the trade-offs explicitly. So far we have been talking about rating data across services. API composition and materialized views solve that problem pretty well. Writing data across services is fundamentally harder though. And there's a reason why. Let's say, for example, when a customer places an order, 3 things must happen together. The order service creates the order, the inventory service reserves the stock, the payment service authorizes the charge. In a monolith, this is one database transaction. You wrap all 3 operations in a begin and commit statements, and either all of them succeed or none of them do. However, in microservices architecture, there are 3 separate databases with no shared transaction. There is no distributed begin and commit statements that span across all 3. So what happens if the order is created successfully, the inventory is reserved successfully, but then the payment authorization fails? Now you have an order record in the one database, reserved inventory in another database, but no payment in the third database. Now the data is inconsistent across services. Now there are three approaches to handling this. The first is synchronization orchestration. So essentially, a central coordinator calls each service in sequence. If any step fails, the coordinator calls compensating actions to undo the previous steps, which is to cancel the order, release the inventory. This is the Saga pattern, and we'll cover it in much more depth in section 6. The second is event-driven choreography. So in this approach, each service publishes an event when it completes its step. The next service in the workflow reacts to that event. There is no central coordinator. Each service knows only about its own step and the event that triggers it. And this is also covered in section 6. Now the third approach is the simplest and sometimes the best, avoiding cross-service writes entirely. So, redesign your service boundaries so that the data that must change together lives in the same service. Sometimes the right answer is not a clever distributed write pattern, but a better boundary definition. Now this connects directly back to what we covered in section 3 about aggregate boundaries. The aggregate boundary defines what must change in a single transaction. Everything inside an aggregate is a local write within one service. Everything that crosses an aggregate boundary is a cross-service write that requires coordination. Now, good aggregate design minimizes the number of cross-service writes your system would need. Now, when you describe a write operation that spans multiple services in an interview, the interviewer expects you to immediately address what happens when part of it fails. Saying a statement like the order service creates the order and calls the payment service, if you say that statement in the interview without addressing the failure scenarios, that will leave a gap that any experienced interviewer will probe on. Now, one of the hardest mindset shifts for engineers who come from a relational database background is accepting that data duplication in microservices is not a mistake. It is often a deliberate architectural decision that enables service independence. Now, in a monolith, you normalize data to avoid redundancy. The product name exists in exactly one row of the products table. Every query that needs a product name joins to that table. This works because everything is in one database and joins are cheap. However, in microservices architecture, the products table, is in the catalog service database. The order service cannot join to it. When the order service creates an order, it needs to store the product name and the price at the time of the purchase. So it copies that data into its own order items table. The product name now exists in two databases. However, this is not a problem. This is a correct behavior for this architecture. The order service stores the product name at the time of purchase because the product name might also change later. If the seller renames a product, the order record should still reflect what the customer actually bought. A snapshot of the data at the moment of the transaction is the right design. Now the search service stores a denormalized copy of the product data so it can serve search queries from its own index. The source of truth for product data remains in the catalog service. The search service holds a copy that is kept current through the events. Now the notification service stores the customer's email address in a local lookup table so it can send emails without calling the user service for every single notification. The user service is still the authority for email addresses. The notification service has a cache copy that gets refreshed through events as well. Now, duplication becomes a problem in two specific situations. So, first is if two services both consider themselves the source of truth for the same data and both accept writes. Now you have a conflict resolution problem, not a duplication strategy. Second, if the duplicate data is never refreshed and becomes stale in ways that might affect business correctness. For example, if a customer is shown one price on the product page but charged a different price at the checkout because the cache copy was not updated. Now the rule for this is pretty simple. One service should be the source of truth. Other services hold copies. Those copies are either snapshotted at a point in time, like the order capturing the price at purchase, or kept current through events like the search index consuming price change events. Now, in an interview, saying a statement like, okay, I would duplicate the product name in the order record because the order should capture the state at purchase time is actually a very strong statement. It shows you understand why duplication exists in microservices, not just that it happens. Now, in a monolith with one database, every read sees the latest write. The moment you update a price, the next query returns a new price. In microservices with separate databases and event-driven updates, there is a delay between when data changes in one service and when other services reflect that change. The delay is eventual consistency, and it is the default state of a microservices system. Now, let us look at an example to see how this plays out. A seller updates, let's say, a product price from $29.99 to $24.99 in the catalog service. Now, the catalog service publishes a price change event. The search service consumes that event and updates its index. For a few hundred milliseconds or a few seconds under heavy load, the product page shows a new price of $24.99, but the search results still show the old price of $29.99. Now, is this acceptable? In most cases, yes. Most users never notice a sub-second inconsistency between two different pages. The few who do will see the correct price when they refresh. Now, this is a very different situation from a banking system where an account balance must be correct to the penny at every moment. Now, there are situations where eventual consistency is not actually acceptable. So, financial transactions where a debit, must be reflected immediately in the user's balance. Inventory checks at checkout where selling an out-of-stock item creates a costly oversell. Security-sensitive operations where a permission revocation must take effect, immediately. For these cases, the right approach is a synchronous call to the source of truth service at the moment the data is needed. Essentially, in these situations, you trade performance, but for correctness. Now, it helps to have a sense of typical delays involved. Event stream consumption through something like Kafka runs between 10 and 400 milliseconds under normal load. Materialized view updates take between 100 milliseconds and 2 seconds depending on the processing involved. Search index updates in Elasticsearch take between 1 and 5 seconds with near real-time refresh settings. Cache TTL expiry depends on the configuration, but common values range from 30 seconds to 5 minutes. Now, when you propose eventual consistency in an interview, always be specific about which interactions can tolerate it and which cannot. Search results can be eventually consistent, but the checkout price must come from the source of truth in real time. If you say that statement, in the interview, that will show you understand the nuance. You're not saying eventual consistency is always fine, and you're not, saying it's always a problem. You're applying the right consistency model to each specific interaction based on the business impact of staleness. Now, this is a consistency problem that users actually notice. A user makes a change and immediately sees stale data because a read hits a replica or a cache copy that has not been updated yet. Now, here's a classic scenario. A user updates their profile name, let's say from John to Jonathan in the user service. The user service writes the change to the primary database. The user immediately navigates to their profile page. The profile page reads from a replica that has not received the replication update yet, and it still shows John. Now the user thinks the update failed, they try again, maybe they file a support ticket. Now the solution is a pattern called read your writes consistency, and the idea is pretty simple actually. After a user writes data, route the specific user's subsequent reads to the source of truth, the primary database, for a short window. All other users continuing reading from replicas or caches with no change. Now here's how this works mechanically. So when a user updates their profile, the system writes the change to the primary database and also set a flag in the cache that says the user just wrote. Now, on that flag has a short TTL, say 5 seconds. When a read request comes in for that user's profile, the system checks whether the requesting user is the same user who owns the profile and whether the recent write flag is set. If both conditions are true, the read is write to the primary database instead of the replica. After 5 seconds, the flag expires. By that point, the replica has caught up and the user's reads go back to the normal path. Now the insight here is important. You only need strong consistency for the user who just performed the write. Every other user in the system can tolerate eventual consistency and will never notice. A user browsing someone else's profile does not care whether they see a name that was updated 3 seconds ago, but the user who just changed their own name cares immediately. This approach gives you the performance benefits of replicas and caches for 99.9% of all reads, while guaranteeing that the writing user sees their own changes. Now, read your writes consistency is a specific named pattern that interviewers expect senior candidates to know. It demonstrates that your understanding of consistency goes beyond just strong or eventual and into the practical strategies that production systems actually use. Let us talk about a pattern that takes the idea of optimized read models to its logical conclusion. CQRS stands for Command Query Responsibility Segregation. It separates the write model, which handles commands, from the read model, which handles queries, into completely different data stores, each optimized for its own access pattern. Now, why would you want to separate models from reading and writing? Because in many systems, the ideal data structure for writing is fundamentally different from the ideal structure for reading. The write size needs, normalized tables with constraints and asset transactions to maintain correctness. You want referential integrity, for example, unique constraints and proper validation. The read side actually, it needs denormalized documents with pre-computed aggregations and fast lookups. You would want one query that returns everything a page needs without joining the 4 tables. Let's make this concrete with an order history page. The write model stores orders across normalized tables, an orders table, an order items table, a shipping addresses table, and a payment records table. Writes enforce referential integrity and business rules. This structure is optimized for correctness. Now the read model stores a denormalized order summary, one document that contains the order ID, the customer name, the total amount, the item count, the order status, and the last updated timestamp. A single query returns everything the order history page needs, no joins, so this structure is optimized for speed. Now, when a new order is placed or an order status changes, the write service publishes an event. The read service consumes that event and updates its denormalized summary. Now, the two models stays in sync through this event stream. Now, CQRS is justified when read and write volume differ by, let's say, 10 times or more. When the read model needs a different database technology, like writes, going to PostgreSQL and reads coming from, let's say, Elasticsearch. Or when different consumers need different shapes of the same data. For example, the mobile app needs a compact summary, while the admin dashboard needs full details. However, CQRS is overkill when read and write patterns are similar, which is the case for basic CRUD applications with balanced read and write volumes. It is also overkill when a single database handles both workloads efficiently. And it is also overkill when the complexity of maintaining two models and synchronizing them through events is not justified by concrete performance or scalability gain. Now in an interview, the key is justification. Proposing CQRS for a simple CRUD service signals over-engineering. Proposing it for a system with high read volume, complex query needs, and dramatically different read and write patterns signals strong design judgment. Now let us walk through a real-world CQRS implementation to make the pattern concrete. Restaurant owners need to update these menus and customers need to browse those menus on the app. These are two very different workloads. On the right side, the restaurant owners update menus through an admin panel. The data model is relational and normalized. There is a restaurants table with the restaurant ID, name, cuisine, type, and address. There is a menu items table with each item's ID, a foreign key to the restaurant, the item name, description, price, category, and availability status. Now the right side enforces business rules, which is, prices must be positive, categories must be valid, and adding an item and updating the restaurant's item count must happen atomically. Now the write volume is pretty modest, so in a few hundred menu updates per day across all restaurants, a single PostgreSQL instance can handle that easily. Now on the read side, customers browse menus on the mobile app. The data model is completely different. Each restaurant's menu is stored as a single denormalized document. That document contains the restaurant name, the cuisine type, and the full menu organized by category. Each menu item includes its name, price, and availability. The document also has pre-computed aggregations like total available items and average price. One query returns the entire menu page, no joins, no multiple round trips. Now the read volume is dramatically higher than the write volume, millions of menus views per day versus hundreds of menu updates. This is exactly the kind of ratio that justifies the CQRS pattern. Now, the synchronization works through events. When a restaurant owner updates a menu item through the admin panel, the write service publishes, let's say, an event called menu item updated. Now, the read service consumes that event and remills the denormalized menu document for that restaurant. The typical lag is under 1 second. A customer browsing the menu sees a version that is at most a second behind the latest update, which is perfectly acceptable. Nobody noticed that a new appetizer appeared 800 milliseconds after the owner saved it. Now, walking through an example like this in an interview with actual schemas and data shapes for both sides demonstrate that you can implement the pattern, not just name it. Let's do an interview practice problem. Let's say interviewer says that, okay, your e-commerce platform has a product catalog with 10 million products. The catalog page gets 200,000 reads per second. The product managers update about 5,000 products per day. Now, how would you design the data layer? Now, let's take a moment to think about this before we jump into the answer. Now, a weak answer would sound something like this. Let's say a candidate says that, okay, I would use a PostgreSQL database with read replicas to handle the read volume. The replicas can serve the 200k reads per second. Now, the problem here with that this approach is that the PostgreSQL replicas can scale raw read throughput, but each read still requires joining the product table with the pricing and inventory tables. At 200 queries per second with multi-table joins, even a fleet of replicas will struggle. The answer does not address the fundamental mismatch between the product managers edit and what customers browse. Now the write model and the read model need different structures. Now a strong answer would start something like this. It will start by calculating the read to write ratio. So 200,000 reads per second versus roughly 0.6 writes per second, which is 5,000 writes spread across 86,400 seconds in a day. Now the ratio is pretty extreme and it immediately points to CQRS. For the right side, the candidate proposes a PostgreSQL with a normalized schema. Product managers update the products through an admin API. Writes enforce business rules like valid categories, positive prices, and required images. At 5,000 updates per day, a single PostgreSQL instance handles this with room to spare. For the read side, the candidate proposes a denormalized data store optimized for fast retrieval. Each product document contains everything needed to render the catalog page: the product name, description, main image URL, current price, stock status, and average rating, all in one document, and there will be no joins. At 200k QPS, the candidate recommends a combination of Elasticsearch for search queries and Redis for individual product lookups, both populated from events published by the right side. Now, when a product manager updates a product, the write service publishes a product updated event. The read service consumes that event and updates their denormalized stores. The typical lag is under 1 second, which is completely acceptable for catalog browsing. Now the result is faster reads with no join and a clean write model with proper validation and the ability to scale the read and write size independently. The answer works because the candidate does not just name CQRS. They justify it with specific numbers, choose appropriate technologies for each side, and explain exactly how the two sides stay in sync. Now let us go deeper into materialized views because they are the primary tool for making cross-service data available without runtime API calls. A materialized view is a pre-computed query result stored in a read-optimized format. In microservices, the source services like catalog, pricing, and inventory, they publish the events when the data changes. A consuming service listens to all relevant event streams and builds a combined denormalized view in its own database. This view is called materialized because it is physically stored as an actual data, not computed on the fly every time someone queries it. Now, to understand the denormalization, think about an order history page. In a monolith, displaying an order requires joining the orders table, the products table, the users table, and the payments table. One SQL query with 3 joins. In microservices, each of those tables belong to a different service. You cannot join across those boundaries. Now, the materialized views, they solve this by denormalizing all of that information into a single document per order. The order ID, status, and created date come from order service events. The product names and prices at time of purchase are snapshotted when the order was created. The customer name and email come from the user service events. The payment status and method come from payment service events. One query returns everything needed to display the order history. No cross-service calls at read time. Now, keeping the materialized view fresh is handled by the event stream. The view rebuilds automatically as events arrive. If an event is missed or processing fails, the consumer can replay from the last known offset in the event stream. For additional safety, periodic full rebuilds can be scheduled to catch any drift that might accumulate over time. Now, the costs are real and should be acknowledged honestly. Storage is duplicated because the same data exists in the source service and in the view. There is processing overhead from consuming events and updating the view. The view is eventually consistent and lags behind the source by milliseconds to seconds. And the system becomes more complex because event schemas must be maintained and consumers must handle edge cases like out-of-order events. Now, these costs are worth paying when the alternative is calling, let's say, 4 or 5 services at read time for every single request. Now, reference data is a category of data that many services need, but only one service should own. Product names, user profiles, currency codes, country lists, and pricing tiers. This data gets referenced across the entire system. Handling it correctly prevents the most common data ownership conflicts. Now, there are 3 patterns for how other services access reference data, and the choice depends on the freshness requirements. The first pattern is snapshot at event time. The order service needs a product name and price when creating an order. It captures a snapshot of this data at the moment of purchase and stores it in its own database. That snapshot never changes, even if the product name or pricing changes later. The order record should reflect what the customer actually bought and paid, not the current product name. The order service does not need to consume ongoing product events for this data. It captured what it needed at the moment it mattered. Now, the second pattern is an event-driven local cache. The notification service needs the customer's email address to send emails. It consumes the user updated events from the user service and maintains a local lookup table mapping user IDs to email addresses. When it needs to send an email, it queries the local table instead of calling the user service. This is appropriate for reference data that should stay reasonably current but does not need to be accurate to the millisecond. Now, the third pattern is a synchronized API call. The checkout service needs the customer's current default payment method at the moment of checkout. It calls the payment service API synchronously because this data must be absolutely fresh. The customer may have just changed their payment method 10 seconds ago. Using a stale cache copy could result in charging the wrong card, which is a serious business error. Now, the decision between these 3 patterns comes down to one question: what is the cost of staleness? If the data needs to reflect a point in time, use a snapshot. If the data should be roughly current but a few seconds of delay is fine, use an event-driven local cache. If stale data causes business failures, make the synchronous call. These 3 named patterns with clear selection criteria makes your interview answers concrete and actionable instead of being vague. Now, search is almost always a cross-service concern. Think about a search query like, let's say, red shoes under $50 in stock near me. That single query touches data from 4 different services. Product attributes come from the catalog service, price comes from the pricing service, stock levels come from the inventory service. Now, warehouse proximity comes from the location service. No single service owns all of this data, and no single service's data can efficiently handle full text search combined with the price filtering, stock filtering, and geospatial queries. Now, the solution is a dedicated search service that owns a search index, typically Elasticsearch or OpenSearch. An indexer process consumes events from all relevant upstream services and maintains the search index. Each document in the index is a denormalized product record containing all searchable attributes in one place. This is essentially a materialized view, but one that is specifically optimized for search. It supports the full text search, filtering, relevance ranking, and geospatial queries. These are capabilities that no individual service's operational database provides efficiently. Now, this is an important, ownership distinction here. The search service owns the index, the indexer, and the search API, but it does not own the source data. The catalog service is still the authority for product names. The pricing service is still the authority for prices. The search service is a derived read model. It assembles and indexes data from multiple sources, but never modifies or contradicts the source of truth. Now, for consistency, a price change takes between 1 to 5 seconds to appear in search results. This is acceptable because search results show approximate information. A user browsing search result does not expect price to be accurate to the millisecond. The actual price is always confirmed from the source of truth at the checkout time. If a product was $49.99 when the user searched, but the price changed to $52.99 by the time they click through, the product detail page shows the current price. The search result being a few seconds behind does not cause a business error. Now, the search is one of the most common features in system design interviews. Explaining how the search index is populated for multiple services through events rather than querying those services at search time demonstrates a deep understanding of cross-service data patterns. Now, caching in microservices introduces a question that does not exist in monoliths. Which service is responsible for caching data, and which service is responsible for invalidating the cache when the data changes? Now, the ownership rule is this. The service that owns the data owns the cache invalidation logic. Other services that cache a copy of the data should follow the owning service signals, whether those are events or TTL settings, to invalidate their caches. Now, there are three common patterns. The first is a source-owned cache. The catalog service caches its own product data in Redis. When a product is updated, the catalog service invalidates or updates its own cache entry. Consumers of the catalog API automatically get fresh data because the source service manages the cache. This is the simplest pattern and should be the default choice. The second is a consumer-owned cache with a TTL. The order service caches product names locally to avoid calling the catalog service for every order it displays. The cache has 60-second TTL. After 60 seconds, the next request fetches fresh data from the catalog API. This works when slight staleness is acceptable and the consuming service wants to reduce its runtime dependency on the source service. The third is a consumer-owned cache with event-based invalidation. The search service caches product data and consumes product-updated events from the catalog service. When an event arrives, the search service invalidates or updates the relevant cache entry immediately. This provides fresher data than TTL-based caching, but at the cost of consuming and processing the event stream. Now here's a pattern you must avoid. Service A caches data from Service B, and Service B has no idea that Service A has a cache. When Service B data changes, Service A cache remains stale with no invalidation mechanism. There is no event to trigger a refresh. There is no TTL to force an expiry. The stale data just sits there looking correct until someone compares it with the source and discovers they do not match. These bugs are extremely difficult to diagnose because the stale data does not look wrong just on its own. Now, when you describe caching in an interview, always states who owns the invalidation. For example, the statement like, okay, the catalog service caches product data and validates on write is a complete answer. Statements like we cache product data leaves a gap, that any experienced interviewer will notice and question. So you should complete the sentence, and so that paints the full picture. Now, each separate microservices database is optimized for transactional workloads, fast reads and writes for individual records. Analytical workloads have very different requirements. They involve aggregations across millions of rows, trend analysis over months of data, and cross-domain reports that combine data from multiple services. Running these workloads against operational database is a design mistake. Now, here's a concrete example. A business analyst wants to run this query. Let's say, show me the total revenue by product category for the last 90 days. This query needs order data from the order service, product categories from the catalog service, and payment amounts from the payment service. Running this aggregation across 3 microservice APIs would be slow and resource intensive. Worse, it could degrade the operational services for real users. A complex analytical query that scans 90 days of orders should not compete for database connections with the customers trying to place new orders. Now, the solution for that is a separate analytical store. Each microservice publishes domain events to an event stream. An ETL pipeline or stream processor consumes these events and loads them into a centralized data warehouse, something like a BigQuery, Snowflake, or Redshift, or a data lake. The analytical store contains copy of data from all services in a format optimized for aggregation, joining, and thread analysis. Then business analysts query the analytical data stored directly. They never touch the operational databases. Now, this approach preserves the service independence in several ways. Services only need to publish events. They do not need to support arbitrary report queries. The reporting schema can differ from any service's internal schema and can be redesigned without affecting any service. Adding new reporting dimensions does not require changing any service's code, and heavy analytical queries do not affect operational performance for real users. Now, when an interviewer asks you about reporting or analytics in microservices system, they expect the answer is always a separate analytical store fed by events. Running analytical queries directly against operational microservices database is consistently viewed as a design gap. And here's something you should note down in notes for preparing for the interviews. There are 7 data ownership patterns that cover the vast majority of cross-service data problems in microservices. First is database per service, so this is non-negotiable. Each service owns its data store, no shared databases. Second is API composition. Call multiple services and combine the results at the request time. This is best for real-time data from 2 to 4 services. Third is materialized views. Pre-compute the cross-service data from events and store it locally. This is best for high-read cross-service queries where slight staleness is acceptable. Fourth is CQRS, so separate the write model from the read model into different stores, each optimized for its access pattern. This is best when read and write patterns differ dramatically. And fifth is event-driven local cache, so consume the events from the owning service to maintain a local copy of referential data. This is best for data that should stay current but can't tolerate seconds of delay. Sixth is snapshot at event time, so capture the data at the exact moment it is needed and store it permanently. This is best for point-in-time records like the order capturing the price at the moment of purchases. Seventh is analytical store, a centralized data warehouse fed by events from all services. This is best for reporting and cross-domain analytics. The selection rules ties them together. Start with the simplest pattern, which is API composition. Move to more complex patterns like materialized views or CQRS only when you can articulate a specific problem that the simpler patterns does not solve. Too many downstream calls, for example, too much latency, a read-to-write ratio that is too skewed. The complexity of the more advanced patterns is only justified when the simpler approach has a concrete limitation. Now, being able to name these 7 patterns and explain when each is appropriate puts you ahead of the most candidates in interviews. Many engineers know that each service should have its own database, but far fewer know that how to handle the cross-service data problems that it creates. Schema migration is one coordinated change. You update the schema, update the application code, and deploy. In a microservices, a schema change in one service must not break other services that consume its APIs or events. Services deploy independently, often on different schedules, and you cannot force all consumers to update simultaneously. The standard approach for making schema changes safely across independently deployed services is the expand contract pattern. It has 3 phases. Phase 1 is expand, so add the new field alongside the old field, populate both. The API and events include both the old and new fields simultaneously. Existing consumers continue using the old field and they are not broken. New consumers can start using the new field. Nothing changes for anyone who does not plan to change yet. Phase 2 is migrate. All consumers switch from the old field to the new field. This happens one service at a time, each deploying on their own schedule. There is no coordinated deployment, everyone must update by Friday problem. Each team migrates when it fits the sprint. Now phase 3 is contract. Once all consumers have migrated and you have confirmed this through contract test, you remove the old field from the API and events. You stop populating it. The owning service deploys this final cleanup. Now let us walk through a concrete example. The order service wants to replace the single shipping address text field with structured fields: street, city, state, zip, and country. In phase 1, the order service API returns both the old shipping address field and the new structure fields. Both are populated. In phase 2, the reporting service, the shipping service, and the analytical pipeline, each update their own code to use the new structure fields, deploying independently whenever it fits their schedule. Now in phase 3, after confirming that all consumers have migrated and the contract test passed without the old field, the order service removes the shipping address from the API. Now the timeline for this process is typically 2 to 4 weeks, not because the technical work is complex, but because each consuming team deploys on their own schedule. And that is fine. The whole point of the expand contract pattern is that nobody is rushed and nobody is blocked. Now this connects directly to the backward compatibility principles we covered in section 4. The expand contract pattern is how these principles work in practice for schema changes. Now here's a question that tests how well you bring together the patterns from this entire section. Let's say an interviewer says that, okay, the product detail page needs data from 5 different services. How do you avoid making 5 API calls for every page view? And what happens to the product page if one of those services goes down? Now let's take a moment to think through our approach, before you look at the answers. Now a weak answer would sound something like this. Okay, I would call all 5 services in parallel. Parallel calls are fast. If one service is down, I would show a degraded page without that data. Now, if you go say that statement in the interview, the problem with that answer is that parallel calls helps with latency, but they're not with reliability or load. At 100,000 page views per second, each of those 5 services receive 100,000 calls from the product page alone, on top of whatever other traffic they handle. The answer also does not explain how the degraded page actually works in practice, like which data is missing, how does the UI handle it, what does the user see. Now a strong answer will take a different approach entirely. Instead of making 5 API calls per page view, the candidate proposes a product page service that maintains a materialized view combining data from all 5 upstream services. The product page service consumes events from the catalog service for product details, the pricing service for the current price, and the inventory service for the stock status, and the review service for the ratings, and also the promotion service for active discounts. It stores the denormalized product documents in its own database with all 5 data points in a single record. Now, when a client requests a product page, the product page service queries its own local database. One query, 0 cross-service calls. At 100K QPS, this is the only pattern that scales. Now, for resilience, the answer is built into the architecture. If the catalog service goes down, the product page service is not affected at all. It reads from its own database. The only impact is that product updates stop flowing until the catalog service recovers. But existing product continue to be served with the last known data. For a product page, this is perfectly acceptable. The product name and description did not change just because the catalog service had an outage. Now the trade-off for this is eventual consistency. A pricing change takes 1 to 2 seconds to appear on the product page. This is acceptable because the actual price is always confirmed from the pricing service at a checkout time. The product page shows the best available information, and the checkout flow verifies the authoritative information. Now, what makes this answer strong is that the candidate addresses both parts of the question, performance and resilience, with a single architectural decision. The materialized view solves both problems simultaneously, and the candidate clearly articulates the trade-off with a practical mitigation. So when you need data from another service, there is a systematic way to choose the right pattern. Let us walk through the decision tree. The first question is whether this is a read or a write. If it is a write that spans multiple services, the answer is the Saga pattern, which we'll cover in section 6 more deeply. If it is a read, then let's continue. The second question is how many services are involved. If you need data from 1 or 2 services and the volume is low, API composition works well. Call the API directly at request time. However, if you need data from 3 or more services, or the volume is pretty high, a materialized view or a CQRS is a better approach. Now, the third question is whether the data needs to be fresh in real time. If the staleness causes business errors like showing the wrong account balance or selling out of the stock inventory, make a synchronous API call to the source of truth at the moment the data is needed. If the seconds of staleness are acceptable, like for search results, product catalogs, or dashboards, use a materialized view or an event-driven cache. Now the fourth question is whether the read and write patterns are dramatically different. If the reads outnumber writes by, let's say, 100x to 1000x, or if the read model needs a fundamentally different data shape than the write model, CQRS is justified. If the read and write volumes are pretty similar and the data shape is the same for both, a single model is pretty sufficient. The fifth question is whether this is for reporting or analytics. If yes, then the answer always is a separate analytical store fed by events. Never run analytical queries against your operational databases. Now the value of this decision tree in an interview is not about the individual patterns, it's the reasoning process. Walking through the decision tree, arriving at a pattern through systematic analysis rather than stating it from memory, demonstrates the kind of structured thinking that the interviewer is looking for. It shows that you are not just recalling a pattern you have read about, but reasoning through the problem to find the right solution. Let us bring together everything we have covered in this section. So database per service is non-negotiable. Each service owns its own data exclusively, no exceptions. The shared database, is an anti-pattern. It prevents independent deployment and schema evolution. Every benefit of microservices depends on this boundary being enforced. Now for cross-service reads, we cover two patterns. API composition calls multiple services and combines the results. It is simple and works well for the real-time data from 2 to 4 services. Now Materialized views pre-compute the cross-service data from events, delivering high read performance with eventual consistency. Now data duplication is a deliberate trade-off, not a mistake. One service is a source of truth, and other services hold the copies. Eventual consistency is the default in microservices. It is acceptable for most reads, but not for financial transactions or security and sensitive operations. The read your writes pattern handles the most common case where a user must see their own changes immediately by routing that specific user's reads to the primary for a short window after their write. Now, CQRS separates write and read models into different stores. It is justified when read and write patterns differ dramatically and is overkill for basic CRUD. For reference data, we have covered three strategies: snapshot at event time for point-in-time records, event-driven cache for data that should stay current, and synchronous API calls for data where staleness causes errors. Then the next is search indexing is a derived read model fed by events from multiple services. Cache ownership follows one rule: the service that owns the data owns the invalidation logic. Now reporting, it uses a separate analytical store fed by events, never the operation databases. And the schema migration across services uses the expand contract pattern, which is to add the new field, migrate the consumers, and then remove the old field. Now there are the common interview mistakes, that you should be aware of and you should try avoiding during interviews. The first one is proposing multiple services sharing a database is the most damaging interview mistake someone can make. So please don't do that. The second one is calling 5 or more APIs per user request that would create latency and fragility at scale. The third most common, it's a very common interview mistake, is proposing CQRS for simple CRUD, which over-engineers the solution. The fourth common mistake is ignoring consistency trade-offs, which makes the design sound much more incomplete. And the last one is, it's a common mistake that you should avoid is describing caching without the invalidation strategy that leaves a gap, that interviewers will actually follow up and probe you on. Now here's some key numbers to keep in mind. Event stream lag runs, between 10 and 500 milliseconds under normal load. Search index refreshes takes 1 to 5 seconds. Cache TTL commonly ranges from 30 seconds to 5 minutes. The read your write window is typically 3 to 10 seconds after the write. CQRS is justified when read volume exceeds the write volume by 10x to 100,000x. And API composition works well up to 2 to 4 services before materialized views become the better choice. Now looking ahead, we'll be covering section 6, which will address the cross-service write problem that we have identified in this section. When two services both need to update their data as part of one business operations, Sagas coordinate their workflow with compensating transactions for failures. Now section 7 will build on the API composition pattern through the API gateway and backend for front-end layers, which are often where the composition happens in practice. And section 8 will extend the eventual consistency discussion into system-level observability, covering how to monitor consistency lag and detect when materialized views are not fully updated. So in the last section, we'd established a rule that is fundamental to microservices. Each service owns its own database. Now that rule gives us independence, separate deployments, separate scaling, and separate teams. But it also creates a problem that is genuinely hard to solve. So what happens when a single business operation needs to write data across multiple services? Now let's think about, let's say, placing an order on an e-commerce-like platform. That one action touches at least 3 services. The order service creates the order, the inventory service reserves the stock, the payment service authorizes the charge. In a monolith, all of this happens inside one database transaction. If the payment fails, you just roll everything back. The database will never be in a broken state. However, in a microservices architecture, there is no single transaction that spans 3 separate databases running on 3 separate servers. If the payment fails after inventory has already been reserved, you cannot just call rollback. You need an entire different strategy. And this is exactly what this section teaches. We are going to cover why traditional ACID transactions break down across service boundaries, why two-phase commit exists and why it is usually avoided, and then the real solution, the Saga pattern with compensating transactions. We'll go deep into orchestration versus choreography, the transactional outbox and inbox patterns for reliable messaging, idempotency, deleter queues, retry strategies, state machines, and a full worked example of a checkout saga, with multiple failure cases. And this section ties together everything we have built so far, and is the material that comes up most common consistently in system design interviews. So let's get started. Now, to understand why distributed consistency is hard, let us first look at why it is easy in the monolith. In a monolith with a single database, you get 4 guarantees from every transaction, known as ACID. Atomicity means the transaction is all or nothing. Either every state in the transaction succeeds or none of them take effect. Consistency means the database moves from one valid state to another valid state. Isolation means concurrent transactions do not interfere with each other. And durability means that once the transaction commits, the data survives even if the server crashes. Now, as you can see on this screen, the slide shows a SQL transaction for a checkout operation. Now, in one transaction block, we insert the order, update the inventory to reserve the stock, and insert the payment record. Now, if any of these three statements fail, the entire transaction will roll back. The database is never in a state where an order exists without a corresponding payment or where inventory is reserved without a matching order. Now, here's why this breaks in completely in microservices architecture. Now, in microservices architecture, the orders table lives in the order service database, the inventory table lives in the inventory service database, the payment table lives in payment service database. So there are 3 separate databases potentially running on 3 separate servers managed by 3 separate teams. Essentially, there is no single begin transaction statement that will span all 3. And then the problem actually goes much deeper than just databases. If you authorize a payment through an external provider like, let's say, Stripe, you cannot just undo that authorization by rolling back a local database transaction. If you, let's say, reserve inventory in another service's database, issuing a rollback in your own database does nothing to release it. So the core challenge is this. Each service can guarantee ACID with its own database, but there is no built-in mechanism that guarantees ACID across multiple services databases. Every pattern and technique in this entire section exists to handle that gap. And here's why this matters for interviews. When you propose a design that writes data across multiple services, the interviewer expects you to address consistency right away. If you do not bring it up yourself, they will definitely probe you on this. And the fact that you did not raise it proactively signals that you have not thought through the hardest part of the design, so please make sure you cover this during the interview. So if you cannot use a regular database transaction across services, now is there a protocol designed for exactly this problem? There is. It is called a two-phase commit or 2PC. So two-phase commit works by introducing a coordinator that manages the transaction across all participants. The protocol runs in 2 phases. In phase 1, called the prepare phase, the coordinator sends a message to every participant. Can you commit this transaction? So each participant acquires the necessary logs on its data, validate the operation, and responds with either ready or abort. In phase 2, called the commit phase, the coordinator looks at all the responses. If every single participant says ready, the coordinator sends a commit command to all of them. If even one participant said abort, the coordinator then sends rollback to all of them. Now the result is atomic. Either all participants commit or all participants roll back. The transaction spans multiple databases and achieves the atomicity we lost when we moved to microservices architecture. So then, why does this section not end here? So if 2PC solves the problem, why do we need sagas, compensating transactions, and everything else we are about to cover? Because 2PC comes with costs that makes it impractical for most microservices architectures. Understanding those costs is important because interviewers specifically test whether you know why 2PC exists and why it is avoided. So this is what the next slide will cover. So two-phase commit guarantees atomicity across multiple databases, but that guarantee comes at a cost that conflicts with the fundamental goals of microservices. The first problem is blocking and log contention. During phase 1, each participant acquires logs on the rows involved in the transaction. Those logs are held until phase 2 completes. If the coordinator crashes between phase 1 and 2, participants are now stuck holding their logs indefinitely. Every other transaction that needs those same rows are blocked as well. In a system processing thousands of orders per second, this log contention becomes a severe bottleneck. The second problem is that the coordinator is a single point of failure. If the coordinator crashes after sending the prepare messages but before sending commit, the participants are in an uncertain state. They have already voted ready and now they're holding locks, but they do not know whether to commit or roll back. Recovering from this requires a new coordinator to read the transaction log and resume, which adds significant complexity and delay. The third problem is latency. 2BC requires 2 full network round trips to every participant. In a microservices is a system where participants may be in different data centers or different regions. Each round trip has latency. A checkout that would take 50 milliseconds in a monolith might now take 300 to 500 milliseconds with 2BC. The fourth problem is reduced availability. If any single participant is unavailable, the entire transaction cannot proceed. If you have 4 participants each at 99.9% availability, the combined availability of the transaction drops to approximately 99.6%. 2PC trades availability for consistency, and that trade-off conflicts with the microservices' goal of independent service availability. Now, the practical reality is that 2PC works well in tightly controlled environments. 2 databases in the same data center, managed by the same team, with low latency between them. It does not work well for independently deployed microservices with separate databases, separate teams, and separate availability requirements. For interviews, here is an approach that shows depth. You should explain 2BC briefly, then explain why you would choose Sagas instead. You should say a statement something like this in the interview, like 2BC guarantees atomicity, but it creates a blocking, latency-heavy protocol that reduces availability. That conflicts with why we choose microservices in the first place. Sagas achieve eventual consistency without distributed logs, which preserves service independence. With that kind of reasoning is what separates a strong answer from a weak answer. So you should definitely follow that pattern in the interviews. Before we learn the solution, let us make sure the problem is completely clear. We need a concrete scenario that shows exactly why distributed consistency is hard. A customer places an order on an e-commerce platform. Let's say there are 3 services that need to update the data. The order service creates the order record with the status of pending. The inventory service then reserves 2 units of the product, and then the payment service authorizes $599.98 on the customer's credit card. If all of these 3 succeed, the order is confirmed, and then everyone is happy. Now consider what happens when things fail. In the first failure case, let's say the order is created, the inventory is reserved, but the payment fails because the customer has insufficient funds. So now the system is in a broken state. The order exists, the inventory is reserved and unavailable to the other customers, but there is no payment. The customer has not been charged, but the payment is locked. The product is locked up. Now, in the second failure case, that would be when the order is created, but the inventory reservation fails because the product is out of stock. The order now exists with no inventory backing it. If the Saga proceeds to the payment step, we charge the customer for something we actually cannot ship. Then there will be a third failure case. All 3 steps succeed. The order is created, inventory is reserved, and the payment is authorized. But then the order service crashes before it can update the order status from pending to confirmed. The customer has seen charge, can see the charge in the credit card statement, inventory is reserved, but the order is still showing pending. Hence, the customer sees no confirmation in their account. Now, each of these failure cases require a different recovery action. There is no single rollback that fixes everything. For the first case, you need to release the inventory and cancel the order. For the second case, you just cancel the order entirely. And for the third case, you might need to retry the status update or refund the payment and release inventory. This is exactly the problem that Saga solves. Not with one big distributed transaction, but with a sequence of local transactions, each paired with the compensating action that can reverse its effect if something goes wrong later. Now, in an interview describing these specific failure cases before proposing your solution shows the interviewer that you understand the problem much more deeply. So, for example, just naming the pattern, you're actually demonstrating why the pattern is needed. A Saga is a sequence of local transactions. So each transaction updates one services database, and each transaction has a corresponding compensating transaction that can reverse its effect if a later step fails. The key insight to understand is this: a Saga does not guarantee atomicity in the asset sense. It guarantees something different. It guarantees that the system will eventually reach a consistent state, either by completing all the steps successfully or by running compensating transactions for all the steps that already completed when a failure occurs. Now the distinction is fundamental, so let us be very precise about it. A database transaction is all or nothing. Either every statement commits or everything rolls back. At no point is the data in the partially committed state visible to anyone else. A Saga is different. Each step commits immediately in its own service database, so the committed data is immediately visible to the rest of the system. If step 3 fails, step 1 and 2 have already been committed. Their data is already visible, so you cannot just roll them back. What you can do is compensate for them by running new transactions that semantically reverses their effects. And compensation is not exactly same as rollback. There is a point worth being very clear on here. A database rollback discards uncommitted changes. The data goes back to its previous state as if the transaction never happened. A compensating transaction is a new transaction. It does not erase the original, it counteracts it. Now, cancelling an order is not a rolling back the insert statement. It is creating a new state change, setting the order status to cancelled. Refunding a payment state is not undoing the charge. It is creating a new refund transaction on the customer's credit card. The original charge and the refund both exist in the records. Now, there are two main approaches to implementing sagas. The first is orchestration, where a central coordinator service manages the saga and tells each participant what to do. The second is choreography, so where each service reacts to events from the previous step with no central coordinator. We'll cover both in detail in the upcoming slides. So when you mention sagas in an interview, immediately clarify this distinction. A saga is not a distributed transaction with rollback. It is a sequence of committed local transactions with compensating actions for failure recovery. Getting this right shows the interviewer you understand the concept much more deeply, so please do that. Now let us walk through exactly how Saga executes step by step using an e-commerce checkout example. In the forward flow, when everything succeeds, each step executes and commits in its own service database. Step 1 commits the order creation in the order database. Step 2 commits the inventory reservation in the inventory database. Step 3 commits the payment authorization in the payment database. And step 4 goes back to the order database to update the status to confirmed. Now let us walk through the backward flow. Suppose step 3, the payment authorization fails. At that point, step 1 and 2 have already been committed. The order exists. The inventory is reserved. We cannot undo those commits. So the Saga runs compensating transactions in reverse order. First, it releases the reserved inventory compensating for step 2. Then it cancels the order compensating for step 1. Now let us be more specific about what each step and each compensating action looks like. Step 1 creates the order with the status of pending. If compensation is needed, the compensating action updates the order status to cancelled. The order action record is not deleted. It remains in the database with a cancelled status, which is important for auditing and customer service. Step 2 reserves inventory by decrementing available stock and incrementing reserve stock. The compensating action does the reverse, incrementing the available stock and decrementing the reserve stock. The reservation record may also be kept for auditing purposes. Now step 3 calls the payment gateway to authorize the charge. The compensating action calls the payment gateway to void the authorization. If authorization has already been captured as an actual charge, the compensation would be a refund instead of a void. And step 4 updates the order status to confirmed. This is a final step in the saga, so it has no compensating action. If we reach step 4, the saga has succeeded. Being able to list each saga step alongside a specific compensating action for a concrete scenario is a level of detail interviewers expect at the senior level interviews. It proves that you can design sagas, not just cover them abstractly, but can go in much more depth and detail. So let us test what we have covered so far with a question that frequently appears in interviews. Let's say an interviewer asks you this question. Okay, how is a saga different from a distributed transaction? And what happens if a compensating transaction itself fails? Now this is a two-part question, and take a moment to think through this before we start covering the answer. Now, a weak answer would sound something like this. Let's say a candidate says that, okay, a Saga is basically a distributed transaction, but using events instead of 2PC. If a compensating transaction fails, we retry it. The answer is not ideal and it has two problems. Saying a Saga is, quote unquote, basically a distributed transaction is not correct. They have fundamentally different guarantees. And saying like retried, does not also address what happens if retries keep failing. Now, a strong answer addresses the fundamental difference first. A distributed transaction using 2PC holds logs across all participants and guarantees atomicity. The data is never in an intermediate state that is visible to other parts of the system. A Saga does something different. It commits each step immediately in its own database. After step 2 commits, that data is visible to everything else in the system. If step 3 fails, step 1 and 2 are already committed and visible. You cannot roll them back. You must run compensating transactions that semantically reverse their effects. So during the window between the failure and the completion of compensating transaction, the system is in a temporarily inconsistent state. This is the trade-off. Sagas, they give up the atomicity in exchange of availability and service independence. For the second part about compensating failures, the strong answer is layered into multiple things. So compensating transactions should be designed to be idempotent, so retrying them is always safe. You retry with exponential backoff. If retries keep failing because the downstream service is down for an extended period, the failed compensating message goes to a dead letter queue. An alert fires to the operating team, a human operator, or an automated recovery process handles it when the service recovers. The system must always have a path for the scenario. You never silently drop a failed compensation. Now, what makes this answer strong is that it explains the fundamental difference clearly, acknowledges the temporary inconsistency trade-off, and addresses the failure of compensation scenario with a practical layer response. Now let us go deeper into compensating transactions because they are the mechanism that makes Sagas work. A compensating transaction is a new transaction that semantically reverses the effect of a previously committed transaction. It does not undo the original, so it creates a new action that counteracts it. This distinction matters because it changes how you think about Saga design. In a database, rollback discards changes that have not been committed yet. The data reverts to its previous state as if the transaction never happened. Compensating transactions cannot work this way. The original transaction has already been committed. Other services may have already, read the committed data and acted on it. So you cannot just erase what already has happened. You can only create a new action that neutralizes the effect. Now let us look at some concrete examples. If the original action was creating an order with status pending, the compensating action is updating the order status to cancelled. The order record still exists in the database. It is not deleted. This is important because the customer service teams need to see cancelled orders, and auditing requires a complete record. If the original action was reserving, let's say, 2 units of inventory, the compensating action is releasing those 2 units back to available stock. The reservation record may be kept for auditing purposes as well. Now let's say the original action was authorizing a $59.98 payment, so the compensating action depends on the timing. If the authorization has not been captured yet, you void the authorization. If it has already been captured as a charge, you issue a refund. In both cases, the payment record shows both the original transaction and the reversal. Now here is a case where that is easy to overlook. If the original action was sending a confirmation email, there is actually essentially no compensating action. You cannot just unsend an email. This is exactly why notification steps should be placed at the end of the Saga or sent only after the Saga is fully confirmed. Non-compensable actions should always come last, so you never need to be able to reverse them. And these are the 3 design rules for compensating transactions that you should follow. First, every Saga step must have a defined compensating action before you implement the Saga. If you cannot define how to compensate a step, reconsider whether the step belongs in the Saga. Second, compensating transactions must be idempotent. Running, release inventory for order 1 to 3 twice should produce the same result as running it once. This is because the orchestrator might retry compensation due to network failures. Third is some actions simply cannot be compensated. Sending emails, calling third-party APIs with irreversible side effects, and shipping physical products are all non-compensable. Design the Saga so these steps happen last. Now let us talk about the two approaches for implementing sagas, starting with orchestration. In the orchestration approach, there is a central coordinator called the orchestrator that manages the entire saga. The orchestrator tells each service what to do and handles the results. It holds the saga state machine, meaning it knows which step to execute next, what to do when a step succeeds, and what compensating actions to trigger when a step fails. Now the workflow works like this. The orchestrator sends a command to the order service, let's say create this order. The order service creates the order and responds. The orchestrator then sends a command to the inventory service, which is let's say reserve this inventory. The inventory service reserves the inventory and responds. The orchestrator then sends a command to the payment service, authorize this payment. If the payment service responds with a failure, the orchestrator knows that it needs to compensate. It sends a command to the inventory service that release the inventory you have just reserved. Then it sends a command to the order service, which is to cancel the order. Now, the orchestrator is the single place where the entire workflow logic lives. It makes execution decisions and manages the failure recovery. Now, there are clear advantages to this approach. The entire workflow is visible in one place. You can read the orchestration codes and understand the full flow from start to finish. It is straightforward to add new steps or change the order of execution, and all of the error handling and compensation logic is centralized, which makes it easy to reason about. However, there are still some disadvantages. The orchestration can again become a single point of failure. If it goes down, no sagas make progress. There is a risk of the orchestrator accumulating too much business logic. It should coordinate the flow, not perform the business computations. And there is a tighter coupling, because the orchestrator must know about every service participating in the saga. Now, orchestration works best for complex sagas with 5 or more steps, conditional branching, or interset failure handling. In those scenarios, the visibility of having everything in one place outweighs the cost of coupling. Now, when you describe a saga in an interview, the interviewer will ask you whether you would use orchestration or choreography. Having a clear opinion and assessment with reasoning is expected, so please let's prepare for that in the upcoming slides. The second approach is choreography and works very differently from orchestration. So in choreography, there is no central coordinator at all. Instead, each service listens for events and reacts by executing its local step and then publishes the next event. Here is how the flow works. The order service creates the order and publishes an order created event. The inventory service then when it receives it, it reserves the inventory and publishes an inventory reserved event. The payment service is subscribed to that event. When it receives it, it authorizes the payment and publishes the payment authorized event. The order service is subscribed to that event. When it receives it, it updates the order status to confirmed and publish an order confirmed event. The notification service picks up the final event and sends the confirmation email. Now, no service tells another service what to do. Each service independently decides how to react to the events it cares about. The advantages of choreography are compelling. There is no single point of failure because there is no orchestration that can crash. The coupling is looser because your services only know about the events, not about each other. And adding a new consumer is pretty simple. You subscribe a new service to an existing event without changing any of the existing services, and each service commit remains fully autonomous. But there are also a few disadvantages as well. So the overall workflow is spread across multiple services. There is no single place where you can see the complete flow. Debugging is harder because you have to trace events across services to understand what just happened. Compensation logic is distributed, meaning each service must independently know when and how to run its compensating action. And cyclic event chains where service A publishes an event that triggers service B, which publishes an event that triggers service A again. These cyclic events can be difficult to detect and prevent. Now, choreography works best for simple sagas with 2 to 3 steps where the flow is straightforward and the failure handling is not complex. In those scenarios, the loose coupling and autonomy outweigh the reduced visibility. Now, let us compare these two approaches directly because choosing between them is a design decision that interviewers frequently test on interviews. On control flow, orchestration uses a central coordinator that manages the entire sequence. Choreography has each service reacting to events and independently with no central control. On visibility, orchestration gives you the full Saga logic in one place. You read the orchestrator code and you see everything. With choreography, the workflow is spread across multiple services. You need to look at each service to piece together the full picture. On coupling, orchestration creates tighter coupling because the orchestrator must know about every participating service. Choreography is loosely coupled because services only know about the events they consume. On failure handling, orchestration centralizes all the compensation logic in the orchestrator. With choreography, each service handles its own compensation independently, which makes it harder to reason about the overall failure recovery. On complexity ceiling, orchestration handles complex workflows well, even with many steps and conditional branching. Choreography tends to become confusing once you go beyond 3 or 4 steps because tracing the event chain across services become increasingly difficult. Now here's the practical reality of how production systems handle this. Most teams they use orchestration for their most critical workflows like checkout, payment processing, and order fulfillment. And these are complex multi-step flows where visibility and centralized error handling are pretty important. For simpler, less critical flows like analytics updates, notification triggers, and cache invalidation, they use choreography. These are straightforward reactions to events where loose coupling matters more than the centralized control. Now, a pattern that many teams experience is starting with choreography because it feels simpler and more aligned with microservices principles. Then as the workflow grows to 5 or more steps, debugging event chains becomes painful and then they migrate to orchestration. For interviews, a strong answer sounds like this. You can say a statement like in the interview like, okay, I would use orchestration for the checkout Saga because it has 5 steps with complex failure handling and I need the full workflow visible in one place for debugging and reasoning. For downstream processes like sending notifications and updating analytics, I would use choreography because those are simple, independent reactions to the order confirmed event. Now, if you see that statement in the interview, that will be a pretty strong answer. In addition to that, choosing the right approach for different workflows within the same system rather than picking one approach for everything will also show mature judgment, in context of architectural decision making to the interviewer. So please do that as well. Now that we understand sagas, we need to solve the reliability problem that sits underneath them. When a service updates its database and needs to publish an event, how do you guarantee that both happen together? Without solving this, you can lose events or publish events for changes that never actually get committed. Now here's the problem. Imagine the order service creates an order by inserting a row into its database and then publishes an order created event to the message broker. These are two separate operations. Now what if the database insert succeeds but the event publish fails? The order exists but no other service knows about it. Inventory is never reserved, payment is never authorized, and the order is stuck in limbo. Now the reverse is just as bad. What if the event publishes successfully but the database insert fails or gets rolled back? Now other services start processing an order that does not exist in the order service database. Now the solution for that is actually those problems that we just mentioned is the transactional outbox pattern. Instead of publishing directly to the message broker, the service writes the event to an outbox table in the same database as the business data within the same database transaction. So when the order service creates an order, it inserts the order row and the outbox event row in a single transaction. They either both commit or they both roll back. There is no window where one exists without the other. A separate process called a message relay reads the outbox table for unpublished events, publishes them to the message broker, and marks them as published. Alternatively, change data capture tools like Debugging can tail the database transaction log and publish outbox entries automatically, which avoids the latency of polling. Now, this is why this works. The order insert and the outbox insert are protected by the same database transaction, which gives us the atomicity guarantee we need. The message relay handles the eventual delivery to the message broker as a separate concern. Now the transactional outbox is a specific pattern that interviewers expect senior candidates to know. It demonstrates that you understand a subtle but critical point, which is to publishing an event and writing to a database are two separate operations that can fail independently, and you need a mechanism to ensure that they stay in sync. Now let us look at the actual implementation of the outbox pattern, because knowing the concept is good, but knowing the implementation is what sets candidates apart. The outbox table has a straightforward schema. Each row represents an event to be published. It has an event ID as a primary key, the aggregate type, and the aggregate ID to identify which business entity the event belongs to, the event type like let's say order created or inventory reserved, a JSON payload containing the event data, a created at timestamp, and a published flag that defaults to false. Now the code that writes to the outbox is a key part. When the order service creates an order, it opens a single database transaction. Now inside that transaction, it inserts the order row into the orders table and inserts the events row into the outbox table. Then it commits. Both rows either commit together or they roll back together. There is no gap between them. Now the message relay is a separate process that runs continuously. It polls the outbox table for rows where the published flag is false, publishes those events to the message broker, and then marks them as published. Alternatively, if polling latency is a concern, change data capture tools like Debugging can watch the database transaction log directly and publish the outbox entry in the near real time without polling. Now, there is a subtlety here that matters for correctness. What if the relay publishes an event to the message broker successfully but then crashes before it can mark the outbox row as published? On restart, it reads the same row again, and because the unpublished flag is still false, it publishes the same event a second time. This means the outbox pattern guarantees at least one publishing, not exactly once. Events here can be duplicated. Now, this is not a bug. It is a known property of the pattern, and it means that every consumer of these events must be idempotent. Processing the same event twice must produce the same results as is processing, as once. We'll cover exactly how to achieve that in the next few slides. Now here's a question that directly tests your understanding of reliable event publishing. Let's say an interviewer asks you, okay, your order service creates an order and needs to notify the inventory service to reserve the stock. Now how do you guarantee that the event is always published when the order is created? Now, not a good answer would sound something like this. Let's say a candidate says in an interview that, okay, after inserting the order into the database, I publish an event to Kafka. If the publish fails, I retry. Now, that answer misses a fundamental problem. There's a gap between the database commit and the Kafka publish. If the application crashes after the database commit but before the Kafka publish, the event is lost permanently. Retrying only works if the application is still running to do the retry. The answer does not address the atomicity problem between the database write and the event publish. Now, a strong answer would sound something like this. It will identify the problem first, which is, okay, the database commit and the event publish are two separate operations that can fail independently. Now, to solve this, you use a transactional outbox pattern. Instead of publishing directly to Kafka, you rewrite to the event to the outbox table in the same database as the order within the same transaction. Now both the order row and the outbox row either commit together or they roll back together. Now after that, then a separate message relay process reads the outbox table and publishes events to Kafka. After successful publication, it marks the outbox entry as sent. If the relay crashes before marking it, it publishes on restart, which means consumers might receive duplicate events. So consumers must be idempotent, meaning processing the same event twice produces the same result as processing it once. As an implementation option, you could also use Debugging with the change data capture to tail the PostgreSQL write-ahead log and publish the outbox entries automatically. This avoids polling latency and is the approach many production systems use. Now, what makes this answer strong is that it identifies the atomicity problem, proposes a concrete solution, explains the duplicate event consequence and how to handle it, and mentions a production-grade implementation approach. The outbox pattern guarantees that events are published at least once, but at least once means the same event might arrive at a consumer more than once. The inbox pattern handles this problem on the receiving side. Now let us be specific about why duplicates happen. There are several scenarios. The message relay publishes an event to the broker but crashes before marking it as sent in the outbox table. On restart, it publishes the same event again. Another scenario could be the broker delivers a message to the consumer, but the consumer crashes before committing its offset. The broker does not know the message is processed, so it redelivers. Or the third possibility could be network issues, which they cause a retry that results in the broker receiving the same message twice. Now, in all of these scenarios, the consumer receives the same event more than once. If the consumer is not prepared for this, it will process the event twice. In the inventory context, that means reserving twice as much stock as needed, which is not good. Now, the inbox pattern solves this with a simple mechanism. Each consumer maintains an inbox table that records the ID of every event it has successfully processed. Before processing any event, the consumer checks, is this event ID already in my inbox table? If yes, then this event has already been processed, so this consumer skips it. If no, the consumer inserts the event ID into the inbox table and processes the event, both within the same database transaction. Now the transaction is important. Inserting the inbox record and performing the business operation happen together. If the consumer processes the event but crashes before inserting the inbox record, it will reprocess the event on the next delivery, which is safe because the business operation and the inbox insert are atomic. Now, one practical consideration. The inbox table grows over time. You should periodically purge entries older than the message broker's retention period. So, for example, if Kafka retained messages for 7 days, there is no need to keep inbox entries older than 7 days because those travel events, will never be actually redelivered. Now, mentioning the inbox pattern alongside the outbox pattern in an interview, it will show the interviewer that you understand the full reliability chain. Reliable publishing on the producer side and reliable consumption on the consumer side. Now, idempotency is a property that executing an operation multiple times produces the same result as executing it once. In microservices with at least once delivery, idempotency is not optional. It is a requirement for correctness. Some operations are naturally idempotent. Setting a value is idempotent. Let's say set username to Jonathan produces the same result whether you run it once or multiple times. Deleting a record by ID is idempotent. Let's say, for example, delete order 123 succeeds the first time and there is no operation afterward. Similarly, reading data is also always idempotent. Now, other operations like listed over here in the slide are not naturally idempotent, and these are the ones that cause problems. First one, for example, is incrementing a value is not idempotent. So for example, if you say add $10 to the account balance, that will give you a different result every time you run that operation. The second scenario is let's say creating a record with an auto-generated ID. That is not also idempotent because each execution creates a new record. And similarly, sending an email is also not idempotent because each execution will send another email. Now, for operations that are not naturally idempotent, you use idempotency keys. The caller generates a unique key for each logical operation and includes it with the request. The server checks whether it has seen that key before. If it has, it returns the previously stored result without re-executing the operation. If it has not, it executes the operation, stores the result associated with that key, and returns it. Now, the concept was introduced briefly in section 4, but in the context of sagas, it becomes even much more important. Consider what happens in a saga when the orchestrator sends a command to the payment service, let's say, authorize $59.90 for order number 123 with idempotency key, let's say, IK_ABC. Now, the payment service processes the authorization, but the response gets lost, let's say, due to the network failure. Now, the orchestrator does not know whether the payment was authorized or not, so it retries the same idempotency key. Now, the payment service recognizes that it has already processed idempotency key, _ABC and returns the original result without charging the customer again. Now, without that idempotency key, the customer gets charged twice. With it, retry is completely safe. Now, if you propose retries, anywhere in your design during an interview, the interviewer will always ask you how you handle duplicates. Idempotency keys are the expected answer. So most message brokers provide a delivery guarantee called at least once delivery. This means every message will be delivered, but some messages might be delivered more than once. Now, understanding why stronger guarantees are not practically achievable helps you design correct systems. Now let us walk through why exactly once delivery is effectively not possible in distributed systems. Imagine the message broker delivers a message to a consumer. The consumer processes it and sends an acknowledgement back to the broker. But the acknowledgement is lost due to the network failure. The broker does not receive the acknowledgement, so from the broker's perspective, the message was never delivered. It redelivers the message. The consumer now has already processed it but receives it again. From the broker's perspective, it delivered it twice. From the consumer's perspective, it received it twice. Neither side did anything wrong. The network failure made exactly once delivery impossible. Now, these are the 3 delivery guarantees to understand. So, at most once delivery means the message delivered 0 or 1 times. If the delivery fails, the message is lost and no retry happens. This is fast but unreliable. It is acceptable for non-critical data like metrics or analytics where losing a single data point does not cause problems. Now, at least once delivery means that the message delivered 1 or more times. No messages are ever lost, but duplicates are possible. This is the default behavior for most production message brokers, including Kafka, RabbitMQ, and SQS. Now, effectively once is a practical answer. You combine at least once delivery with idempotent processing on the consumer side, so the broker guarantees the message arrives at least once. The consumer's idempotency logic using index tables or idempotency keys ensures the message is only processed once, even if it arrives multiple times. So, the practical approach is pretty straightforward actually. So, you accept at least once delivery as a default, make every consumer idempotent. This gives you effectively once processing, which is the strongest guarantee that is actually achievable in practice. Now, let's say the interviewer asks you about exactly once delivery. The correct answer is that it is not achievable in a distributed system due to the fundamental nature of network communication. But you can achieve effectively once semantics through idempotent consumers. We have talked about retrying failed operations, but what happens when retries keeps failing? You cannot retry, forever, and you cannot silently drop messages as well. Now, dead letter messages queues actually solve exactly that problem. A dead letter queue or DL queue is a holding area for messages that cannot be processed after multiple retry attempts. Instead of retrying indefinitely or discarding the message, the system moves it to DL queue for the investigation. Messages that end up in the DL queue there are several reasons behind them. The first one is, the consumer might have retried, let's say, processing 3 to 5 times and it keeps failing. The message payload might be malformed and cannot be deserialized. There might be a bug in the consumer code that causes a crash every time it encounters a specific message type. Or, the fourth case could be that a downstream dependency might be permanently unavailable for that specific request. So essentially any of these 4 reasons that could lead a message to essentially going to the dead letter queue. Now what happens when the message lands in the dead letter queue? A specific process as outlined here will be getting followed. So for example, the first step will be an alert will fire to notify the on-call engineer that messages are accumulating. The engineer will then likely investigate to determine whether the cause is a bug, a bad message, or a temporary outage. If the issue is fixable, then like a bug that gets patched or a downstream service that recovers, the message can be replayed from the DL queue back to the main queue for reprocessing. If the message is genuinely unprocessable, for example corrupted data or invalid state, it is logged, archived, and removed. Now DL queues are essentially important, are very important, especially in the context of sagas. Let's say consider a compensating transaction like, let's say, release inventory for order 1 to 3. If that message fails after all retries and there is no DL queue, the failure is invisible. Inventory stays reserved for an order that has been cancelled. Customers cannot buy that product, revenue is lost. However, with the DL queue, the failure is captured, an alert fires, and an engineer can ensure the inventory gets released. Mentioning dead letter queues when discussing, message-driven architecture shows the interviewer that, you think beyond the happy path. You're designing for what happens when processing fails, not just when it succeeds. Now, retrying failed operations is pretty essential in distributed systems, but retrying incorrectly can turn a minor outage into a much larger one. Now, here's a scenario that illustrates why naive retries are actually pretty dangerous. Let's say the inventory service goes down for 10 seconds. During those 10 seconds, 5,000 messages accumulate in the queue. When all 5000 messages retry simultaneously, the inventory service comes back up and immediately gets bombarded, with 5000 requests. It cannot handle that increased burst, so it goes down again. The 5000 messages retry again. The service comes back up and gets overwhelmed and then goes down. This cycle will essentially repeat and the service never fully recovers. This is called a retry storm. Now, exponential backup is the first tool to prevent this. Instead of retrying immediately, you wait an increasing amount of time between each retry attempt. The first retry waits 1 second, the second waits 2 seconds, the third waits 4 seconds, the fourth waits 8 seconds. This spreads the retries over time and gives the recovering service space to handle normal traffic before the retry load arrives. Now, but exponential backup alone is not sufficient. If the 5000 callers all start with a 1 second delay, they all use the same backup schedule and they all retry at the same time. Now the retries are synchronized. Adding a random jitter will actually solve this problem. Jitter adds a random delay on top of the backup interval, so all the 5000 callers retry at slightly different times. The recovery service receives a steady tickle of retries instead of the burst. Then you also need a retry budget, which is the maximum number of retries before giving up. For synchronous calls, 2 to 3 attempts is pretty normal. For asynchronous calls, you can do 5 to 10 attempts because the cost of each attempt is pretty low. Now, after exhausting the retry budget, the messages will know they'll move to the dead letter queue. Now, the standard formula for calculating the delay is take the base delay, multiply it by 2 raised to the power of the attempted number, add a random jitter between 0 and the base delay, and cap it at the maximum delay. With a base delay of 1 second and a maximum delay of 30 seconds, the delay look like this now. So attempt 1, will wait 1 to 2 seconds, attempt 2 waits 2 to 3 seconds, attempt 3 waits 4 to 5 seconds, attempt 4 waits 8 to 9 seconds, and then it caps at 30 seconds. Now, an interview saying some statement like, exponential backup with jitter is the expected answer when retries comes up. If you simply say, retry after 1 second, the interview will ask about the retry storms problem. And then you should, definitely cover the concepts we just covered like jitter, retry budget, and the formula we just covered as well.